That is cool. That technology.
Anyway,
But no,
like San Diego,
show up
like Quantum Networking. We have to match my I know San Diego. And so I'm just going to drop a name because I don't know if you know this person. And I said that said, oh, I walk my edge office in Genuflect every day.
We're concentrating on right now quantum stuff. So you're in right here. So I know we are back a long time ago with Texas Instruments making quantum machines on all license. We made some spectacular quantum machines on all license. What happened in the 80s and 90s. Okay. So for us. We made some spectacular devices, but even with the best like we couldn't control it with the quantum well, the tunnel was very control for it with the tunnel next door. So it makes us so great to be nice devices or couldn't combine it together.
Well, I mean, that's the only way to scale some of these transport-based systems. Just because if you try to add more IOs to a single price tag, you basically end up with more lines, generate more heat, generate so it's really low have to go that way. And yeah, that does not require a optical which is the real trick. So without getting too much
it is a lot of it does. And I've got a tall, skinny string theorist. I've got a
see how successful we are. It's a long-term contract. My concern here is that they just does what he wants to, but because he wants to do they have a long
I hope you enjoyed this and other sessions.
Well, because then you guys are yeah, they're using squeeze states for their so it's interesting. Squeeze states are a lot easier to trying to get all
there's a new word that's coming up that's called voluntold.
Well, that's not just that. We've had that one. Receive repeater. You can't put a price tag, right? Or a vacuum channel. Bottom of the Atlantic Ocean. Okay, fair enough. So you and the Quantinuum guys and the Quantinuum, y'all get together and so we're members of the UC. They have a series of talks about foundational technologies, pulling the hard vacuum is one, cryostats is another, error correction. Well, I haven't seen ours do too much in the way of error correction. The QEDC, the CQN guys have incredible error correction. Taking him into that. But I was just at QIP yesterday, and there was a lot of talk of error correction. And I think people are starting to believe now that surface codes are sort of running out of steam, and they're looking for other ways to talk about it. So like the flag. Well, I mean, just in general, there are sort of classes of error correction codes.
Yes, no.
So the question is, how efficient are they?
I tried.
Well, no, I think there's still there was a thing probably about 4 or 5 years ago that started out where you basically take your holographic theory, maybe a CFT, and come up with these holographic characteristics because that was the big thing 4 or 5 years ago, and now people are talking about so anyway, here I'll give you I just got back from the room, so I have a lot of
I am so happy for her. Cool. John oh yeah. Yes.
How far along?
COVID is kind of messed stuff up. And it would send me still pictures of them. You could see who was on the side. Still pictures of everyone. Because that's all. That's all. I'm doing well.
That's right.
Go to Two minutes, ladies and gentlemen. All right, ladies and gentlemen, thank you for being here. I think this is a very exciting opportunity event here that we have because, first of all, we're here at the Capsule Factory. We're going to talk about the implications of quantum. It's South by Southwest, and we're here live in person. And you've got to be excited about it. So, I want to start off talking a little bit about quantum, and I want this to be interactive. I want some audience participation. And so, first of all, any quantum experts in the crowd? Hands up, quantum experts. Okay, now, keep your hands up just for a minute. Those of you that want to be quantum experts, note who they are, and come talk to them at various times. And don't talk to just one of them. Because this one of the things we've learned from quantum is God really does play dice with the universe. Things are ambiguous. And so you'll find, as you'll discover in some of these panel discussions going on, not everybody thinks quantum is going to happen in the same way. So talk to several of them to get the varied opinions. You'll see a lot more of that during the panel discussions. But quantum is this new, exciting, sort of mysterious thing. And you put quantum in front of anything, and it's a lot cooler, a little mysterious. I mean, everybody knows about mechanics. Mechanics are really cool. They fix things. But think about a quantum mechanic. A quantum mechanic can get your car out of the garage without having to open the door. And you put it in front of, quantum computing, quantum communications, quantum cryptography. It's cool. But I'm not sure it works. There's some ambiguity, so I'm not sure it works for everything. I want you to think about quantum veterinarian. First of all, you don't know for sure if the quantum veterinarian really cares about the health of your pet. And second of all, let's say you have a sick pet. You take it to the quantum veterinarian, you leave it there, and a little while later the quantum veterinarian calls you and says, you need to come in back to the office, and you're nervous about this. And you come in and you go, how's my pet? quantum veterinarian reaches underneath the counter, puts a box up on the counter and says, "Oh, your cat's feeling much, much better, just don't open the box." So, all joking aside, we're here to really try to demystify what we can about quantum. And so, audience interaction and participation is important. In this particular event, I'm going to introduce Rick here in a moment. He's happy to take your questions, but you have to hold up your hand and he has to call on you. And so please do ask questions as we go along during his talk. In other sessions later on, you may have to wait till the last 15 minutes or so. Those rules will be described for each session. But please be interactive and ask questions as we go along. So we're trying to demystify quantum, a subject that's a lot of people talk about, and not everybody knows. Actually, nobody knows everything. Richard Feynman famously said, anybody that says they understand quantum mechanics doesn't understand quantum mechanics. But my company, Zyvex Labs, if I didn't say, my name is John Randall. I'm here from Zyvex Labs, and in part representing UT Dallas, which is part of the Quantum Partnership. I helped UT Dallas set up a center for solid-state, atomic precise fabrication of solid-state devices, but the Quantum Partnership also includes IBM, MITRE, and Amazon Web Services. And along with the fantastic help from Mary Wynn here, we've set up this series of sessions we hope you enjoy very much. So now a real treat for me, I get to introduce what I consider a real quantum wizard. Now first of all, my little company works a lot with Sandia National Laboratories. So we work with fantastic Shashank Misra, Scott Schmucker, Esmeralda Busman. These are fantastic quantum scientists, and they all report to Rick. Rick is a senior manager at Mueller, is a senior manager at Quantum, of the Quantum and Advanced Microsystems Group at Sandia National Laboratories, and manages their quantum, Sandia Quantum portfolio for quantum information science. He's also the Deputy Director of Quantum Systems Accelerator, one of the 5 DOE centers for National Centers for Quantum Information Research Center. And Rick came to Sandia in 2003 after having served as Director of Materials Science Simulation Center at Caltech, where he also did his graduate work. Now, don't have to hold this against him, but Rick spent 2 years, 2016 and 17, in Washington, D.C., working on the National Strategic Computer Initiative. Now, although he was raised in Chicago, his mother and grandmother were both born right here in Texas Hill Country, so this is sort of a homecoming for him. I want you to make sure he feels welcome. When not working, Rick enjoys biking and hiking in the New Mexico trails, spending time with his wife, Tess, and his son, Alex. So let's give a big Texas welcome back to Rick Milton.
Yeah, so again, just if you haven't heard it 6 times already, you know, please interrupt, ask questions. This is for you. If I'm saying something that you think is crazy or wrong, quantum experts are willing to disagree, raise your hand and disagree with me. I mean, that'll add to the overall kind of perspective on what we know and what we don't know about science. Excellent. Okay. Yeah, so I'm Rick Muller. I'm from Sandia, and I'm going to be talking about the quantum state. And I apologize for the small size of the font size. So bottom line up front, what I want to leave you with is that quantum information science broadly is important because it changes what we think of as easy and hard. And I want to stress, it doesn't mean that it can do everything. And so sometimes, we're never going to run Microsoft Word on a quantum computer, or at least I hope we never run Microsoft Word. Right? So, but it does some things much better than classical computers or classical processors can do. And those are really interesting things to study. Most of the applications that we hear a lot of hype about are still some way off. There are some things here today that people are doing in quantum information science, and I'll talk about those. And so it's important to know the technology and the opportunities that are coming down the pipe. Okay, so I started by saying quantum makes some hard things easy, and as I was thinking about this, making hard things easy, is always the core of disruptive technology. So, we used to build fortresses in caves or out of, logs, and then somebody invented the wheel, and all of a sudden you could, bring these gigantic stones to your house and build a fortification out of them, right? So, a wheel makes some things much easier, right? Moving around heavy stuff. Telecommunications, right? All of a sudden you don't have to be in person, you can have Zoom meetings for whatever mixed pleasure that is. But again, it changed the things that we thought were easy and hard. And what I want to leave you with in quantum is it just changes some of the things that we thought were easy. Some of the things that we thought were hard are now easy with quantum. And one of the metaphors that we can use here is we can look at lasers and light bulbs, right? So lasers were the first example in technology of coherent light, in much the same way that quantum devices are the first example of coherent information. And so lasers were amazing at many things that regular light couldn't do, but lasers didn't replace light bulbs, right? We have light bulbs still. So lasers do a very specialized set of functions, but they don't replace light bulbs. And similarly, we think quantum information science is going to change a lot of what we do. It's not going to replace everything that we currently use, sensors or communication devices or computing devices for. And the other analogy that's apt with this is that it took a long time for us to figure out what we were going to use lasers for. And I don't think anyone thought, back in the early days that we were going to use them to scan groceries at the checkout, right? I mean, the big application of that is still unknown. And that's the case with quantum as well. So people have proposed a number of applications to information technology, defense, to energy, to finance, to chemistry, to various large industry. We don't know where the big differences are. We don't know what the checkout counter is. Hopefully it's a little more exciting than checkout counters. But we really don't know where the ultimate applications are. I'm going to go through a few here, but it is very likely that not only where quantum's ultimately applied, but also the technologies that make it happen will be totally different than anything that I imagine right now. So if you ask me a hard question, I might just say I don't know, because genuinely, I don't know a lot of these things. Still, these are pretty important technologies, and ones that impact our kind of national and our economic security. So things like cybersecurity, things like inertial guidance, the ability to make chemical reactions work that we can't get working at room temperature and ambient pressures right now. I mean, these are things that people think quantum can impact, and so that's why so many people are excited about the technologies and the field. But again, we don't know exactly what all of the applications are going to be. Okay, so I was 19 when I took my first quantum class, and this was right after that book by Gary Zukav, The Dancing Wu Lee Masters, came out, and I'd read it, and it's all this kind of woo-woo quantum stuff, and I took this class, and I'm like, oh my God, it'll never be boring, and of course, any field that you spend 30 years, 40 years in has its boring aspects of it. What I thought was so exciting was it was just so weird. And so two of the examples, one of which John alluded to in the beginning, kind of get at the core properties of quantum. So everyone's heard of this idea of a Schrödinger's cat. And so in our version of Schrödinger's cat, we're not going to harm any theoretical cats. So you can think of a cat in a closed experiment where there is a 50% chance that a sleeping gas will be released in there. And so there is a chance that the cat is either asleep or awake. And so classically, we think that it's either one thing or the other. And in quantum mechanics, what quantum mechanics tells us to do is that we have to think of the cat before the cat is observed as being in a superposition, being at the same time awake and asleep. And maybe, you know, again, when you first hear that, it sounds like, well, maybe that's just wordsmithing or something. But that actually has real implications on why quantum can do things that classical processors can't do. And then similarly, and I'm not going to go into Bell's theorem and some of the entanglement weirdness unless you guys really want to. But there are, you can entangle particles together, which means that the state of one particle is correlated to the state of the other particle, even if they are separated by, you know, the distance between the Earth and the Moon. You know, we think those correlations hold modulo any disturbances to those things, right? And so what you need to make quantum devices work is some combination of superpositions and entangling operations. And there are applications, so there are quantum communications applications, let's say, that just use superpositions right now. So you don't need everything. But if you want to, let's say, make a universal computing device, you need to be able to make arbitrary superpositions and then have some access to an entangling operation. And that makes a universal computing device. And so, again, you know, just to kind of touch off the story of my idealistic 19-year-old self, you know, what has been gratifying after spending a lot of time in this field is that all those weird things that I thought were kind of so cool that they'd never be boring, you know, actually have implications in why quantum works. Right. I don't know that I can completely explain, you know, exactly why it works, but the math works out. And sometimes in quantum we have to settle for situations where we don't really understand it, but the math works out. Okay, so I wanted just to give you at least, there's room in the front. I wanted to give you guys at least a little bit of an understanding of kind of what kinds of devices people are using to make quantum devices out of. And so these are just cartoons. I think I stole the pictures from Scientific American without attribution, so maybe edit that part out of the video. But you know, what do we use to make quantum states out of? And there are, so you know, there are a whole lot of two-level systems in physics, and you can make a quantum device out of just about any isolated two-level system. And as somebody that reviews a lot of grant proposals, people have proposed just about every two-level system you can possibly think of. But you know, the big ones now are atomic states. So you know, we have this kind of Bohr picture of this planetary model for atoms, and they have orbits that go around them, and they can be in different discrete orbits, right? That was kind of Bohr's insight to this. And so you can choose one of those orbital states as your computational 0 state, and the other one is your computational 1 state. And so you can then do a computational operation by just exciting that orbital from the ground state to the excited state. Right? And it's a perfectly valid way to encode quantum information. One of the nice things about that is that, to a very good approximation, every atom is exactly equivalent. So if you're encoding information in that way, probably, you know, every rubidium atom you use is going to be exactly the same as every other rubidium atom, except for obvious things like, you know, isotopes and things like that. Another way is the polarization of photons. Photons are quantum particles, and you know, we know something, right? We all wear polarized sunglasses to keep glare from coming off the. So you can encode quantum information in, let's say, either vertically or horizontally polarized light, and so you can chop it up, and so a 1 might be vertically polarized, and a 0 might be horizontally polarized, and you can encode information in that way. And in fact, some of the quantum communications strategies use actually the fact that you can not only do that, but you can also make another choice where you do it at, you know, plus 90 or plus 45 degrees and minus 45 degrees from 180 as well. And that you often can't tell. Those are kind of equivalent ways of describing the state. So it's a choice of basis you make. Electron spins. Electrons act like little magnets. They have a spin, so they kind of act like a magnet that can point up or point down. And in fact, my own favorite and John's favorite way of encoding information is in electron spins. So you can encode a 0 in down and a 1 in up, and if you're really, really careful, you can transition between puddles of electrons that have spins pointing down and spins pointing up, and if you've got a magnetic field present, you can distinguish those two. And then superconducting currents. We've got IBM in the house. IBM is developing really amazing stuff based around superconducting technology. And there are a number of different ways you can encode quantum information in superconducting qubits. One of the kind of easiest to understand is you can look at the superconducting current around a loop, and that flux is quantized around the loop. So you can think of it flowing clockwise being a 0, let's say, and counterclockwise being a 1, and you can make superpositions of those states as well. So these are all examples of things that we can make discrete states out of. We can make superpositions out of, so we can make arbitrary mixtures of them. And then ultimately, if we're really clever, we can entangle pairs of those together. And so some of these are then harder to do entangling operations between than others. So like photons, right? Photons don't interact much with other photons. So it's actually fairly hard in photonic quantum computing to get those entangling operations to work. And they go through all kinds of shenanigans to kind of either make them work or do some kind of post-selection to select cases where they've already interacted. Don't ask. Some of these, like superconducting currents, I mean, these are macroscopic scale-ish circuits. So you can use a lot of the same circuit fabrication techniques to make superconducting qubits that have interactions between each other that can form an entangling basis. So, a lot of what people in quantum information science do is just, kind of understand how superpositions and entangling operations work, and then most importantly, how you protect those from noise. Because again, with great power comes great fragility, and so quantum states, their power comes from these very delicate superpositions, but that also means that you just breathe on them or look at them cross-eyed and they all fall apart. Okay, so what can we do with quantum devices? So one of the things we can do is we can do computations today that are currently impossible. And so one of the main things that we would love to be able to do efficiently is make nitrogen into ammonia. Right? That's the core of the green revolution in fertilizers. Currently it's been estimated that 2% of the world's energy goes into a single chemical reaction, the Haber-Bosch process. And the Haber-Bosch process takes really high temperatures and really high pressures to work. And in fact, there is a phenomenal Radiolab episode on Haber, who was the first person in the Haber-Bosch process, which I can't recommend strongly enough. But in any case, so 2% of the world's energy goes into doing the Haber-Bosch process in factories somewhere. But of course, plants do this all the time, and they don't need high pressure, and they don't need high temperatures to do this. There are little nodules on roots that can actually use an enzyme called nitrogenase, and just at ambient pressures and temperatures, make this reaction work. So nice work coming out of Matthias Schroer's group at Microsoft has estimated that we only need something like 200 error-free qubits. And so for those of you who know something about quantum, error-free should be sending out big alarms right now. But if we could make error-free qubits, we'd only need about 200 error-free qubits to really model nitrogenase exactly. That doesn't mean that we can necessarily portions of the active site of that enzyme and put it in an industrial process. This is why we have a chemical industry, right? These are hard problems, even when you understand everything about the catalytic pathways. But nonetheless, that's the type of thing that could be possible today, that's possible with quantum computers, that's impossible without.
So Rick, you mentioned, and it's very true, there's a limited number of problems that right now we know that the quantum algorithms are very good at. But understanding quantum chemistry and quantum physics in a way that we can't do if it doesn't do anything else, wouldn't you say that this is an outrageously valuable thing to have?
Yeah, this is, I mean, again, and this is why, so, I work for a national laboratory. One of the things that we do a lot of are materials under various conditions that you might not have normal materials under. So being able to simulate materials under high temperatures and pressures, understanding how well armor works or how well things resist heat or pressure. These are really important things. And again, this is one of the reasons why so many people are excited about quantum right now. But it doesn't just do computations. The other thing that quantum devices could do is enable provably secure communications. So, for anyone who has worked in kind of information science or communication theory knows about Alice and Bob. Alice and Bob want to be able to communicate securely with each other, but there's this horrible Eve who's in the middle who is an eavesdropper. And so Alice and Bob want to call each other up on the phone and say, oh, I've got this great stock tip, you should buy Yoyodyne, but then Eve finds out about it and does it. So one of the things you can do between Alice and Bob is you can use a technique called quantum key distribution to distribute a cryptographic key that you can use to encrypt that conversation. And this is kind of the same strength as a one-time pad type of cryptographic system. So it's about as given a long enough key size, it's about as secure as we know how to make encryption. So what Alice and Bob do, this is with the photon polarizations as well. And so Alice and Bob basically send 4 times as much information to transmit the key as they need. And then Bob just guesses how those were encoded. And then Alice calls up Bob afterwards and tells Bob which of those were correct and which weren't. And based on that, with that you can then kind of determine, that's where that factor of 4 comes from. You can determine what the cryptographic key was of a proper size, and then you can encrypt that. So now so then the nice thing is that if Eve listens in, that destroys those superposition states, right? Because she's one of the things that happens to quantum superpositions is when you measure them, when you observe them, you no longer have the superposition anymore. It's either one state or the other state. And so you can not only detect when an eavesdropper is on the line, but you can also make sure that they're not getting any useful information, because you still need then the kind of, I guess lasers don't work on anti-reflective coated surfaces. So Eve can't get any information out of the process. There are all kinds of caveats. There's a reason why we don't all have quantum key distribution telephones right now. In fact, we've got some expertise in the audience and people who deal with some of those photonics issues. But this is another area of the promise, and this, in fact, is one of the things that China is investing heavily on: ground to satellite communications that are QKD encrypted. Well, I won't editorialize, but you can ask questions. So another thing is quantum networking. So one of the things we can do is we can entangle computers together. So let's say, I keep on expecting the doc to show up on the anti-report. So let's say I've got a computer. Sandia has a quantum computer called QScout. The Quantum Scientific Computing Open User Testbed. We spend too much time doing acronyms. So, you know, we have a computer in one lab, and let's say, you know, Betty makes another computer in the lab next door. We can use encrypted networking to basically make those two computers act as they are a single computer. So they can communicate with each other at high speed, at high data rates, everything. And so unlike quantum communications in the previous example that just uses superposition, here you really need to create and distributed entangled pairs of something, probably photons, we think. And so this is something that the city of Chicago is working heavily with, and a lot of the others. So I'm co-director of one of the 5 DOE quantum centers, and we pretty much just do computing. But some of the other centers really focus on networking capabilities and communication capabilities as well. And so this is the promise. We also hope, I'm going to get to quantum sensing in a second, there are all kinds of promises we can get by collecting quantum information as well. And we can network those in and kind of have access to the full quantum degrees of freedom of that information. Okay, so now quantum sensing. So you know, again, you know, I mentioned how quantum superpositions fall apart, cross-eyed, and so you can use that hypersensitivity that quantum states have to actually make very accurate sensing devices. And so one of them is position, navigation, and timing devices, which is extremely important to the Department of Defense because, of course, the first thing that goes down in any arena is something like GPS. So all of a sudden you don't know where you are. And so the question is, how do you navigate in environments where there aren't GPS? And it isn't only warfare, right? You might be underground and you don't have access to the GPS satellites. So one of the things you can do is you can make what are called atom interferometers. So these are states of atoms in some vacuum that we put in a superposition, kind of in the paths that they take, and then you then interfere them at the end. And so if you've heard of the LIGO gravity detection experiment, this is based on kind of similar technology, although I think that was photonic actually. But we make them out of atoms here, and so these have all kinds of applications. One of the things Sandia wanted to do, I know I'm not supposed to be talking about Sandia, but one of the things Sandia wanted to be able to do was then miniaturize that. So these things now exist in kind of laboratory scale, the big optical tables right now. And we wanted to, I mean, but we did things like, it's not showing up on the fucking screen, vacuum package, so we don't need to have a vacuum pump anymore to hold a good vacuum there. And so again, in addition to sensing acceleration, sense gravity, so like mapping out the Earth's gravitational fields a really big deal for a lot of positional sensing applications. It's also big for like oil exploration, right? You can potentially see underground cavities, right? So you can see when the mass changes. In fact, I was at NIST and looking at the watt balance, which is the new standard for the kilogram, and there was a big, so it's like 10 floors below ground, and there was a big rock on the other side of the wall, and they could actually sense the presence of that rock with their atomic apparatus there, right? So gravity was actually different from one side of the room to the other. I know Jun Yi at CU Boulder and Jilla has this experiment where he can take a atomic clock and raise it like, you know, millimeters and actually sense the difference in the gravitational field by just raising it up, you know, millimeters now. I thought it was meters, and I was corrected that they're now millimeters. Yeah.
So with so thinking of interferometers, INSs, and stuff like that,
yeah.
we talk navigation. One of the biggest challenges is drift.
Yeah.
Right. So that's what we use with. So with the fragility of
yep.
it, like how would you deal with drift? Like, are you exponentially causing drift to be more of a problem?
Yeah, and so one of the solutions, right, this is always the cop-out in technology, is you make a hybrid device, right? You then take maybe a kind of tactical grade navigational system and you correct it with the quantum things. And we also think like the one we've developed works along a single axis now. It doesn't do multi-axis, right? So you can't do gravitometry with it. But no, drift is, and so this is enough out of my field of expertise that I'm just going to repeat the things that I've heard my people say, which is that you basically have to track the fringes in these atomic oscillation states and kind of figure out where you are. You basically count fringes, I think, and that then lets you handle drift. But you know, drift is still very much a current research topic right now.
Because that's what we used to do, right? With the old INSs, like we used to fly.
Yeah, Will.
So just to go further down that topic, there are people working on quantum networked devices so that they can actually synchronize the clocks between devices. So when one of them goes out of sync, it actually is self-correcting as a network. So.
Yeah, and DARPA is the only part of the government that actually spends more time on acronyms than Sandia does. and DARPA's project is called ROCKET, which stands for Robust Optical Clock Networks, which, you know, you have to kind of stand in awe of that kind of program. Yeah, question about.
Can you use one of these quantum devices to explore all possible acronyms in parallel?
Yeah. Technically, no, but. Okay, so then the other thing I wanted to capture something about what people. So in addition to sensing gravity, you can also sense electric and magnetic fields. And one of the exciting things people are doing is making brain scanners and brain-computer interfaces. So, you know, right now, you know, if you go into an MRI machine, it's this gigantic superconducting magnet that you sit in the middle of, and, you know, you have to be there all day. So you can literally reduce this to the size of kind of a shower. It's development, so it's a lumpy shower.
Football helmet.
Football helmet, perfect. We are in Texas after all. So like a football helmet-sized device, and you've got these optically pumped quantum magnetometers that are very sensitive electric field devices that can see the kind of three-dimensional distribution of electric and magnetic fields that are going on inside your head. And again, you know, so as someone who's read way too much science fiction, you know, there are all these brain-computer interfaces. This is some of the technology that ultimately could go into kind of making, you know, kind of high data network between your brain and some computer system, which of course then leads to Skynet or something.
So actually, Xilinx has a subcontract to Teledyne to working on the DARPA N3 program, where they're using these optical paramagnetic sensors, so they come up with the opium.
Oh, right, exactly. Yeah, that's worth at least $500,000 in funding right there. Okay, so now I saved the worst for last, and I particularly apologize for the small part of this one. Okay, so I wanted to talk about errors and how to mitigate them, because one of the main areas where, you know, people talk about this technology as if we're going to, you know, be cracking cryptosystems and solving the photosynthetic error tomorrow. The reasons we're not is that quantum devices have many more ways of making mistakes than classical devices do. Classical devices typically just have goes to a 1. Quantum devices, because it's a kind of richer set of information, have many other ways of making mistakes. And in fact, so you know, day one of the ENIAC computer, which is one of the first vacuum tube-based computers we ever made, day one, the ENIAC is accurate to 1 part in 10 to the 16th, right? So, you know, it made a bit flip error for every 10, you know, whatever that is, octillion operations, right? So we actually developed all of this sophisticated mathematics for error correction that we never needed because classical computers were already so accurate that we didn't need it at all, right? And like transistors today are 1 part in 10 to the 28th, right? I don't even know that's like age of the universe type thing, right? Quantum computers are about 1 part in 10 to the 3, which means you can kind of do 1,000 operations without a mistake. Well, those of you who know something about counting operations and computing devices know 1,000 operations is not very much. So, but luckily, they worked through all of this really great error correction mathematics when they in the early days of classical computing and in communications, right? So our cell phones use error correction because we're talking through noisy channels. So we know that we can go from 10 to the minus 3. If you can get below a threshold, which we think is roughly 1 part in 1,000, you can then correct the errors of that, but you need a whole lot of qubits. And that's why the people that were experts in this field might have smirked a little bit when I said 200 error-free qubits, because to make a single error-free qubit takes somewhere, we think somewhere between 100 and 1,000 normal qubits. So, if I say it takes 200 qubits, perfect qubits, you should think somewhere between 20,000 and 200,000 real qubits. So, obviously in a world in which we've made, 80 qubit devices, we're a long way away from 20,000 or 200,000 qubits. And a lot of how we're going to advance the field will result in having more intelligent encoding schemes. But frankly, sometimes you kind of hope that a miracle breakthrough is going to occur and somebody gets some huge thing, because this is just a kind of major impediment right now in terms of the number of qubits you need to do the big computing applications that we want to be able to do. But we've got a lot of really, really smart people working in that area.
So for the layman, what is the improvement from the 1 to 1,000 that happens with these mathematical corrections?
Okay.
Like how much closer are we getting to the 1 and 10 to the 28?
So think of it like with each doubling in the number of qubits you have, it gives you an extra factor of 10 in accuracy or something like that. I think I probably have the ratio flipped around, but that's what you're doing. So you can take a bunch of 10 to the minus 3 qubits and maybe make a 10 to the minus 5 qubit out of that. And so, similarly, you can take a bunch of 10 to the minus 5 qubits and make a 10 to the minus 8 qubit out of that. And so that's called code concatenation. And that actually isn't the way people are doing it now, but that's kind of the idea. And you can think of it like a repetition code, right? So in classical communications theory, you can just repeat something 3 times, right? So instead of sending a 0 to you, I can send 3 zeros and you do majority voting, right? So even if there was a single error there, you know that 2 of those there, and you can work out the probabilities, right? What does the error rate have to be before I get an error in a distance 3 repetition code, right? So if it's greater than whatever, I can't think when I'm in front of people, so I'm not going to try to do the math. But and if you have 5, well, you can have more errors in that channel than if you had 3, and so repetition codes work really well for classical communications. So you can think that we're doing something like a repetition code, but we've got, instead of just 1 dimension of error, so like the bit flip 1, we can also make a whole other dimension of error. So instead of 3, maybe you need 3 squared, right, is just a way of then thinking why the resources rise so fast in correcting errors for quantum devices. And it's a great, this is not something, probably obviously, that I'm expert in, but we have people that are experts in them, and it's one of the most kind of intellectually stimulating area of this. Although I haven't seen major breakthroughs. I haven't seen the miracle, right? So it's like nobody expected the FFT, right? You know, when people figured out how to do the fast-Fourier transform, it made a lot of operations, you know, and that was just doing operations more intelligently, right? But it just totally changed the way that we could do signal processing, right? And so I feel like we're kind of, you know, multiple FFTs type breakthroughs away from being able to make this work.
Yeah, so one of the things to improve the fidelity of the qubits, the reliability, and drop the error rate is coherence time. And different systems have different lengths of coherence times. So going to systems that have longer coherence times and going to great efforts, the area I know well, silicon quantum computing. You want to go to isotopically pure silicon, you get rid of the unpaired nuclear spins, which can cause decoherence. And so it's both a numbers game, getting a large number of physical qubits to make up a logical qubit, but it's also just improving the engineering of the material system in the particular two-level system you're working with.
Yeah, and so like the people that make superconducting qubits not only work on, you know, making pure superconducting materials to make those qubits out of, but they also change the way that the qubits work to be kind of tailored to the noise environment. So, you know, if you've got a kind of high charge noise environment, you can kind of push that qubit behavior in a different direction to get better behavior. And there are a lot of trade-offs being made like that.
Also, it's not just coherence time, it's gate speed.
Right, exactly. So it's kind of the ratio between the two that gives you the error rates. Okay, so, you know, something that you probably already know, quantum is growing worldwide. It's actually hard to find really up-to-date business. These are from like 2019 and 2017. But you know, patents are growing worldwide now, and it's not just the United States that are patenting everything. So you know, China has a huge number of patents. There was a nice article in The Economist in 2017 that started to kind of break down patent applications by different areas. And so the United States has the majority of the quantum computing ones. China has a lot of the quantum cryptography and communications-based ones. Sensors, I think it's spread much more evenly. So this is a worldwide game now, and it's probably going to take, you know, the best minds from the world to really make this work ultimately. You know, there are near-term applications now. So you know what I've hopefully left you with is some way of separating the science from the science fiction in this. So, you know, quantum has a lot of power. It is not going to do everything, and we're still a long way away from it doing all of the things that we know it can do. But there are a lot of near-term applications in sensing and communications that people are exploring now, and some of these you can even buy kind of turnkey solution devices for. And again, I've been doing research for, let's just say, 30 years, and this is the best field I've ever worked in. These are the best people I've ever worked with. It's just the most, you know, so thinking back to that idealistic 19-year-old, you know, for me personally, it isn't that the field itself is so exciting, but the people I've found working with in this area are just the best people I've ever worked with. So it's just been a blast. So I think I'm formally out of time, but I'm happy to answer any questions.
Of course. So we just talked about China and the U.S., and I'm sure there's European counterparts that are really developing knowledge. Is there any country that's surprising us with their knowledge base or patents? Kind of dark horse?
That's a good question.
I think you would name
I haven't looked beyond China, to be honest. I just kind of good.
So it's interesting that
you can tell what governments.
For all the things that Erdogan is not. Erdogan is cued his entire culture to be one that is technological.
Yeah.
And he's incentivizing STEM like no other country, maybe.
Interesting. Okay.
So.
Yeah, that would be interesting to take a look at.
Yeah, place a look. Anybody else who's got thoughts about it?
Yeah, no, I mean, you know, the places that I know. Sorry?
So I take a couple of courses online, and most of the students that I take it out of Latvia Q World.
Oh, that's fascinating.
And so there's Polish, there's Indians, there's everyone from Europe. Yeah, everybody's basically in there getting their feet wet and trying to learn, and most of what we're doing is computing
Yeah.
algorithms, you know, edge detection, image processing,
Oh, that's excellent.
optimization,
Oh,
things
that's
like
great
that.
stuff.
So,
Yeah.
I think that's where there's gonna be a lot of, growth, is basically in the algorithm or software as a service. Basically, you send up your problem and get a result back.
Well, Olivia can tell you some of the stuff she's doing.
Yeah, question over here.
Okay.
I think
Yeah.
it was in 2015 that there was a quantum machine learning paper published, just stating that like the set of possibilities that could be there. And precisely one thing that was not in your presentation was about quantum machine
Yeah,
learning.
yeah.
So what 7 years later, how is the state of the field?
Yeah, so that's a great question. So the question for everyone is, you know, we also all know about AI and machine learning, and it's a really hot topic. So if you've got, you know, quantum and you've got machine learning, why don't you put them together and see if there's some synergy? You put two of the hottest things together, and it's like Brangelina or something. And so just, I mean, I guess personally, I'm still something of a skeptic. But you know, the smart people that work in my group on this seem to think that there's something there that you can use quantum either devices to implement machine learning, you know, so you can use them instead of the little neuro-inspired circuits. So you can use quantum devices to either, you know, run them, or you can use quantum algorithms and quantum data to train them. And I believe that's still thought of as promising, but I haven't seen a killer app in that area.
But there is a lot of work in that in the QCNNs, quantum convolutional neural networks,
Yeah.
TensorFlow Quantum. So there is some published papers out there, and there's practice being done and research.
Yeah.
Now, what about QKD and blockchain? Any synergies or overlap?
I am sure there's somebody working on those. I don't, you know, so you can imagine. I don't know if like having secure communications solves any of the bad actor characteristics in blockchain, right? You know, most of the things are like 50% attacks, and I don't know, but you know, maybe you can do something where you have some. I mean, there are all kinds of applications of quantum. You're like zero knowledge proofs, where you can, you know, or like what do they call it? I'm blanking on it. Yeah, blind computing, where you can compute on encrypted data, even if you don't know how to decrypt it, right? So there are, and I'm sure with all the startups in quantum right now, somebody's doing quantum blockchain. So yeah, question on that?
Pilots that you have out there, what are the most practical applications that you're seeing today from those pilots?
So near term or long term?
Right now.
Right now, you know, there are some quantum computing algorithms. They're called variational quantum algorithms that actually seem to work hybrid. So you have kind of a classical computer drive a quantum application, and some of those look promising, and some of the work done at some of our partners may have enough qubits to really start probing those right now.
Seems optimization, I think, is
yeah.
is
So
one of the key ones.
so one of those variational quantum algorithms is called quantum.
UAOA.
Yeah.
So
I can't remember the acronym.
there's also not a gated quantum computer, but a whole D-Wave action,
Yeah.
where it's using qubits of a sort, not in a gated way, to do optimization problems. That they're showing a lot of promise of. It's a great way to do optimization. They haven't, to my knowledge, the last thing I saw, they haven't really beaten the best supercomputers at optimization, but as they build up the number of qubits and improve that, it looks like a very attractive way of solving a subset of problems that are important. Optimization problems obviously are very important.
Yeah, and it is particularly difficult to really tell how, you know, when approximating a hard optimization here. Right? So this is like traveling salesman problem, right? You want to visit all of the major league ballparks, starting from Austin in the shortest path. right? So that's something that we actually know is called NP hard, right? That's in that hard computational category. And so we don't think that quantum computers can actually solve it. In fact, we are relatively certain that even quantum computers cannot solve NP hard computational problems. However, there's this whole subfield. So today I learned there's this whole subfield called theoretical computer science, where they do things like categorize computational problems into all of these subclasses, and it's like, you know, BQP and MIP star, and you know, you just think they're making stuff up, but it's fascinating work to the very small extent that I can understand it. But one of the things that I think is fascinating is that nobody understands how hard it is to kind of take a kind of NP hard problem, and then how much does approximate, right? What if you only want to get like a 90% solution, right? Though, you like ask a theoretical computer scientist and you think they're just going to give you an answer, and they just start talking about, well, no, there's the structure of these problems, and you never really see the hard, right? You can think of optimization problems that are very easy to solve because they're already close to their global solution, right? And so I'm blathering. The point about optimization on quantum computers is that even if you can't solve them exactly, or even if D-Wave can't solve them exactly, they might have a very good way of approximating them. And since that's so important in logistics, shipping stuff and planning routes, that any improvement in optimization problems is just very, very important to industry and society. Am I getting the hook?
No. We had till 10:05.
10:05?
Or 11:05. Excuse me. 11:05.
11:05. Okay. Sorry, I didn't see who was next.
Yeah, so I was wondering about sort of like the outlook on deployability for just the average person. So I know that like right now you can, I guess with IBM, you can get time with their quantum computer. You can do like hybrid algorithms or whatever on it, like indirect discovery, stuff like that. I was wondering what the outlook is for that for just the average person to like go on there and like use a quantum computer for a certain amount of time.
Yeah, no, I think what IBM supplies is just amazing. And many other vendors are doing the same. And some places like Microsoft calls their like Azure Quantum, and they've got multiple different qubits on their system that they can that you can access through the cloud. I guess my feeling is we're still looking for that miracle breakthrough. And so so we build our own quantum computer at Sandia. It's based on trapped ion technology. Why do we build one instead of just letting a company like Google or IBM or IonQ build one for us? Well, you really understand everything about the machine when you can build it yourself, and you understand how to make it better. What are the things holding it back? And so I hope, with no offense to our IBM colleagues, that there is still, a kind of tinkering aspect of making quantum devices, seeing whether they work, seeing whether they don't work. The problem with it right now is that, it takes, a dilution refrigerator costs $500,000, and you can't buy one right now because they're only made in Finland, and there's a 1-year waiting list for them, right? So it's kind of hard to get in the door of some of these fields. One of my fantasies is for like running a quantum center that has like, a lot of companies like Cold Quanta and Montana Instruments working on it, and Toptica is that we could get everyone to work together to, build a little turnkey thing that you could buy for $200K and stick in a lab. I don't think that's realistic at this point, but maybe we could find ways of making tinkering with quantum devices a little more available. And maybe things, so I didn't even talk about diamond defects. So there are these color center defects in diamond chips that are quantum active, and you can access optically with the laser. And so, that actually could be a platform that you might be able to get in the door. And people are making little like nano NMR devices out of them to like measure how the magnetic field changes across a protein. And so, you know, some of those might actually let other people get in the door. So, you know, I think cloud computing is, you know, cloud access to quantum computers will continue to be the way that most people get familiar with this. You know, again, my own hope as someone who runs a group that likes to build a lot of different devices is that you know, non-corporate building of these devices will continue to be something that we support and enjoy.
Okay, ladies and gentlemen, we're coming. One last question back there. Go ahead.
Forgive me if this shows my ignorance, but how is the theoretical, like let's say with quantum is in the fullness of time and it's where we hope it can be, how is it in terms of energy consumption compared to classical computing?
That's a great question. So in some ways it is much, much worse, right? It takes a lot of energy to keep a dilution refrigerator at, you know, a millikelvin temperature, right? Yeah. But there are other aspects of quantum computing that have reversibility in it, and so, you know, the most efficient way thermodynamically to make a computing device is to make it perfectly reversible, right? Because that's kind of the thermodynamic optimum for that. And so, you know, there are aspects of quantum computing that is, you know, reversible and as energy efficient as they can be. That brings in a whole other set of problems, but, you know, in the near term, not energy efficient at all. In the long term, there could be reasons to hope that you might get very good data out of the devices.
Okay, ladies and gentlemen, I think we've run out of time. Let's give Rick a big hand. Today, find him, ask him the questions that didn't get answered. We have the next session is going to start 11:15, Mary? 11:15, Quantum for Good. What we can expect to see from quantum technology, or what we think we can expect to see from quantum. We're going to have a great discussion around that. So please come back in about 10 minutes.
Jen, how are you guys?
We've got
like I said, I'm just
And they might aspire to have 5. We don't grow on trees. Others it's finding data in
What's your name again? I know I've seen you around here, but I'm sorry, it's the first time I've been here. I've been told I look like a ridiculous number, some of which I simply agree with, and others just laugh at me. And this one I don't think. But the reason does make me said that I look like Rob I don't at all. And I'm glad I'm not Rob because he did. Michael York, Mr. Feeney from the Women's World, just a lot of more than that, people come up and start talking thinking that, you know, who I am. And I'm not good at things all the time. I must have talked about all the things that were really obvious. I'm not good at things. And so I looked at Ralph from the we were his brother, right? You know, I was explaining that to a friend of mine that I didn't recognize somebody else all the time. I was just saying he's going to he was like Alabama. He looks up and says, Charles. So yeah, I have a generic phrase. So what's your
I'm very flexible. Perfectly secure, very easily
That sounds good to me. All right.
This kind of thing is a lot of that's why when people keep asking, like, what is it, what do you do?
I think this could be the difference.
Like, networking is never the smartest person in the room. How much I know. I don't know. Yeah, that's the bagels. That's already there, grab one.
I never actually went to the site now, but Harvard University.
But it's one of the two, like, you know, the other thing is
not what everyone like what I heard about my
I would say light load.
well, I applied for a job, especially in they really
Well, good morning, everybody. Welcome along to this session on Quantum for Good. My name is Michael Bratz, and I'm a specialist for quantum computing at Amazon Web Services. So I'm normally based in Seattle. I lead our business development team for bringing quantum computing to market. I'm sure through this panel we'll talk a little bit about what AWS is up to. We've got some other sessions later today. But we're building quantum computers, we're making services available in the cloud so that you can get started with quantum computing. We collaborate with a lot of the folks here today in quantum computing. So we're excited to sponsor this event and also to get involved in this panel as well. Because we've got a great lineup here today, and all of these companies want to do well as companies, but we also hope we'll do some good as well as we bring this technology to market. So why don't we do some quick introductions to your crowd. So Jenny, why don't we start with you? What is Quantinuum doing for good?
Okay, so my name is Jenny Striebley. I'm the Senior Director of Offering Management at Quantinuum. You might or might not have heard of that company. It's about 3 months old, but it came from the merger of Honeywell Quantum Solutions, which is about 100 years old. Honeywell was about 100 years old. Honeywell Quantum Solutions, not obviously 100 years old. And Cambridge Quantum Computing, which is a UK base. So together we're about 300 to 400 people strong across the entire globe, so the sun never sets. On Quantinuum, for a small company, I think that's pretty impressive to have a global footprint right out of the door. So we're a full stack quantum computing company. I'm responsible for the hardware, so we have what's called System Model H1 is available right now through the cloud. You can go on and run quantum algorithms on System Model H1. through our combination with Cambridge Quantum. We have our software, top of the stack and midware stack applications. So we have a product right now called Quantum Origin, which is a key generation service, and we'll have some new offerings coming out and other applications we're hoping to talk about that I think will do a lot of good for society as quantum computing matures.
Cool. Well.
So my name is Worley. I'm one of the co-founders and CEO at StrangeWorks, which is a quantum computing company here in Austin, Texas. We're primarily a software company. We're like 301 people. See, we're 14 people. There's only 14 of us. But we make software tools for enterprise and developers to actually work with quantum computers and interface with them. That's about it.
And Rebecca?
I'm Rebecca. I'm one of the co-founders originally of Quantum Thought, which was a venture studio that we put together to start kind of throwing spaghetti at the wall in this like wild west of quantum and come up with how we can apply these things. And so we would start little kind of ideas, and if they matured, then they would spin out in companies. And our main spin out, which I spend most of my time on now, is QSecure, and we work with the, if you're here for Rick's talk, he gave a good background on the quantum computing threat to cybersecurity. And so we work on the side of preventing that sort of quantum Q-Day, or if you remember Y2K. So that's what I spend most of my time on now. And I'm very excited to be here because I remember when I joined the quantum space in like 2019, one of the Jack Hittery, one of the leaders in the space, hand counted the number of people that were in quantum. You remember this? And it was like 800 people. And one of the main reasons I got into it is because there's so much potential to shape it for good, and ethically, and be good for humanity. So I'm excited to talk about the good applications. So thank you for having me.
Of course. Well, so if you were here for the last session with Rick from Sandia National Labs, he gave a great overview of all the different components of quantum technology. So across computing and sensing and communications and cloud delivery. And so that was kind of the foundational aspects of quantum. And on this panel today, you've kind of got a sampling from all of those companies that are implementing what he talked about as the foundational science. So from AWS, we've got cloud delivery, Quantinuum are building hardware, quantum hardware and software as a stack. Whirling his company are building out software tools that developers can use so that they can get access to the software in the cloud, and then QSecure looking for the communications and security aspect of it. So for this panel today, we very much want you to be engaged in this. It's not just me asking questions like, stick your hand up, let's have a conversation about this and keep going. So Rebecca, let's start with the big one, quantum security and Shor's algorithm, potential threat to modern encryption standards. That would be bad if that happened. So what's the good?
What's the good side? Yeah. So just to give a little bit of a background, there's a good number of unknown unknowns when it comes to quantum, but one of the sort of knowns is that back in the 90s, this really smart guy named Peter Shor came up with this algorithm to use a sufficiently powerful quantum computer to do math that ends up breaking a lot of our public key cryptography, which is the thing that we rely on to protect our data today. And the reason we rely on it today is because it's really mathematically hard for classical computers to break. And whoops, turns out quantum computers are really good at that. So this is a known threat. We know that it'll probably happen when we get a 4,000-ish qubit error-corrected quantum computer. Could break something like RSA 2048. So we have this line where we're trying to get ahead of. And also to kind of take another soundbite from Jack Hittery, he came up with this phrase SNDL, store now decrypt later. So it's this idea that we because we're not just waiting for this thing to happen, this quantum computer to be developed. It's the idea that data is harvested today, and it's if not encrypted for the future. Say it's bank account information, say it's social security numbers, etc. Harvested today, shelf life. Once we get to that quantum computer, if it's in the hands of someone you don't want it to be in the hands of, that's still bad. So what we do is, put the doom and gloom aside, it's a solved problem. Well, more or less. We use new math, so NIST is standardizing new algorithms to replace the ones that we have today that are easily breakable by something like Shor's. So at QSecure, we apply that and a number of other things, and we bring that to enterprise, government, et cetera, and defend against those sorts of data breaches.
So Jenny, can you talk us through a little bit about the challenges in building a hardware system that would be sufficiently capable to run this kind of algorithm? Like, you know, there is the bad outcome of breaking RSA 256 in the future, but you know, a hardware development company, what are the things that need to be overcome? Just give people a sense of how challenging it will be to even get to that future.
I think there's two issues. So there's scaling. We talked about the number of qubits you need, and if you were here at the previous presentation, they talked about error-free qubits, which is like not where we are today. Today, we're in this era where the qubits we have are noisy, and that was also talked about in the keynote speaker. That this quantum, there's a lot of power in it, but there's a lot of fragility in it. That if it really interacts with the environment, it can pick up the noise that's in our environment. So we go to great lengths to shield our qubits from the environment. We use ion trapping, ion quantum computer, and so those ions are atoms. Atoms are sort of nature's perfect qubit, but if you put any noise around them, you can decohere them or you can put noise on them. So really there's a lot of effort going into right now to shield these, to make them have this high fidelity, to make the error correction work. And then the other piece is getting that to happen at scale. So you have to have really low noise qubits, but you have to have a lot of them. And so those, I think, are the two big issues. I think there's huge engineering issues. When we talk about the quantum workforce, I think that's another big issue. You know, there's not that many quantum algorithmics people who graduate from, but there are a lot of mechanical engineers, a lot of chemical engineers, a lot of material engineers, a lot of laser engineers. We all need to get them into quantum and work on this grand challenge together, because all of those disciplines need to come together to make this possible.
So just to wrap up on the encryption and security piece, Worley, what's
Well,
your take on
it's
this?
a good thing that we break encryption. So I think the way that we secure data is fallible from the get-go, right? We build a wall, you tear it down, we build a bigger wall. So we keep just making the keys longer. This isn't, you know, it's basically a matter of time and resource. So with enough time and enough resource, I can break anything today, right? And so we just try to make it take thousands of years and cost millions of dollars. And then now you go find some other victim on the internet and break their encryption because they don't have that. I actually think that this will herald an entirely new age of security. Things like a quantum internet, we're using entanglement for you to be connecting to things where if anybody did try to look at it by being an observer, they potentially break in, right? And so it's destroyed. New post-quantum cryptography that's being developed, all of these things. So I actually think this is a good thing. I think all quantum computing is doing, these kind of fear and uncertainty and doubt around it, is really bringing us to the realization that the way we secure data is kind of not that great from the get-go.
Yeah, and Rebecca touched on it just before. There's an effort going on at NIST now, so the US government agency that looks after standardization and controls of cryptography. They are working through a process right now to identify and then recommend to all of us a set of new cryptographic standards that we can adopt in industry to potentially use. So stay tuned for that.
And
oh boy,
the questions already. I was just wondering, like, do you guys have like a sense of like a specific timeline of when we would expect to have a quantum computer that could break it?
So I just saw on LinkedIn somebody has started their Y2Q countdown. So I think they picked April 14th, 2030. April 14th. So not April 15th. I'm sure there's that. So 20. That's what they say, and I'll do it's on the internet, so it must be right. So I'll go with that. But 2030. That isn't that long away, right? Time goes fast, especially when you're developing technologies. 8 years is a blink of an eye.
Time is not linear.
Perception of time is not linear.
So we're at the earliest stages of this technology. It's moving very rapidly, but it's so hard to predict the future. And the metaphor I use all the time is it's like the Wright brothers have just taken off. Like we have aeroplanes, we can kind of do some neat tricks with them. But to then predict like when we can cross the Atlantic Ocean for the first time, or land on the moon, you know, that prediction is so hard. But it's going to move very quickly. Yeah.
So I want to come back to something that I talked to Rick a little bit about, and that is even if we don't we're going to come up with new algorithms and new really useful stuff. But even if we don't come up with new algorithms, just what a universal quantum computer can do in terms of understanding quantum materials, quantum chemistry, will just have huge impacts. And so, have you thought a little bit? Can you say a little bit about where you think that may take us in terms of engineering materials?
Yeah, I can start, but I'm sure others have things to say. You know, I think it's going to kind of be in a couple of realms. So there is a field of sort of exotic quantum-based materials today that are very much, let's say, university curiosities. They tend to rely on, let's make it, try it, measure it, make it, try it, measure it, you know, this very experimental process. And so to build up sort of logbooks or capabilities, and then you can kind of do some extraction of what the best material would be. Modeling those very inherent quantum materials is something that I think a quantum computer could do more nearer term and help build out those logbooks. Maybe you don't have to do the full logbooks to make those type of materials. Where those are going to go, I don't know for sure where those are going to go. You know, that would kind of be the next step, is are there really good applications at scale that need those type of exotic materials? So that's sort of one, I think, area. The other one is a little bit, I think, further out even, is talking about like pharmaceuticals and how do you make drugs, and you can short down the whole drug discovery cycle. Again, take either work at the front end of it, try to take some of the trial and error out of it, work at the back end to try to accelerate some of the clinical trials or some of the environmental dependencies. Those, I think, are maybe the two bookends of quantum materials or quantum drugs, drug discovery. Could be out there.
What? Rebecca? Yeah?
Yeah, and especially for those of you who weren't here for Rick's talk, the one sort of exciting application areas is in nitrogen fixation and producing ammonia, which doesn't really, by itself sound super sexy, but when you think about how I think it takes up 2% of our energy production. So you translate that into,
and that's one of just a huge number of catalytic reactions that we just don't understand well enough how to make.
Exactly.
Yeah.
Yeah.
Lots more like that.
So just one use case cutting down 2% of the energy usage, and you could think of how we could scale that, or we could grow into other use cases. Yeah.
Yeah. Question over here.
For Jenny. You say that the biggest challenges, one of the biggest challenges is actually getting an error-free qubit. But how do you measure that? How do you actually know you have an error-free qubit?
That's a good question. That's a good question. So we're just on the starting point, I think, of error correction and looking at some of these error correction protocols. I think there's got to be better protocols that are being made that are going to more efficiently. But basically, you're always trying to extract some of the algorithms are syndrome extraction. So you're looking at the qubits, trying to measure them, seeing if you're detecting any error in process. There's also post-processing that can be done to detect error. But in the calculation, trying to do syndrome extraction, look to see if there is errors in it, and that's how well can you then measure those errors, can also then limit how good your error correction can be. So that's one of them. I think there's going to be a lot more error correction. At the end of the calculation, though, you're ultimately getting out some probabilistic curve, and at the end of the calculation, how clean is your probabilistic data? Are you able to pick out the data from the noise? And once we get to have a quantum computer that's so big that can do things that a classical computer can't do, you're just going to have to trust it to know if it's right, because you can't model it classically. And that is the value of today's quantum computers, is you can still simulate what is going on a classical computer with CPU or GPU. And so that's kind of the name of the game today, is let's run these algorithms on today's quantum computers, let's classically simulate them to see if they're right, and then build trust. So if I can trust a quantum computer today with 20, 30, 100 qubits, then the expectation is that we'll be able to trust that quantum computer when it has 2,000, 40,000, 200,000 qubits, because you won't be able to measure it.
think suffice to say, if someone's looking for a really neat PhD topic right now, and it is a rich field of study in quantum error correction right now. There's a lot of fertile ground to cover in that space. I just want to pull it back to applications a little bit more. So we've talked about the potential threat to encryption standards, but there's a lot of good that can come from introducing new technology, a new type of computer into the world, and operating that computer in a hybrid environment where you're working with other systems, so the CPUs and GPUs and other specialty processors. Now we've got quantum computers running together. And Worley, you're starting to see how developers are pulling these technologies together and combining them with other things. What good have you seen in the world?
It's super exciting. There's things like quantum optimization that you can do fairly effectively today, which are very useful for, think about, autonomous vehicles, right, and the path to them. Think about managing the energy resources. If you all have an electric car and you drove it here and you went home tonight and plugged it in, the grid would fail, right? So optimizing things like that or transport delivery, those are really exciting. I'm sorry, I did 16 in the last couple weeks. I just got off one. I have laryngitis, my apologies. But it's fine, pop into the chlorophyll. But the other applications that we're seeing are people starting to do work in drug discovery, starting to do work in things like oil reservoir management, things like that. They're very, very exciting.
Yeah, the title of the presentation is Quantum for Good, and I think that it only makes sense if it exists a quantum for bad. So,
this never comes up.
If the worst thing that we can expect from quantum is that they crack some password of an email account, this looks quite safe. We already have this problem nowadays. So, is it really something life-threatening or species-threatening that quantum computers could bring, or just that the encryption is the only threat?
Well, if you want to, thank you, sir. If you want to go, my team has had to bring me water every panel on this. Sorry. I'm going to jump in on that if that's okay. If you want to think about really bad stuff, think about, I like to look at it as 2023 is going to be 1963. When a guy named Jack came out with a microprocessor and said, here's this thing, and nobody thought of autonomous vehicles or AI or drones or any of these things, right? I believe that in this decade, we will hit another point like that. That doesn't mean quantum computers are ubiquitous, there's general quantum computers, immediately, but it means that there are problems, there are opportunities, there are threats that we don't even know of, we can't even imagine, because this is literally going to be a completely new field, a completely new realm. And so, the things that worry me are the unintended consequences of the technology in a world where things that would take thousands, hundreds of thousands, millions of years to calculate are now all of a sudden things that can be done in weeks, months, days, weeks, months. And that, I just popped out.
Every
it's
time
so
we
bad.
say something smart, he gets a treat.
That's how your cup runs out.
It's an incentive-based program. But that's what concerns me, right? What concerns me are that we have no idea the unlimited potential of this technology that we're about to hoist upon the world. And so I think what's important is, if you look at companies like AeroQ and Nick Farina, a bunch of people under Quantinuum is involved in a lot of these efforts as well, as I'm sure QSecure is. There's already people doing quantum epics and quantum groups and having these discussions. So one thing I really feel confident in is that the community that are bringing this products and these technologies to market are cognizant of that and are actively thinking more than any other in my last 30 years of technology career, any other projects, any other new technologies that I've seen. So that makes me feel a little bit comfortable. I think there's a lot more work that needs to be done. But the scary stuff, it's not encryption is the worst. There are definitely things that are bad. For example, what new weapons technology could quantum computing unload that is loads worse than nuclear technologies, right? I mean, you could sit and imagine all kind of things. And the problem is we can't hold back on the technology. We just have to be aware of those things, but we have no idea what those potential threats could be in reality, because we don't know what different people will use this incredibly powerful technology for.
Yeah, just to add to that, more reinforce that. Imagine this is a panel of computing for good in the 1960s. No one would have been able to point to some of the things that we now are able to do. Like you said, building really, really good weapons with computers. And you think of the potential of a quantum computer, which again, a quantum computer is not just a better computer. It's not just, you know, HPC on steroids. It's it's different applications, and there's so much we do not know. It's kind of like, you know, if you ask people in the horse-drawn carriage era what they wanted, they say better horse, not an automobile, right? Because they couldn't conceive of an automobile. Again, they're pointing to that there's so much that we don't know, which on the good side of things is incredibly exciting because there's so many inventions and things to come up with that we can't even, like, we're in this box right now and it's going to broaden our horizons so much. But again, think of things like how many people have taken like a 23andMe or something like that. Right, so now all of that genetic data is stored somewhere. With today's computers, we cannot really do much that's very interesting with that data, but enter a quantum computer. It may be able to make sense of that data in a way that could be both helpful and harmful.
Figure out what all that stuff they call duck DNA really does.
There you go. There you go. So, you know, very cool stuff, but also maybe when we gave people that information, like our information, or very sensitive information, under the assumption that there's not that much that can be seen in that. But later, you know, that might change. So stuff that's already stored now, thinking about how do we think about ethically protecting that in the future where we have these really powerful tools.
I mean, to put it into perspective, just think about how much the U.S. or the Chinese or the Indian government is putting into this as well. So that should be something that's telltale.
Question from Will.
So, just to follow on your issue, I mean, I'm not going to say that having the ability to decrypt everybody's messages across the entire world is actually a trivial, advantage. Right? That's a big deal, and they don't call it an extinction event for cryptography, lightly. But let's just you want to have other bad potential. Talk about this biology concern. We just went through, the global economy is still going through the second year of an event that was caused by a single virus that happened to be a little bit easier to transmit than other viruses. And we all know that there are variants that are sort of mutating and occurring. What happens when somebody gets hold of a quantum drug discovery application and uses it to create a better virus that there is no protection against it, and then decides that they're going to infect themselves and travel around the world spreading it?
I literally just turned to Becky. It was like, wow, you were skating dangerously close to the whole genetic weapons and targeting people.
So there are a lot of really bad things that could happen. To take the optimistic side of Will's yes, we've just been through a global pandemic, but we as a society have also produced a vaccine in the fastest time frame like ever possible, using high performance computing techniques and a lot of the data there as well to do that sequencing work. So for any new emerging technology, there's dual use factors to it. The good news is, and we talk about this at AWS all the time, quantum's special because of the physics that's going on. It's really special. It's magic that happens at the physics level. It's not that special as like a broader technology trend. Like we've been through big technology trends before with GPS and AI and machine learning, that kind of thing. We know what some of the factors are that need to come into managing these dual use technologies so that we get the societal impact that we want from them. So, quantum's special because of the quantum physics. It's not special in how we manage this kind of technology and its introduction. You've had one already, so I'm going to go. We'll come back to it.
Hopefully this will get us off the dystopian path.
Yeah.
So the question is, what applications are we seeing in supply chain and logistics that quantum can really optimize?
Yeah, I mean, look, a lot of people like to use the traveling salesperson example of kind of logistics, right? If you wanted to go to 14 cities around the world and have the most optimized path, my laptop does it in a couple thousand seconds. You go add 8 cities, it takes 3,000 years, whatever, right? So, but primarily autonomous ships, Maersk and others are looking at these autonomous drone ships. And so if you look at those, there are so many factors to navigate an autonomous drone ship across the Atlantic and Pacific Oceans. not just for weather and factors and paths and optimization. So there's work going on there. I know that Volkswagen and other car companies are looking at the autonomous vehicle pathing, right? And then there's all ancillary things. For example, the electricity that you use. Like I said, if you all home an electric car, plug them in, they're going to fail. So how do you optimize when people charge, or how, or those things? These are all things in and around the logistics kind of area. FedEx is looking at stuff. UPS is looking at stuff. DHL is looking at stuff. An example I like to use is not quantum, but to give you an example of how this could be applied. Some friends of mine years ago started a company called FlightAware, and they were pilots, and they got hired once by a transportation company, and what they found was that one company was beating the other. They were using less fuel, they were getting there faster, and it was simply that one company hired military pilots, one company hired commercial pilots. The commercial pilots took off like this, got to the cruising altitude, and the military pilots went, right, saved much fuel, saved much stuff. So using that as a very classic example, and now think of all of the different factors and variables in a logistics system or supply chain system that you can apply this computer biology to, and look at all the probabilities of different actions and reactions, and then apply them to their system. So that's probably an area I think is going to early on see a lot of progress.
And I'll add to that I think I saw this morning that Deloitte has a grand challenge right now to try to calculate how planes can be more fuel efficient if you take into account more variables like different weather patterns and things like that we know affect avionics. We've seen Airbus had a challenge on how they effectively pack cargo inside. And I like these applications that go to avionics, because avionics is such a critical part of business, being connected. Not only do you feel it emotionally and that you get to travel across the world to see your family, but it's also how we do business. And I think through the pandemic I hope we realized how important travel is and how important Zoom can do a lot, but there's no replacement for a face-to-face meeting. There's no replacement for being face-to-face in a session like this. So avionics is important, but it's also has its environmental challenges. And so it's really, I think, a great application to see some of these avionics companies, Deloitte stepping up and putting these grand challenges out there that are going to advance quantum computing, but also advance them in a place that's really going to help, I think, the environment.
So just to give everyone a quick framework for how to think about applications in quantum computing. With the kind of computers that we're going to have access to in the next decade or so, there's probably three themes that we can work in. One's optimization problems, so anything in like scheduling, logistics, and like path optimization, that kind of work. The second is in machine learning. So can we use a quantum computer to accelerate the training of a machine learning model and reduce that computational cost? And the third thematic is computational chemistry, so things we've been talking about like the Haber-Bosch process and materials design, that kind of thing. So, but across all of those themes, it's not just a quantum computer that's going to do the work. It's a quantum computer in combination with other forms of compute, a hybrid environment. So for any application like logistics, you're going to be, the companies that are taking advantage of it are the ones that are already using high performance compute in some way, that will then incorporate quantum computing as kind of like the next wave of that technology. So you kind of don't have to wait for quantum to get started in, getting benefit out of different operations. Use existing technologies and then add quantum to that over time. We got a question on the back?
Yeah, so those applications have largely to do with taking information and doing something with them, right? Looking at the combinatorial result. Can you say anything about, or do you have any insights on the phenomenology with like a bee flying in entanglement, or photosynthesis and producing energy, through entanglement? Are there any insights like that you see coming from some of this work?
Yeah, anyone want to take that one? I have no idea. We cannot wait to find out. And this is the exciting thing about quantum computing, is that we don't know what's going to be possible with these machines because we can't simulate these machines. There's no way to use a classical system today to emulate the behavior of a quantum computer in the future. And so we're already into this realm where it is practically impossible, it's too difficult, computationally expensive, to simulate what we can do with a quantum computer. So we do not know what those quantum computers can do to help us investigate these kind of questions. So that's why this whole industry is so excited about to investigate.
To butcher a Feynman quote, that when he kind of famously sort of maybe came up with the idea of a quantum computer, he's saying, you know, the only way to describe and understand nature is you can't do it computationally, you gotta do it with you gotta model quantum with quantum. So understanding the nature of things is kind of in the DNA of quantum.
So for classical computing, the comparison's already been brought up of like we're 1963 for quantum or whatever. For classical, there are all these milestones of like the microprocessor, the compiler, the personal computers. What are the milestones for quantum?
It's error correction. This is why I say classical computing was kind of adopted in this long curve, right? And there were all these milestones. Then we had an internet, we had personal computers before that, you know, all this stuff. Quantum computing, the reason I evangelize for people to get involved with it now, like as soon as possible, as deep as possible, is that unlike that, it's going to go like this, and then we're going to make a few minor breakthroughs, mostly on error correction, and then if you're not already there, I think you're going to be missing out. I think error correction, you know, adding another qubit isn't really hard. We know how to do that. Adding one without the fidelity of the system going down to, you know, unusable, that's very difficult, as Jenny said. I really see that as one of the primary things. The other thing is something there's some people in the room maybe working on, which is, you know, computers don't have memory, right? They don't have storage. They don't have a lot of the basic components when you think of a computer. So all of those, you know, primary things around there, I think are very, very interesting areas and are the milestones that will eventually help us get there.
I'd say one thing you hear about, I agree with everything. One thing that you hear about is the word, I'll say quantum supremacy is a word that you'll hear a lot, you'll read about what that is, and that is, I think, there's cases of it already that have happened, and so there's some that maybe there's a quantum advantage, and then I'd like to separate that from like a quantum economic advantage. But these are cases where a quantum computer can do better than a classical computer. And so there's some unique cases that have been demonstrated so far. They don't have an economic advantage. But from my perspective, the big milestone is when can we do something on a quantum computer that brings economic advantage that can't be done on a classical computer.
And that's a great point. That's the reason I don't bring that up is my focus is on not using these computers for what we do today. But I'm super excited about that 1963 moment where there's all these things we haven't imagined. So I'm focused completely different. But quantum advantage is clearly absolutely the number one, you know, milestone that we're all looking for. And there's all these other things in the error correction stuff that we'll have to lead to it.
Is there something like Moore's Law or anything that resembles it?
Nevin's Law.
Yeah.
Actually, what is Nevin's Law? It's like the rate is it's something that has not really been proven, but people throw it around, and it's kind of like a faster acceleration curve than Moore's Law.
Yeah, I wouldn't say they're laws yet. There's more conjectures about what might eventually become a law. But we need some more data on the curve before we can declare a trend.
Moore's Law is not called Moore's Law; it's an observation.
Exactly. Yeah. Exactly. So we're not quite there yet.
But they do talk about how Moore's Law is kind of, you know, coming to a close.
Yeah.
And you can't fit more on a chip. You can't get smaller.
Question about AI. So memory for machine learning is a big issue. Long-term memory and capture. How will quantum affect memory for artificial intelligence, or do you have any comment on that? Because that's a big area.
So QRAM is what people talk about, quantum RAM. And that's, you know, there's sort of different levels of memory in your computer, just like there's going to need to be different level of memory. Unless someone knows different, I don't think that there's a real viable solution yet for QRAM. And so, does anybody want to disagree with that?
I know somebody working on it.
We know people working on it. Lots of lots of publications out there, but I don't think anybody. I don't think you can go buy a QRAM box today. So I think that until that kind of nugget gets solved, that could limit the number of like how much big data for like a machine learning application. If you really need to have all this data loaded into the computer and stored for the whole calculation, and if your coherence times, if it has to be stored longer than the coherence time of your qubits, that could be a calculation that's not a great fit.
So I got some bad news for memory, for quantum memory. The magic of quantum computing, one of the reasons why this is so interesting to us, and we can do some cool stuff. one of the downsides to it is that quantum information decays. The system will decohere, it becomes noisy, even if we've got error correction and all these tools. So storing quantum information in memory, like right from the outset, is extraordinarily difficult, and it decays over time, no matter what you do. So that's not going to be a silver bullet for like large-scale memory type applications. But there's some interesting stuff that we can do in the processing of data that could potentially help us store that data more efficiently as well. So that can be useful. Yeah.
How long do you think we are before it becomes useful for national security, which is a different calculation than economics?
I'll go back to what I read online, that April 14th, 2030 is when they say that there's going to be a computer that can break encryption. So
there's been $20 billion invested by governments all over the world in this. It's for one thing, which is national security, right? So they already see the threats to encryption, the ability to make different weapons, the ability to have better logistics for their military forces, better secure communications. So I would say that started probably about when we met, right? Probably around 2018 or so. There was already heavy investment in that area.
Well, they don't want to get left behind. I mean, they want to be at the forefront, so governments are putting that dollar in.
One interesting trend we've seen is that the commercial sector is kind of leading on the application front. So we're seeing a lot more investment from the financial sector, the automotive sector, the aviation sector in commercial R&D of these applications. But those same applications can be adopted by the Army and the Navy and the Air Force to do work. So logistics at Amazon looks a lot like the logistics for the Army as well. And so those dual use applications are possible there.
And one thing, especially for those of you both in quantum, and would really love to inspire people who are not in quantum to kind of try it out too and get involved, because I think it can be a little alienating sometimes to try to get into the quantum realm if you're not a quantum physicist, but there are spots for everybody. And I think that in terms of quantum for good, we need more and more people from diverse backgrounds coming in and building things. The government has programs like the SBIR program or STTR program. It's called like the Government Seed Fund, I think. And so you can apply for small to large grants if you have an idea or you're working on something, because the government wants to incentivize people working on these problems both in commercial and in labs to work on things that can ultimately be used for government and commercial.
So I'm going to do one more question, then we're going to sort of change topics just a little bit and get to sort of the international collaboration kind of theme in this, because that's a good one about it. So Bob.
Just want to make a comment, is that this is quantum for good, not quantum computing for good. So talk about national security, well, there are a lot of other things beyond quantum computing. There's sensors, certainly quantum communication. If you talk about quantum memory, we're computing, but you also need repeaters as the first topic. So the commonality of these quantum technologies. And then also just there is a panel at the end about quantum security, which is
Exactly right. I appreciate that. So one of the things we discussed as a panel in the lead up to this is, as quantum technologies has kind of like brought all of us together into this room, we're also seeing that happen on the international stage as well. Like there's a lot of collaboration that's happening between countries and between organizations for quantum technologies. And Jenny, do you want to comment on some of the things that you've seen as a good factor in that collaboration?
Yeah, so my career path has been, I started my first postdoc in quantum computing 20 years ago. Thought I wasn't going to go anywhere, left the field, went on worked on quantum sensors, and then, that's the thing that if you work for 100,000 people, there might be a couple hundred people all of a sudden that you find out are doing quantum in your company, so then I went back into quantum computing. But I joined quantum computing during COVID, and what I thought was totally sort of barrier breaking was that all of these workshops, seminars, we just totally democratized them. By now they're all online. Instead of needing $2,500 to go to a conference and $2,500 airfare, you just needed the Zoom link, and maybe they charged $150 because they had to host it or something like that. So this really democratized, I think, the access to some very critical conversations around quantum, and that's enabled countries and regions that aren't gonna be the first to invest at the national scale to start getting a grassroots organization. So Quantum Latin America, Quantum Latino, that's an organization that's kind of grassroots, that people are having access to information, and you don't normally think, is those really the regions that first to invest? And now they're starting to see investment there. Big investment in India, and India's always had a very strong leadership position in software workforce, and huge investments coming there to really start develop now the quantum software engineers that are gonna be empowering, I think, a lot of companies. Of course, we have China's hugely investing, Australia's investing, I think South Africa has a quantum kind of grassroots team. So I'm a silver linings person. I think COVID has done a lot of terrible things, obviously, but I think one of the things it did is it really made, by forcing us all to be online, it made a whole bunch of information available to people and got a lot of people interested in it, and I think they stay interested and can start, taking that from a grassroots organization to really deploying it and getting involved in all the companies that are out there. A lot of small companies have also grown up with it.
Well, you've got a developer community that's a global one?
Yeah, we started that. I mean, we have users around the world. We have partners in all of the major countries you can think of: France, Germany, Japan, just everywhere, even India and other places. That's what's so amazing about this, is that it really did kind of take off during COVID, right? Like, we started our company, we launched in South by in 2018, and then a couple of years later, this happened, and it happened kind of at the same time the interest was increasing, and it drove down the barriers to entry for a lot of people. It made it a lot more global, because now people from all over the world could jump on a Zoom link that Jimmy mentioned and attend that. And so, we see this as hopefully as a global thing that stays global, because of the national security issue you brought up. In a lot of countries, there's parts that there's some divisiveness there, but for the most part, we met for the first time at a conference in Tokyo, in Japan, with people from all over the world already. I mean, it's like, from my entry into it, it's always been a very large, very global community. So I think there's more collaboration in this space globally than any other field that I've worked in my career, and it's really great to see, because I think things are advancing faster, and I think things are becoming more open and more collaborative as we move forward.
So, in addition to democratizing kind of the knowledge of quantum computing and getting more people involved, so a lot of the companies are involved in democratizing the access to the systems themselves, so the actual hardware. So AWS has got a number of different quantum computing systems available that we make available through the cloud. IBM's done a great job as well, democratizing access to technologies, and running hackathons all over the world, so hackathons in Africa and the Middle East, that are enabling people that have an interest in this technology to actually touch it for the first time. The quantum computers that were built in universities and national labs during the 90s and 2000s, they were only available to the humans that were in those labs at the time to work with to touch them with a screwdriver. But through the cloud, we've been able to launch these technologies and make them more accessible to anyone that wants to work with a quantum computer anywhere in the world can actually participate in something today. So that's great. Yep.
When you think about, when you think about quantum for good, how powerful that is, because you can access it from anywhere, no matter who you are, and you can play around with it. Whereas, computers back in the day, you couldn't do that. It was sort of rarefied air. So in terms of bringing in that diverse community and getting people from all parts of the world into it.
Let's not just automatically include all the bad actors too, though.
Well,
right? I mean,
was
democratization is a democratization of good and bad. That's why you have a liberal world order that counters the bad in the world, right? So,
yeah, I think that falls back into, like, earlier in my career, like the open source argument, like you're sharing the code so all the bad people can see it too. 25 years later, there's been no like crazy thing that's happened. It's been a good thing that it was open and collaborative.
Right.
I think in general, more eyes on things and more access to things negates that to a certain extent. I mean, you're always going to have bad actors, but I think you look at from my friend Brian Behlendorf, the Apache Software Foundation, all the software they use, it's in everything. You touch it every day somehow. You never see about some giant security breach, some giant thing. You look at Red Hat being one of the largest acquisitions in the world ever, and how many enterprises depend on that software where that code is freely available. I do agree, it absolutely gives access to both the good actors and the bad actors. But I think we've now proven, at least on the software development side, that, you know, there is a way to be completely open and completely collaborative and negate some of those bad actors and stuff. It's very rare that you have, for example, an open source project that creates some stuff, whereas you do have commercial projects that still are responsible for tremendous data breaches and stuff. And that's not saying one's better than the other. I just think at this point in the game we have enough history. You know, it's kind of a Lindy effect. We've been doing it for 25 years and proven that a lot of the bad isn't being done. We've probably got a considerable amount of future when that continues to be the case. I think that will be the case on the long run.
Alright, so we've got about 5 minutes left, so we're going to do rapid fire questions. We're going to answer quickly, we're going to ask quickly, and then Mike.
So not that I want to give Worley a chance to plug his book, but how do you see best ways to attract the next generation of talent to come into the environment, right? We have to get that next generation of talent, or it's going to happen like AIML, where we're going to be looking for data scientists and it won't be.
Well, Rich, I'm glad
so
you
what's the right
mentioned
age to start?
I think it's very simple, I promise you. It starts with, this is a ball, it could be red or blue. Basically, you know, I believe that you should start with kids. And it was funny, Chris Ferry, who does this incredible series of science books, I was lucky enough to get called by him and collaborate with him on this book. Funny story, I thought this would take about 2.5 hours. I got a rum and coke and told my wife, leave me alone. I'm gonna be in a studio and then knock out this kid's book. About 9 months later, I realized that was not gonna be the case. And the editor said, entanglement's a very large word, and we have to keep the 4 to 5 words per page. And I was like, wow, distilling this down is impossible. But I think you should start. I think you should start very young. I am advocating in DC right now to take quantum education programs down into high schools and even down to middle schools.
I'm trying to get quantum badges for Girl Scouts.
That would be that's amazing, right? That's the kind of stuff. I think that's what we should be doing. I took my first computer science class in 7th grade, right? So why aren't we teaching people quantum information sciences early in the basic concepts?
And if you can develop that intuition early about it, you know, and so you don't get stuck in that, like playing a didgeridoo, a lot easier for a kid to learn than an adult because you don't unlearn stuff.
Well, right, their minds don't have to unlearn everything.
So rapid fire round, Willie.
Right. Blaze Ridge.
Yep, we're back there.
So I guess following up on that, like if somebody, like for people who are from like a tangential field looking to go into quantum computing or quantum information in general, what would you guys say would be like the biggest place to go for that, or you know, how would you go about that?
Can I put in a quick plug for we have a program called Q-Force, and we just brought in a group of Q fellows, and we really deliberately made sure not to pick all quantum physics postdocs. People from all different backgrounds, just trying to get people into it, and so we give them a little funding and to work on a project and collaborate with mentors, and so Q fellows come.
And go look and see what companies are hiring. You might just think, oh, it's going to be a bunch of quantum physicists. It's not. Go look and see what's hiring, and you'll find something for a whole breadth of professionals.
So the panel right after lunch is the quantum workforce development panel. So there's going to be a whole session on how we generate that workforce. My favorite place to point people to get started is a website called Quantum Computing for the Very Curious, and it is written in a very accessible manner, but by one of the fellows that wrote the canonical textbook on quantum information. So it's sort of very close to that. 2 more quick questions, and then we're done. Around. Yeah, satisfied at all.
You got so many questions early, which was shocking. Yeah. We don't ever get questions, just so you know. If you're on a quantum panel, you're used to anybody have questions? Nobody has questions. So,
all right. So, real quick.
Yep.
Analog quantum computing is a way to understand a fair amount of stuff before we get big into quantum computers. Rick Silver's did some beautiful work in this.
That's another great starting point. So to wrap up the panel, let's do some quick predictions for the year ahead. Jenny?
Oh, why did you start down here?
What are we going to see in 2022?
More small companies.
Yeah.
More small companies. If you every morning you wake up and the first thing I do is look at LinkedIn to see what small company happened the next day, the day before. So more small companies.
There's so many already. I believe that 2023 will be the 1963 moment. I thought that I think we'll make progress this year towards that. I think it'll be probably mid-year. It's not going to be like, oh, there's a general purpose quantum computer, we fixed everything. But it'll be the fundamental kind of moment, like when that microprocessor came out, where we have things that are just advanced enough to really spark an united industry.
I think a lot more government funding this year. There's some bills in the works and things. Or partly your work, and I'm sure your work as well. So that maybe some gets to that point, quantum advantage, slowly but surely.
And I think we're going to start to see a lot more work using available quantum computers to do some really interesting stuff and learn some things that we haven't seen before. So we're kind of in the period now where quantum computers have been available in the cloud for a couple of years on IBM, 18 months on AWS now. People have done the work and are starting to produce the papers and talk about what they've achieved using these new systems. So we'll start to see a lot more publicity about the practical work that people have done investigating applications. Thank you very much for attending this panel. Come back at 2 o'clock.
So we're working with the Department of Energy. We're taking 250 starting projects around cybersecurity. So it'll be very interesting to talk with you about yeah. So I'll be that's all I
What?
Sorry,
You never know, right? Yeah, very much
want to be able to have
really like that. Well, I don't still hope we'll get more push that forward because we really love nothing better than working on that. Another version of that policy think about that's not something you have to have a new way of thinking. Keep an eye out. A couple different. Well, the other thing is, right, you're going to stand out there. But the problem is, if you've got thousands of devices, some of them are very fragile. You really want to spend all that time doing a heat loader on every one of those devices. Tony Hawk, or working with your coalition in the battlefield, have their own payloader, which is theirs. How do you make that all work? She broke there and now you're so we would love to work with you guys on that. You know on the what we want to do. We want to reach out to you. Okay. Great. Awesome. All right, I'll do that. We will catch up when I have a chance to show you how these great to talk to you.
I haven't done any of
Sorry, I didn't drag the
Saturday. Saturday.
Oh, you asked the question. So I'm like, now it's just breaking the that's a really bad problem. By the way, there's one that you might care about. Sorry,
you said iron.
I thought for there was like a happy hour at the end of the day at like 5 o'clock. I don't know.
Channel together. What do you think first?
Somebody mentioned it here, I've heard it before,
I used to work at IBM, so I used to bother a lot whenever I had to read Now I can't. Now I have
It's the really hard, runs the concept, 2 to 5 years. Yeah. But then they also have this is so big, I still possibly have
Technically, NVIDIA collapsed and IBM, which I've done to do.
What we're using might be some of the challenges.
I generally try and stay
by the
away
way,
from
let's
partnerships on like
I assume so. I don't know the reason is.
Yeah, exactly. Every time there's like
Look it up, let's talk.
I like when you respect stuff. Like, it must be here.
It's like, let's talk about the intention. What is
Services were down. But I think they're like
that they work. As far as I know, Reed Russians never coming into the army, so Reed Russians broke into their house and come out. Like, they sort of shoot him away.
Yes, I know what you're talking about.
I mean, that's just how it's always typically how people something going But the hard part is such a problem. You're only to take over all of them.
Their only exit is like retreating back to breakout provinces.
The thing is, would we accept that? We would accept them for like, you would accept it now until they get there, and then they're like, look, now we're putting in peacekeepers, and then you say this, people say, well, we want to cut out this content, we're full of there. What's the Robert in the house and have a law set? It's content. So,
well, one of the companies that was here at last time,
myself.
building.
What are they gonna take away from that? Nothing. It's illegible. Yeah, it's like, oh, it's so embarrassing, like, that's the only thing I can think of that. It's like, oh, I didn't comment on it.
Yeah, no one knows what to do.
Funding the parasitic power that's stuff.
Anyone who comes to me, no one can penetrate the sources of security from my messy code. I literally used to do that all the time.
Yeah, I listen to anybody and then
like interacting with
yesterday and then now tonight.
So we've got a couple of this code's written by Olivia Lake, Eric Brindle. Delete.
Make things more efficient, just for that, we were utilizing the hydroelectric drive on the ground, showing people combat dispatch from anything that goes power.
This is my savior right here. You, sir.
I have to go downstairs and realize it.
Whatever you want.
It's a damn shame.
I made a mistake.
I'm not allowed to go.
Manchester is
Oh, gotcha. Hold on, wait.
Everything I got it.
And you're yelling and then you couldn't do it.
I'm certainly.
I can't show up. I can show up. I can't show up. That wasn't necessarily somebody who
because it's broad spectrum.
I got that. But there was some other diagnostics.
I've gotten sick from my
so you're gonna have some of these guys. So prototype, how much it's gonna cost you $1,000 for 7 conferences. And then about we're gonna put it on literally taking. Yeah, there you go.
That's part of the whole.
So
what I was doing over on the so I'd have to like I'm meeting with you and stop my first meeting with her. Like that, go to work together. Yeah. I was like, we're taking
They take them about 2 hours to get through. And then we put it on go meet with them. Show up an hour early. Introduce the architect and show up later in the day.
Great.
Are here, yeah.
Yeah, the rep, we didn't have any, we did, I remember plan for a while, and you took sort of this we just gathered a whole bunch of rapid tests, but it's like rounding up.
harness AR, VR, media.
That's why I'm not here. We were actually desperately looking for tickets for our meeting. Couldn't find them. There were nowhere to be found. We had one guy that was flying from Europe and had a stopover in this house that they were going to a pharmacy and he was like,
So it's like a free.
Yes, you got food.
You can trust one to anybody who wants to do it, and if you need more, just let me know.
So here's, I'm paying for it. Okay, yeah, so one of the things we're working on.
Yes, you want to put us together, I'm ready.
Yeah, sorry. I was gonna ask, where do I get
You are actually a smart man. I'll go find that service.
I didn't see it.
You just walk into the.
Yeah. I need 2 hours.
3x speed or whatever.
Or you can just run it and
hey, I'm
say,
dead.
this was, if these 3 were the most successful courses of action, then okay, let me go in there and we're going to also come out with kind of like a synchronization matrix of, okay, this was successful, this one, so part of the working is
I have to get back down there.
doing a working, which is probably the hardest bouncing around learning. Also, the decision making process.
Very good.
Is well, how do you adjudicate? This is going to be this. If I did this, this one action would be successful. That was like action, reaction, counteraction. Well, I have more folks. I know I'm going to be better here. Like, well, this passion is like. This guy's got better terrain. This guy's got covered in concealed routes. Oh yeah, that's where your position.
I don't know, but I don't want to stop.
And then you okay. They look at all of the best case and the worst case. Which way do we align ourselves if they wipe us out? Okay, now how do I array against prepare myself for the most dangerous first way? So
you gotta hope that your assumptions on there.
Well, that's my thing. Then like, well, what are the inputs to it? So I'm like, so I gave our guys like, here is the commander's guidance worksheet. So this could say what and that was man said this is exactly what I think is the most important to this piece. I have to maintain combat power. I have to be prepared to transition. Most important logistics. Is it logistically supportable? Well, like that. Hey, that's kind of important. Right? Is that important? So I'm like, oh, that's interesting. Well, let me send you the articles of these are some articles of this. So it trains the AI how to think. Both from the OpCore as well as the movement. So
hey, how's it going?
It's more. It's so I think we're going through. We've been working with. I think the Army's interested in it. Because again, it's just another tool in the kit bag. Whether they use it, especially if you use it during training, that's the way that you'll train the staff more rapidly, especially with all the staff turnover and everything. So,
really cool, good stuff.
But, if that, especially the photonics thing, that would be.
Could be like I'm just trying. So they're at the stage where they've proven it in the lab on a thing, produces power, it works. They've gotten the money to build the next version. They're using tritium as their power supply now. It's relatively cheap, but they can put never will. So they can increase the power density by just switching out the isotope. And then they're just trying to figure out the use case. Like, am I trying to build this in a long sheet that goes in the wall of the thing? Does size, weight, and power still important in space or other applications? Or am I trying to build a Duracell form factor? Like what?
what am I trying to
I
build?
I really think that the main element would be,
Yeah.
there should be.
You said it's called Vertex?
Vertex, VERT.
Yeah, next session is 2 o'clock.
Okay.
Great board, I mean, artwork everywhere. We're just big on artwork and inspiration.
I think you don't allow me taking pictures.
No.
Great.
No.
It looks like
interesting. Okay. I'll buy that. It's changed. Yeah, I do.
Yeah. Yeah, what do you see, a butterfly?
Right.
No, that's a.
I mean, I'll buy that. They've changed it since I was.
Maybe that gives different implications on me if that's what I see.
Yeah, right.
Okay. Tell me what this is, Vicky. There's words in there somewhere.
Right.
That's right. Yeah. There's my doggy is mean fat. That's me. And I'm gonna take a picture of this and figure this one out if you don't mind.
When you get done with that one, John, there's another one over there.
Almost slow us down. Love the clock.
Oh, look, I think this is the key.
Oh, there you go. Those are the words.
Okay.
That you gotta look for in here, so you better take a picture of that too.
I better too. Give me something to do.
Otherwise you'll come up with 50 words that aren't even on there.
If I can't fall asleep, I know what to do now.
Don't even see glue on it.
Because that's probably not one of the ones that's relevant to those.
Accelerated founder pitch.
So there's no doubt other words embedded in there. You know?
Oh yeah.
Randomly.
Hey, there's John taking.
Look, look at this. Fred. Fred. But I'm not here to
this is Anton. See the doors?
Okay.
The big,
I saw it on the map, it's like off to the corner, and I can't find it, where it was anyway, or on a round table already, so I'm trying to locate it now.
Applications of quantum.
We'll be starting at 2.
2?
2 p.m.
Oh, great. Okay, so this is where it's gonna happen.
If you want to put my jacket's up here in the corner, if you want to leave your
Yeah,
bag here.
Yeah,
Yes.
it'll be safe here. Is there another session starting here?
2 o'clock. So we're on lunch break. 2 p.m. with Quantum Talent.
Thank you. Great. I'm just gonna set it kind of here. And everything will be fine here, right?
Yeah.
And you've got computers and stuff laid out.
Maybe we need a spill. Move that out of the way.
Is this where the session 5 and all of the rest of them are gonna be right here?
Yeah,
Okay,
so
good.
I ended up getting ready for
nice.
seats in here.
That's good.
The first session was packed. Second session had a good crowd as well
Yeah,
too.
good.
So,
Okay.
hello.
That's nice.
Alright.
Yeah, we have big quantum here. We're all at lunch.
At lunch right now? How's it going?
It's way too high. quantum computer, it's all about, you know, when does quantum become useful? And it's really interesting, like, well, democratize quantum and it'll be used for good. Democratizing quantum will make it'll be useful for good and how do you count it? So, interesting, it's exactly what we wanted to be. Actually, I've got to check on Joe, I got delayed.
I was ready to talk to someone that was from the US.
Internal company stuff,
No, they finished talk probably close to an hour ago. They're coming back
It's my only really big
for more. Yeah.
Because I know her ways, I counter them openly. She does too. She says something to me and I call her, I don't know, hold on a second. That dude's a band 9, he's a solutions architect. What did he just say? You know, so she doesn't invite me. We got pricing around for $1 million for our clients. She sent me the pricing returns at 3 o'clock on Friday. She never really looked at this stuff. I can't believe it. Yeah, I mean, how do we run a business this way? And the boss is just like, it's all good for me. I don't sit there and say, you're in trouble. I just wish that I would have boss would review something better.
Yo, Matt, what's up, boss? Long time, man. You got a whole scruff going on, too.
I call it my Brazil
Hey, alright.
beard.
How you doing?
It was out 5 weeks. What? Oh, you mean for Southside?
Yeah.
Well, I don't have like dabs.
Oh, well, no, I heard from everybody from
Yeah. I mean, I would have told you that.
Yeah, I mean, I live here. Why would I? Yeah, I feel like it can suck up all the value.
Yeah.
That,
I wish I would have like this carnival this last week, so I didn't do more of all the events that are gonna be stuff things that you need to sign up for, like mentor stuff, investor stuff.
Yeah.
Already, so events are today.
Yeah.
Just like show and crash.
Yeah.
Pre-vetted RSVP.
Yeah, that is that. I will tell you that.
A lot of stuff like tonight,
Like the parties and stuff.
the also venture thing
Yeah.
tonight. You know, like, I'm just gonna show up, like get there early. Whether if I met her.
Yeah, I think you know. Yes.
Yeah.
I think you know. I think you know.
Yeah.
So,
But I'm saying,
I
like,
think.
but I know.
It would have made it.
I
You wouldn't. You
prefer
wouldn't
not
have to. Yeah.
Right.
But I mean, you weren't in Austin this whole time, so that makes sense.
Right.
Why you?
All I need to do is plug in this week, get my shit together.
And that's the reason why I was like, I'm not gonna pay for it.
Yeah.
So I started getting emails like, and this is my first time. Okay, I'm starting to get all the garden advice. So
Yeah. This is nuts. This is like.
I'm getting free stuff, so I'm getting free stuff. Why would we need to pay
Right.
for it? Yeah. Oh man. So
Yeah, I did Miami in January. Brazil last month.
Brazil.
It's a wild country. 3 weeks.
How is that?
My Portuguese is pretty good. Already, I speak Italian.
I mean, you have to be pretty ballsy to go. Was it? I mean, were you just doing that just for fun of it, or? No. I know. Like, I remember your whole plan. I'm saying just like, but just what is it? For Brazil. Is that like a part of the plan too, or is that just like kicks and giggles?
Eventually, with COVID, there's now more companies that are hiring international small teams, like very big teams. So you're trying to feel like, so like, who would be a perfect advisor for, you know, that one of the bigger companies, like a couple thousand employees, but like some top tier tech companies that have those kind of international workforces. If we have the solutions for them in each country, then it's gonna take some bigger to make that happen.
Yeah.
But at least we're gonna spend a little time down there. That was just supposed to.
Yeah. It was awesome.
What are you up to?
Here in Boise. Trying to grow fruit. We're finally about to launch, or I mean, announce our close our fundraise. Cantos 3 is coming. I mean, at first I thought it was just going to be Godfather, and the Catholic going up, and now we're 50 to like my boss is probably going on the Catholics or something like that. So, yeah, it's going to be long, so the biggest fun yet. So, yeah, it's going to be able to start doing some cool stuff, and yeah, so we're going to be announcing that. So I think we're going back to San Francisco. So we can just take some pictures, get ready for the whole.
Feels good a little bit.
Yeah, just a little bit. Some team camaraderie too. I go back to this. Even though I work from home. Yeah. It's good to see. It's good to feel real bodies and see real people.
What's the scene been like in Austin? What's the scene?
It's getting better. Well, I don't know about PC wise, but
have found was great. I've been meeting with a lot of people that are either just got here or about to be here that are working on some really large stuff. Like when I first came here, I didn't feel that the tech frontier was as much. I was like, I felt awesome. That was great, but I was like, where's everyone else? Yeah, I was like, you know, exactly. I was like, where's the crazy? Something like that. And so I wasn't finding a lot of that. I got ingrained into UT. Just like meeting someone that I met somebody, and next thing I know, I'm now a mentor at UT Innovation Center. UT's got tons of cash. They're awesome. They want to I mean, if you're trying to emulate something that's like a great ecosystem was, yeah, exactly.
Where this guy was trying to show off his friend running against the Shasta, and he actually plunged down the building.
California, but
That's floors.
And so. Yeah, so
they're only building these
organizations. Like they're gonna start helping founders. I mean, there's huge people, all those people that are going through there, everything. They're doing their research and then they're helping everything else. How to run the business model.
Go down to where?
Just over there.
Oh, that's actually there. They'll let you know as you start to walk to the back if you've got the right one or not. Because there are multiple people online.
Yeah, oh no, it's just that from
yeah,
general admission.
Yeah, they'll tell you if you're allowed to go back further or not.
Groundbreaking stuff happening. What about groundbreaking? But just more frontier tech.
Yeah.
Type things. And there's a lot of cool people coming down into the town, so pretty excited. Yeah, man. Austin's becoming, I think I'm here for a while. So whenever you come back whenever Austin comes back on your rotation of cities, you know, I'll figure out what the rest of the world is. Oh, you're back. Oh, I thought you were just back here. Oh, shit.
No, when I come, I had to drive car from Miami.
Yeah.
Over 2 days. So I just got
okay.
Yeah, no, I'm
Dude, that's all
2 months can go fast.
Yeah. There's all kinds of stuff in there's awesome stuff.
Were there a lot of investors that crashed that day?
Yeah, there was the Brunstein was awesome.
Was it easy to just put your name on the list, or was it pretty close to for actual investors?
Yeah, it was. I mean, I think if you could see. Yeah. I think if you just found a way to get on the system.
Yeah. Showing up in the elevators.
Yeah.
That's when I saw you. I was like, miss that hair.
That's why I love the hair. Like a lighthouse.
Yep. That works.
guys know when this event starts? 2 p.m.
Yes.
What is it actually on?
This one is Quantum Tower. Oh, I don't know.
Oh, okay. Oh yeah, I did. When we we didn't make it past the second.
They're getting invited to an HR future of work kind of dinner at the Catherine, which is really that's awesome. Yeah, up on the rooftop.
I just realized something yesterday. Just talking. You get invitations to things as they manifest.
Right. No, somebody.
You don't even need it.
Somebody else connected to on LinkedIn was like, dude, I didn't realize you lived in.
Yo, Kat, where are you? Are you still on 16? I want to hear about this pitch. You come to the quantum like through.
Oh, are these someone's waters?
It's like on the other end. I'm just sitting here with a bud catching up. You don't have to RSVP here. And if you need to, I can literally just So, by the way, Matt, this is Kat.
I think so. Yeah.
Yeah, we did.
You were there?
No, not last night.
Oh.
No, when I was, I think in Austin. You look familiar. But I don't think it was last night.
You weren't at the start of the call?
I was, but, well, maybe. The more times, the better.
You gotta tell me, like, this pitch. You could, I mean, just come on.
Just like something that's just the whole world is going towards just cutting down on middlemen.
Yeah.
And he's like, I'm gonna be in that one. I don't know what to say. I was kind of
Really, well, it sounded like you were just like,
I was
it hit a
alone.
nerve.
No, I'm just like, I don't know.
I'm sorry, I know I went on a little, like, tangent, and I kind of left you on the island. Okay, but that's,
No, I just, like, I was over by the window, and I just, all of a sudden, I started getting pitched. This is why
Oh, yeah, exactly. I feel like I need to tweet it right now and just be like, yo guys, don't, like when somebody's just hanging out with a drink in their hand, probably not the best time to go pitch stuff. I don't know. There's time and place.
Well, this is
like, and
though. That's the
I mean, if you're gonna bring up, be a little bit more emotionally intelligent in how you're gonna bring up your business. Like like, don't just, hey, what's up? This is a Shark Tank. Can I pitch you? Yeah, like, you know, like find a way to casually bring it, like a, you know, like a regular person. But you know, you gotta. Matt has been on like a little like soiree for the last like whatever. He just came from Brazil, so he's building his business by he's literally just. I call him a butterfly.
I started in Nashville, and then Austin was like the first expansion market. So there's like land here, it's another ecosystem. So I was here for 3 months in the fall, and then in January I did the same thing in Miami. Got there, now back here. That was in South by, probably for 2 months. But But then in the meantime, there's all that was go in the tech ecosystem that was just.
That would be. Where's your friend is? Where is she? Yeah. She's just.
Is she there now?
She's like a.
It's not expensive. That stuff.
Okay, when I hear Medellin, I immediately think of Entourage and or Pablo Escobar.
Yeah.
It's kind of fun. Yeah.
Phased it out.
Yeah. Well, obviously, I would not. Somebody that says they're Medellin.
Like, not a bad leg.
Really?
No places that aren't that expensive, you can really stretch it.
How do you like vibe that? Like, how did you just like do it? Yeah. So yeah, I feel like the people who do those things, they still need to have like, you know, like can't just.
Yeah, I mean,
you need to have like a little beanbag you're gonna follow on. Because you can't. I'm not gonna start just sending Australian, you know, just doing all kinds of crazy shit if I don't think I can, you know, if I end up getting into some crazy shit.
Yeah.
Then I could just like go and fall back on. Yeah, you definitely. That's awesome. That's cool beans.
I swear we met.
Did she say she was good? She said she was gonna go to Miami.
Yeah.
We met, like,
yeah.
I
know we met.
Oh wait, no, I introduced you guys. Already.
Yeah, it was like
it was
a thing on Rainy.
Yeah, on Rainy. Yeah. I forgot.
Okay, no, this actually, yeah.
It was right before you left.
Yeah.
Wow.
Yeah. That was actually when I met Kat, too.
Well, that's why I'm here. Learning ecosystems. Shake hands, kiss babies.
Yeah, that was actually when
that was a good event.
I love those.
And you guys were just launching your first investment.
Yeah, that's fun.
Wait, first one?
Well, it's first institutional. The pilot fund that they, it's like a proven strategy, did really well. So like they raised like $100 million fund because of like data strategy.
Wait, that was just pilot?
Yeah, the first
So
one.
what's the real one?
This is the same thing. It's just, they looked at the investments that they made and they said, these could be our returns and we'll just scale up our checks a bit more.
Yeah.
Because like 50% of their deals became unicorns. Like A and B deals became unicorns. So they were good deals.
Just another Honda. It's awesome.
So, I wish they were here too.
Yeah, I've never met any of the
and they don't
ensemble.
want to like, they're not being like local. They say that's my job. They're like, we have a deal in Austin, but you have to go win it for us. It's a lot of pressure.
Aren't the founders here though?
No. They're more like, you know, they come from SF. So they were just at like Upfront and like the Venture Center.
And there was one other guy.
Oh no, you meant Nesta. Yeah.
Nesta.
Yeah, he actually just moved to Denver. He's right out of Trinity University.
That's probably just a couple months. Usually
Yeah, they'll be there for, I think, well, probably around 6. It was interesting, the whole team is supposed to be
that was what I actually
up to the point where, you know, the ambassadors.
I gotta go, but he's like the.
Yeah, I run the ambassador program.
They're all scientists, right?
Yeah, but have you done ambassadors? That training would be good. Have you've done the conversations back and
Two of them.
Yeah.
The one where you get the ambassador and said, you need to use more
yeah, for a lot of people that.
Yeah, we track like 8 different startups.
Okay, well, yeah, I'd love to do some write something. Yeah, oh, it's gonna be huge, yeah. This is.
We have a
Absolutely,
lot
yeah.
of great stuff.
There's some of it. I was just talking to somebody actually. Good answer. You can get look at a GT, if you look at something like small, but like the positive reviews are scaling up really quickly. They don't have a lot, like they're growing really quickly.
Or like the percentage of like reviewers.
Well, it's more so like identifying something that's about to break out or that hasn't yet. But it's on the platform and you have those from and it's small, like they're not like big.
Yeah, that will be a very interesting exercise.
Anyway, I'll let you go.
I'm gonna run to the facilities over here, and then I'm gonna come back at 2, start at 2.
Yeah, but if you need to break away,
but also like it's kind of cool we know all this. Like, think about how like put us to use for your benefit.
You like were like I don't know, like I remember your business.
Yeah.
Boa House?
What's that?
Do you know what
Bell House.
The Boa House.
Boa House.
By the way.
On Ladybird. There's like this league, the Austin Rowing Club.
Ladybird's the way further.
No. Yeah, I don't know.
My guess is it's the Austin Rowing Club.
I'm just gonna tell you. I don't know what the Boa House is. I am glad to say though, every single person that set up a meeting this weekend actually got to visit.
That's only Saturday.
It does. Yeah.
I know you killed it.
And then it's a done.
It's like midday Saturday.
Yeah, like I saw everybody. So yeah, that means I can just party for the next 9 days now. I don't need to network.
I gotta get to that.
Yeah, there's like a bunch of events that I want to do.
Are you going to that? Austin Venture Association?
Yeah, I know that.
I sent you that thingy. Dude, I think you just need to stay enthused.
Oh, did you send me that?
Yeah, I sent you the thingy too.
The URRs?
No, wait, did I?
That one's like very.
No, it's locked down. You can't even anymore. Yeah, I can send you. I can send you the details.
Before anybody's there, good enough.
I can send you the details of where it's at.
Yeah. Look, you need
Tell
me
them how it is.
to show the party started.
You are the value proposition. I love this. You can play that yourself. One day they're gonna have like a little Ford tracker and they're gonna check on like
I know.
from Sunrise Cocktails.
Yeah.
So this is my first and last time. Next year, I'm not saying this is what we went to.
Yeah, I was telling Andrew I needed to lock in last week or 2 weeks ago. I sort of what the odds were on something. In Carnival.
Like, I'm so lucky. There's that one spreadsheet with like all of them. And the freaking guy that even let you filter, won't let you copy it anywhere else. I'm just like, what is this? It has like all of the freelance. Are you in that spreadsheet?
You know, it's more from
Hi, or Alpha?
no. I was in the one from that was more of a Google document.
Yeah.
That was
It's worse. Yeah. But this one, I mean, it's the same thing. You can't filter.
We're rotating on our
No, he's like, getting a lot of questions about the detail schedule, and they're wondering if they printed the schedule. Just like on 8.5 inch by 11, we've got like clear standard. It just has everything posted, and it's hard to look at. My mom's actually visiting. Yes. See you last night. She turned 36.
I don't know how, like, what is that?
I can make the sign, but I don't, you don't.
Do they already have the contestants?
No, yeah. I'm gonna find out.
You know how to answer in the form of Jeopardy? Just in case you get thrown in.
In the
The
question?
answer, they give you the answer, you just give them the question.
You ever, where's that coming from? What's that drinking game where you have to speak in questions?
What is?
Or who is, or where is.
What's that drinking game where you have to speak in questions?
Oh, that one, you just like bounce around and you have to like question.
Oh no, it's the where you have like a bunch of cards around a cup, King's Cup.
Yeah, is that okay?
Was that like just one of the random rules?
Yeah, like it was one of the random
It
rules.
wasn't like all the time.
I think it was like, I forgot which one.
I remember there's one that used to have like a
7
little
questions.
green man, so anytime you took a drink,
Yeah.
you could take the head off the drink.
Where's that room? This started off with like, I feel like so many people would actually show up. It's just like, it's like their little like gas station.
Yeah.
Maybe the Mad Cat computer gas station. Everyone else.
Yeah.
I think people would actually, yeah. It would just,
As long as you get
it
on
would
all
end
the
up
good
being its
lists.
own event. It would be the gas station.
There's these like auto RSVP bots out there. They'll just sign you up for all the free ones. There's some event organizers thing. Like a little program event has 300 people signed up, and no one's actually gonna show up. It's just auto RSVP.
Weekend and midnight on Raven Street. Volleyball.
Actually, I need to get some coffee shops.
Oh, what's going on?
No, it's an HR one. That's good topic.
Really? And is it like, can you sit down over there? Am I gonna get attacked? I'm not gonna tell you.
Yeah.
Oh, right.
No.
You're on the dark side of that one.
I'm not telling you.
No, there's none. There's really nothing going on. Well, it's good for me, doesn't mean it's good for you.
I want to know what's
What are you
in
doing?
front of you. I don't care
Everything in front of you.
where. Just send me this stuff.
I think I got confidence. How long is this?
What's going on?
What is this?
Yeah, yeah, you should definitely lead off with where you go. I just sent you the RSVP of this.
Yeah, so you're gonna be
Molly.
I'll be here.
So this guy's pretty cool. My friend Julian, he's partner in industry.
Yeah.
It's fun. His partner is fun.
Do you think you'll get this?
Lance Armstrong.
So you don't want to. I'll be here in a while.
Oh, this contact.
Yeah.
Oh.
I don't know if you can make it. I don't know if you're gonna see. I'm just seeing like the expert here. I think it's across the hallway. If you just go back and get food and come back.
you actually wanna go to, warehouse?
Yeah, I'll walk with you. Cat, are you just gonna call it till?
Just gonna go take
My mom's here too. She and her friend is here.
You know, contrary to poverty, you don't have to pay. I'm just kidding.
They're bros.
Like, my mom's like more fun, like she wants to come to all these events. She's bring her.
Dude, yeah, come here.
Yeah, she's
Yeah.
she's fun, and her
I
friend
think,
is,
and she's down to tango, like we're.
yeah, she goes crazy.
Dude, that's, honestly,
Seems bad.
Yeah.
why don't you tell me just come up? Or are you gonna go nap and?
What's up?
Mom's here.
You get the first intro.
I mean, I do wanna.
I'll do my little blurb.
I can't.
Welcome everybody
Stop.
back to lunch.
If I stop, then I stop for a long
We have a
time.
rally.
I stop for a very long time.
Yeah.
So I don't wanna do that.
I know, I need to like.
I just wanna keep it going.
Yeah.
I would love to be outside. Because it is a beautiful day. I think I'm excited.
I know. Oh, that's good.
How did they found this house? Because I think of these houses, I think of like little like houses. Like I think of like Rainy Street type.
Yeah.
Or this war like communist things. Like I don't think of buildings.
Okay, good.
Is it
I'll just go and get my, how many can come to in this case?
No, it's not fine.
Okay, all right then.
So is it on the other side?
Yeah, I
The highway? East?
No, it's just on. It's that Cedar North.
I'm gonna be on socks for the rest of the day.
Did you sign up for that one?
My new job. I'm gonna just fill the table with socks for the rest of the day.
Yeah.
You are.
Yeah, I'm already. Well, I think I'm gonna. I think Drew Malcock. He's CEO of Factory. He was the company we were supposed to see yesterday. I don't know how he got it instead. But I don't. That's on you. I keep my Insta. That's the only thing that I have left. That's like just
Not.
No.
Not BC.
It's pretty BC.
Taking over.
No, I swear to God, no VCs.
We're gonna go.
I will say this. I will look at everybody in my face. I'll be honest with you. Even my, even, no, it's private. And even my boss, I told him, straight up, he's like, oh, just really, I'm like, no, yeah, that's the only place I can be. Like,
The office or up here to 16. Yeah.
Did you take my card too?
Yeah, I sent both your card and
I
the
don't.
pastor
The only
are
people
struggling.
that follow me on Instagram are people that I actually consider friends.
Yeah. Well,
All my cards or my Mongo passes or what.
You're coming. I don't know if I should stay from this.
So like,
Let's go.
Hi, sir. How are you? Please, I'm already super stressed because everybody else on the panel has a PhD. It's like I'm at home when my wife invites friends over.
Oh, it'll be fine.
Oh wait, it won't be fine.
Is it being taped?
Yeah, it's YouTube.
Okay, good. Because I'm gonna go over, see if I can get a t-shirt. I made some great connections.
Of course.
How's it
That's what
going?
South by Southwest is true. That was good. I'm really interested in this space. As an idea.
whatever we don't
You
use
can't
today,
go. You
they
can't
have
even
some
go and give
left
faster.
from the VIP that they not give away. So,
We're gonna talk
I
about
already
next
took
year's thing. I want to like.
Elena,
I can't even bring one to the theater.
tour lady. I did want to call her something.
we had a quantum conversation with the DoD.
But here's the other thing, is maybe
A lot, right? What's ginseng?
So I'll see if I can make this, this is all the way over at the,
Well, get back for 4:30 if you can. 4:30 is National Defense.
so back at this room at 4:30? What time?
So we're gonna do quantum talent, quantum technologies, then quantum.
At 4:30.
Yeah, quantum defense. Right now. 2.
Yeah.
You probably know I do it anyway.
Well, you're someone able to?
Yeah. James from NVIDIA.
So you're one of those PhD knuckleheads he was talking about?
I don't know.
Just try to listen to that.
I never say it.
No, you never.
Say it.
He never said that. Never said that.
What did you get?
My wife would kill me.
Oh, okay, what is there?
I did ask her as I got out of the army, it's like, why don't I just go get a PhD?
Oh,
You know,
okay.
you're not the type to go get a PhD. You have a master's, just roll with those.
16 was good.
I tried to read her dissertation on cognitive science.
You're right.
Oh, yeah, and we went to like the third.
Is that the Yeah. She, graduated from Northern Illinois University, PhD in cognitive science. She did her undergrad at New Mexico State. Her advisors only advise one PhD. Wow. She gets a lot of calls from her advisors running projects. Can you help? You're the only people we want to understand you than some of the other postdocs I've grabbed from the way. So, yeah, it's really interesting. But unfortunately, she got
Been here all day?
part of
Get up.
Yeah. Was
No, it's good for me to get up.
an
I've been sitting waiting
academic
for my 10 minutes. I get it.
We do 7 times in 5
Just
years.
came up from Cyril Week, gas site down in Houston.
And had a
that was the
vision
thing that you
of like,
saw, statements coming out.
she works in the nonprofit space, really good. Trying to bring curriculum to veterans programs. They're trying to bring veterans from basic programs to veterans.
They were, that conference, yeah, it's just big.
Being a PhD in a nonprofit, PhD in
There's hydrogen there, there's batteries there, there's all kinds of stuff. But anyway, I was down there.
Pittsburgh. Really?
Yeah. One of the people
I was born in Beaver Falls.
DOE, Jim Fritz.
Didn't stay long. I only stayed till I was 3 and then
Yeah, so I got to meet Jim.
My dad got
He
hired to
introduced
Miller
me to
Brewing
one
Company.
person overall in the government
I
lab.
became the PR agent for Southern California Miller Brewing. And I was a team player. 7 or 8-year-old. Growing up
So
in Southern
she
California.
works for Jim Fritz.
With a dad who was in beer.
Person in San Diego. Yes, he knows about it. We gotta talk to you guys.
Do you do a lot of work with Carnegie Mellon, AI?
Interact with all the government.
So you're in CCL, right, at MIT?
Yeah.
So there's, down at Carnegie Mellon, they're really connected to the DoD, there's a task force, well, that's called a set called the AI Integration Center. They're trying to help the DoD pull out the applicable use spaces in AI. Actually, it's run by a friend of mine. And they're linked up directly with the Army. The center is on the, like a hill up there.
And I think you're on the
Yeah.
That should go really well. That's a follow-up.
Really cool. They just think maybe there's some.
It's more into the business.
What MIT's doing in AI.
Can you do this, can you do that?
There might be, yeah, I hadn't heard about that.
Yeah.
That sounds cool.
But no, fantastic.
I mean, I know they had a lot of robotics. That's what they were really doing.
It's been fun. Don't leave.
Oh, grab the spot there, you say, grab the spot now, put your bag on the chair. That's good to hear that, yeah, I was
Yeah.
That's actually my whole I did assistant for a couple of years out in White Sands.
This is one on the pond.
You want to buy everything that you're going to use, and the buyers for the army.
Well, yeah, he down for kind of, yeah, that was, John.
Natural, they've done it for legal.
No, not John, I thought they had, oh, remember.
Like when I was operating the army, I said, I want something from IBM.
Yeah.
Go to a middleman and say, will you please buy me this AI from IBM? And then they write the requirements, and they buy it, they don't talk to me ever again. So they present me, here's what we bought for you. And I'm like, here, I asked you to give me a 6-pack of beer, and you come back with sparkling water.
Sounds like
It's unfortunately all too common.
Well, now I flipped it. I retired in 19 from Army. January 2020, I retired from the Army. So I flipped and went to IBM. And now I'm on the other side. And I'm telling all my operator friends, look, you have to see what people are proposing to the acquisition guys. Because if you don't know what we're saying, you're not in the conversation when you get what they buy for. But then I sent out one of my proposals, and the lawyers, IBM and the owners, were like, hey, you tell this Brian Cook guy to stop handing out proposals. How are we going to have a conversation? Especially in COVID, any conversation. Yeah, sure, right.
Will Oxford.
So you're shaking hands with Chris Bass?
Oh, yeah. Chris, I've known Chris for a long time.
Chris and I are both Calvary.
Oh, yeah.
We crossed paths several times in the army.
Yeah, he's a good guy. I like him.
One of the things we joke about here is that you can't swing a dead cat in the army and try to throw him again. And so it's just really cool to have a team. We come in here and do a defensive leadership council. They don't voice out different programs.
It's almost like you have to know who to approach the right people are, because otherwise from the outside it is an old boys club and it's hard to get in, and it is quite clearly old boys, right? So one of the things I love about Quantum is that it seems to be much more intense than any other physical science that I've been involved in.
I didn't even finish the word quantum, even reaching over my shoulder. It was a slipper. I need my glasses.
Very Okay. They're generals.
No, they're retired generals.
This back spot.
Yeah. Well, unfortunately, it's a societal thing. We train them from birth. Thank you so much. To have that kind of an attitude. And I have 2 daughters, right? So I have been fighting that my entire adult life.
I have a 23-year-old and a 12-year-old. Sarah's free.
Just in case you want water.
Oh, were you bringing other things too?
Oh, sorry. Alright, so I already know you have introduction. And then perhaps we can talk about at some point we may not. I'm assuming you'll be taking questions like all the rest of them. We can't see that clock, which is why
Yeah, I mean, it does seem like that.
But I was going to say for the next session, maybe just as we wrap
Oh, okay, sorry. Unfortunately, I'm not
Good. I might stand up in the middle of it. I'm not bad.
It's your stage.
Oh, okay.
Yeah, make sure you let the panelists talk. That's a joke.
joke with everybody, I've always done all my stuff online, so. Do anything first, not repeat. Sure.
Totally old fashioned. Up in Northwest. Yeah, I'm up in Chester. Yeah.
I was right in the middle of the pandemic.
Well, we've been here 27 years, and it's gone up a little since. We moved out of here from Sulphur Valley here, and
Wearing black.
that wasn't the reason we moved here. That didn't hurt.
It was a demonstration. I did. I had to get out there and use alcohol white drinking.
Well, I mean, if you move. Oh, that's great. Yeah. Well, I think well, we're very fortunate that we got in when we did. Austin is like crazy. To be honest, it's like, it's just too crowded. It still has a lot more. I know, it's crazy. I mean, I thought it's still when I first moved here, I kind of worked at overlooks the 360 bridge, and people would go downhill and you're in the office, but yeah, 620 part. Yeah, we moved to 95, yeah.
And then it was like.
And it was cool.
Right. Oh, yeah.
Probably it's still cool in a different way, right?
Yeah.
But it's still better.
So you don't really like
You know Joe Brooks? Is he here?
Yeah. He's talking at the board. He went down to the office of.
Oh, great. Yeah, I've known Joe for years. Yeah, great. Another great guy.
So, what I'm hoping to.
Well, I haven't seen Joe in a while. Yeah, that's great. I actually seen him.
This is
foundation, father for UBC, and we've been very active with
You're talking about Joe.
Yeah, you know Joe. Everybody knows Joe. Everybody knows Joe.
So what you guys want to say? Same way this year?
Different, do it different. Separating yeah.
Well, Charles, you're in the middle. We want to touch in and let you figure out your. Actually, the Army gifted me with that. Halfway through my So we get started in about 2 minutes, folks, so if you want to silence your devices, we appreciate that. Since we've had a couple of rounds of Amber Alerts during lunch. Really good way to disturb a pandemic.
And unfortunately, this is Texas, so Amber Alerts and Silver Alerts are like a daily thing.
Right.
Yeah. So they stay.
I'm not mad about it.
Not a few days.
John, is there another quantum joke you want to share with us?
He's got a hold of it. He's gonna write a book. He's gonna dovetail off of Worley quantum jokes for babies.
Yeah, it cuts it way back.
I'm sure.
Two keep talking no more. They walk kind of incoherent.
Oh, wait, I get it. So, what's the difference between a quantum theory conference and a fashion show?
I don't know.
In the fashion show, the models actually work.
The John Show. All right, so good afternoon, everybody, and welcome back from lunch. Hopefully, you got some nutrients to get you over the hangover from last night. For the after party this evening. Thanks for joining us today. If you don't know me, I'm Brian Cook, a retired Army Colonel who used to work at Army Futures Command. I lead the IBM Army Futures Command and Forces Command client-facing team here in Austin. I'm joined by three quantum superstars. They're probably getting mad at me, kept calling that. Olivia Lanes from IBM, Charles Wan from MIT CSAIL, or the Computer Science AI Laboratory, and then Jin Sung Kim from NVIDIA. So just a little bit about the structure of the way I'm going to run the show, actually let them run the show, and hand it off to them. We'll start off with introductions, and you get to see where their expertise lies. You probably know some of it already. And then after we get done with the introductions, I'll just turn to them for perspectives for how we get after quantum talent. What are the challenges and catalysts that we can twist and turn on to get further with quantum talent? So I'll turn it over first to Jin to start off with introductions.
So I'm Jin Sung Kim. I'm from NVIDIA Quantum. So I guess a little bit about myself. I spent the past 3 years at IBM Quantum as part of the research staff there. I did my PhD at Princeton, studying single spins in silicon systems. And I guess just to plug a little bit what how NVIDIA lies in the quantum ecosystem, we're relatively new to the quantum scene. But what we've done is built an optimized set of libraries to run quantum circuit simulations, very performant, very at scale, on GPU backends. So we think that we're entering like this very interesting era of quantum computing where the hardware and the systems, the actual quantum systems are relatively small, relatively noisy. It's kind of hard to do actual useful things on them beyond small scale demonstrations and learning about the hardware. So we think that to really enable algorithms research, it's very useful to be able to run quantum circuit simulations on performant backend. So on things like GPUs, which NVIDIA is obviously very good at building. So we've actually demonstrated some benchmarks where we've been able to do some really nice speed ups on quantum circuit simulations using GPU backend. So being able to simulate up to hundreds or thousands of qubits at a time. This is something that your CPU will have a lot of trouble doing. The actual performance and the execution of these simulations is actually much better than what you would see on the CPU. So that's the end of my little plug. But but yeah, just really happy to be here with everyone today.
Charles,
yeah, hey everyone. I'm Charles. I'm a researcher at MIT, where I do research on quantum programming languages. So the basic idea of the question that we want to answer is, what does it mean to program a quantum computer, and how do we help people do that? So some of the questions that we want to answer are, how do you take a classical software developer you pick up from the Googles of the world and give them the basics that they need to understand how to operate with qubits instead of bits, how to operate with quantum data, how to take their existing classical computations and lift them to work on a quantum computer, so to speak, and also how to go beyond that, right, to implement quantum algorithms and design them and test them, using all of what we know about classical software design, testing, deployment strategy. I'm a computer scientist at heart, so I tend to view things from the perspective of saying, we have a piece of software that wants to run on a piece of hardware. What is stopping us from doing that? So, for example, one of the perspectives that we have is, can we take ideas from the design of classical compilers and optimization techniques for a programming language like C or Python, and take those techniques and apply them to the quantum world? Another question, which is from a slightly different perspective, is how do we build languages where the core constructs and the meaning of the features in the language are quantum, so that you can take an existing quantum algorithm, like Shor's algorithm, let's say, and write it in a way that makes more sense, right? That you can actually hope to take apart and debug and understand if something is going wrong. And even to design new algorithms by taking a template for how to obtain quantum speed up for some application and tinkering with the parts so that it will work for your specific case. If you were here for the morning session, there was a pretty funny comic on the screen at one point saying there's a quantum computer and it's a superposition of I have crashed or I have not crashed. Yeah, when I saw that I didn't actually laugh because it's a real problem that you need to deal with. Believe it or not, a quantum computer, it is very hard to tell whether it has crashed or not. It can be like exponentially hard to tell whether you have encountered an error in your program. So it's like literally something that we need to build from the ground up and figure out how to do.
All right, hi guys. I'm Olivia. My background is as a PhD in physics. I did my thesis on superconducting quantum measurement, and then I graduated during the pandemic, which was super fun, and moved to IBM very shortly after that. They still let me work in the lab at IBM in my copious free time, but I am mostly in charge of the Qiskit community and the SDK that we're building to use all of our quantum computers. So I am the lead for the North American team, and I'm a manager on that side of things. And IBM basically started the whole cloud computing era in 2016, I believe, by putting the first quantum computer on the cloud for anybody to use. It was really, really small. Can't really do that much with it except play around, but at this point we have over 20 deployed devices on the cloud right now for literally anybody to use. You can whip up your laptop or your cell phone right now and plug a few HIMARS and CNOT gates and send them to a computer in New York if you really wanted to. But yeah, so I work a lot on the education side of things as well. I work a lot with researchers, with educators, and academics who are trying to figure out how to use these prototype quantum computers, not just for research, but also in the classroom. And I've done, a bunch of hiring for interns and full-time hires over the past year and a half. So I know a little bit about the talent, the need for quantum computing professionals and experts, and I'm just really happy to be here and looking forward to the discussion.
Thanks very much. So that's what we're going to try to talk out or pull out of this and stoke a discussion. Hopefully we'll use the same model that we had this morning. So if you have a comment or a question as we're going through the perspectives of the panelists, just go ahead and raise your hand and get started with it. So the bigger piece of this is trying to continue the success we've already had with quantum. There's a good deal of success that we've already gained throughout the world, really, but specifically in America. So how do we pivot off of that and get the community of interest to go further with this? How do you attract and empower the right people that can come and help this endeavor? And then what are those things that you use? What are the ways and means that you to actually attract an impact? What are the strategic partnerships? How do you equip your educators? How do you get community involvement? How do you take the young computer science developers like my son up in 4 Points who knows Python and get them on quantum? What are all those pieces of parts? I'm going to turn it back over to Olivia, and we'll run through all three of them, and then we'll open it up for questions. So, Olivia, right back to you.
Yeah, I mean, I think, the biggest problem that we have right now, and if you're working in the quantum space, startup big company, the biggest glaring issue is that there's not enough people to hire for your specific projects and needs. There's not that many people who have expertise in quantum computing or are molding their skills to be adaptable for quantum computing. So there's a couple different ways that we can, address this. I'm part of an initiative called the Q through 12 initiative that's trying to basically figure out how to make quantum computing available as an educational tool in elementary through 12th grade. Now that's a really hard problem. How do you teach quantum computing to elementary school kids? I don't know. We've got a lot of really smart people working on it. It's a hard problem. But the other problem for right now that's a little bit more immediate, and I think that we're going to end up talking about here how this is a generational problem and we're not going to solve it overnight. But one of the big issues right now is I think up until this point, quantum computing has sort of been a PhD club where the people that you're hiring to work on the quantum computers really have to be a leading expert in their field. They need a PhD. There's not that many PhDs. It takes like 6 to 10 years to get one. And if you need someone to build a quantum computer right now, you're working with a really small pool. So one thing that I think is developing right now that's of interest is a lot of bachelor's programs, focuses, concentrations, and even some master's degrees that have popped up across the country in quantum computing. So I'm really interested to see, will big companies, will startups be interested in hiring from these places, and how can we work with the universities and these partnerships to make sure that the graduates coming out of these programs are well equipped, because you just can't learn as much as a PhD would in 6 years as you could in a 1-year master's program, right? But if we focus on the things that are really applicable and important for right now, you can have a very successful career and pick up a lot of other stuff on the way.
Charles. So imagine that you're trying to teach computer science or how to program, how to build applications and software to somebody. But instead of teaching them at the level of saying, we're going to add numbers, we're going to use Python, we're going to build web frameworks, draw pictures and make them all connect together. Instead, you have to do it at the level of bits and bytes and logic gates and assembly instructions. That's basically what we have to do in quantum right now. It's actually slightly worse, because on top of that, you add the fact that a qubit is, well, it's quantum, and you add the noise, and you add the fact that there's no actual hardware to run it on. And all of that makes it very hard for somebody coming into the field to actually know what it is they should be doing, right? They can spend a year or many years figuring out, the characteristics of the hardware that they want to use, or the physics and the math necessary to really understand the algorithm that they want to implement. But that isn't what we expect of software developers in, the classical world, right? We're training people how to do specific things and think about very high-level concepts like how to build software that is fast and reliable and can be easily manipulated and maintained. So something that we're going to need moving forward is it's really having the right set of abstractions, right? This could be in the form of a programming language or some software framework or anything really, but we need to have a common set of tools and terminology for people who are coming into the field from classical software, classical engineering mindset to be able to use.
So I think I agree with everything that was previously said. So to Olivia's point about really training the next generation of quantum researchers, I think that's very important. I think a lot of smart people are doing great things to educate people from an earlier age. And to that end, I think that the best way to learn is to do, right? And I think places like IBM have done a really great job of democratizing access to actual hardware, which I think is really, really cool. To take it a step further, though, there's only so many actual quantum computers that are available. So even when I was a researcher, getting access to some of the quant hardware was actually very difficult. So you had to, you know, you had to fight for your time on the actual machine, and even to get anything done, you know, the time has to be portioned out. And, you have to be very strategic about the jobs that you're around. To this end, I think that, you know, continuing on that vein, I think having democratizing simulations, I think that's also a very important thing that will drive the field further. So if you're able to run a simulation that's not necessarily on an actual quantum hardware, I think that could be a very useful way of democratizing access to concepts and the theory of quantum computation.
All right, so we're about to open up for questions and comments. So I want to kind of cheat because I'm the moderator and ask you guys your opinion. So I have a 12-year-old daughter, and I told her, so I'm going to moderate a panel on quantum. So I had to have the discussion about what's quantum bad. How does my daughter start to learn about quantum? How do her classmates think about and get involved in quantum?
You should talk to me.
Yeah.
No, I mean, I would love to talk to your daughter. I do a lot of outreach programs. I especially love seeing, you know, young girls getting involved in STEM at an early age. It's super important to me, super important to IBM. But I think, you know, at that age, right, at the age of like a 12-year-old, 13-year-old, is it so important that we teach them quantum computing? I'm not sure. Like, it's really, really cool, and if they want to get on and, you know, program a few basic circuits, that's awesome, and we can teach them how to do that, and there's tons of information online for a really motivated student. However, I think what's really important in terms of quantum computing education is that it's not just for quantum computing. Quantum mechanics is awesome if you've ever like been exposed to it in a classroom. You know, we talked earlier about how it was so motivating to see it happen when you're just 19 years old. I just want a 13-year-old or a 12-year-old to walk away from any type of lecture or, you know, demonstration, just think, quantum mechanics is cool. I don't care. I don't care if they know how to run a circuit. I don't care if they are, you know, really digging into the hardcore Python at that point. I just want them to think quantum mechanics is a thing that exists and it's really awesome. Because I think that thought will permeate, and you know, if you just let it marinate in their minds for a few years, by the time they get to college, hopefully, you know, they'll pursue it further.
Anything else, Carl?
Yeah, I agree, Olivia. For someone of that age, you know, for a computer scientist like me, I think that, you know, kids of that age, really a lot of adults, would benefit from understanding what is easy and what is hard and what is possible with any computational technology, including quantum. Right? So, as computer scientists, we call this computational thinking. It's being able to take a problem that you're faced with in the real world. Right? I have a robot that needs to get from point A to point B. How do I turn this into a set of instructions, a set of commands, a program that tells it to do that? And then we can think about, well, what are the better and worse ways of doing this? Which ways are faster? Which ways are realistic? And ultimately, of course, we'll get to the point where quantum actually makes a difference, where we say, what are the things that are hard for computers to do? You know, a few years ago, we thought it was hard for computers to recognize whether a picture was a dog or a cat. This was something that was very difficult to do. Enter neural networks and machine learning, this is now something that is considered fairly easy. Today, we consider, you know, Shor's algorithm, factoring big numbers, to be a hard thing to do. Maybe tomorrow it will be easy. And so, I think the biggest takeaway that somebody can have from quantum computing or any related field is just understanding, what can we do? What do we know we can do now? And what in the future we suspect we'll be able to do as well? Which, you know, it just opens a world of possibilities of actually applying these ideas, and also, if you want, doing research to figure out new ones.
I appreciate that. Jay?
Yeah, so I think in order to learn quantum, there's a lot of math that you need to know, and you need to be inspired to know it. So a lot of times when I'm presented with like a Hamiltonian, or I see some equations or like linear algebra in a paper, I have to fight the urge for my eyes to just not glaze over and to sit down and work through it. But you know, at the end of the day, like I know that like what's important in the field and like where the field is going, and having that I guess 1,000-foot view of the field and knowing what's important like having that inspiration is really important to instill young people in order for them to really get excited. So like once they know like, oh, this is a cool field, like we should drive towards this, then that gives them the motivation to really sit down and, like, for me, like work through the Hamiltonian, work through the math.
Yeah, so one of the ways that we're doing this in AI and ML in Texas is there's a program down at White Sands where they bring the students to the proving ground, 6th and 7th graders, and they get to fool with robots and actually program them, right? So you get that thought process to get them excited to actually taste and smell what they can possibly do. John?
Yeah, I've heard people express that while certainly you need and want some people that are seriously involved in quantum computing and quantum software, that you also, to make some of the things that are going to make all this possible, you need mechanical engineers, you need maybe chemical engineers, a wide variety of skill sets. And so while you do want to concentrate and try to figure out how to bring the best and brightest in to tackle directly some of the real hard problems of quantum computing, I believe, to your point, just to have some appreciation of quantum things generally will help. And people tend to work on problems that they understand. If I'm trying to make a quantum resonant tunneling device, I can tell somebody, well, we need to have really good control of the tunnel barriers and the width of the quantum well. But if they understand that the tunneling rate through this is exponentially dependent on the thickness, they understand how important it is to control that. They understand that quantized energy levels depend on the thickness of this. So I think, would you agree that it would be, in addition to the talent that you need to work directly in quantum computing, that a more general quantum aware set of engineers would be really valuable?
Yes. I agree. No, I can elaborate a little bit. So, I mean, I think it's really important, like you said, to have all sorts of people involved in the field. It's very interdisciplinary. I think not only do we need specialists, we need people like you were talking about, engineers, computer scientists. I think we can come at it from, you know, a bunch of different angles. Computer scientists, I think, should learn a little bit more about the physics to be quantum aware. I think the physicists, myself included, need to learn a little bit more about the computer science in order to be, you know, the best research scientist I can be. So yeah, I totally agree.
I also agree, but I do think there's value in something that Charles mentioned before, in that if you're able to abstract away certain elements of the stack, you can come in as someone who's not familiar with the field and be very productive if things are abstracted away the correct way. But I definitely agree in the sense that like more is better, more awareness is better.
Right. I think, you know, in the early days of a technology innovation, the pioneers have to know more about the overall environment. You know, I got a computer science degree, you know, 35 years ago, and we had to learn assembly language. We had to learn how an operating system worked, down to memory managers and processor schedulers, and we had to learn how networking protocols worked just so we could write the code above it. And so, like, it seems like that's where quantum is today. But you know, the success will be when the developers aren't really even using the word quantum, because what they know about is the capabilities it unlocks. And you talk about the abstraction, and it seems like blockchain might be, you know, a step or two ahead. Where right now blockchain developers still need to understand a decent amount, but it's not very far away where high schoolers and young college kids are going to be, well, they already are, coding on the blockchain without knowing details of how the blockchain works. Am I thinking about it kind of the right way, the analogies?
I think I agree with that, because I think there's this growing community of developers who, you know, aren't necessarily from physics backgrounds, but they are starting to understand, like, pick up the concepts of quantum computation, things like entanglement, how to program them, and really, you know, if you have access to like a Python front end, you can start programming some basic quantum applications. But to that end user, I don't think it's necessary for them to really understand, like, you know, the material science, like, you know, the nitty-gritty, what's going on microscopically, because at this point we also have front ends that plug into various backends. So, you know, ideally, in an ideal world, you can write a quantum program and then you can send it to any variety of like quantum backends. So in that sense, I do kind of see that dichotomy starting to emerge.
The other parallel I would draw, I mean, you mentioned blockchain. I mean, machine learning is another example of a field where the success of the field has just been entirely dependent on people's ability to immediately take the technology and start hacking on it, while they do not actually understand necessarily how it works. And quite frankly, very few people, if anybody, knows how it works. But the fact is, it works. People take it. People use it to do their own cool things. And eventually they just think about their applications and stop thinking about what is powering it. I think we are, of course, a long way from that, but it would be a great world to live in.
Yes, in IBM and in NVIDIA, which current initiatives do you have to recycle talent that you have in other disciplines to what?
Well, I don't know if it's recycling per se, but we have a really huge internship program, and we hire at all different levels for the internship program. So we hire PhDs, master's students, undergrads. We also have people in IBM who don't necessarily work in quantum who are allowed to do part-time work in specific quantum careers as well, you know, like give it a shot, see if they like it. And this internship program and these co-op positions, I think, really help fuel our talent pipeline. And we've always been of the opinion that the more people that are doing quantum, the better. So it's not like we're going to try and hire every single person, you know, who does an internship with us to IBM, but the more quantum talented people there are in the ecosystem, in the world, the better off we're all going to be.
I guess on the NVIDIA side, the short answer is I don't know as an external hire, and I won't never one. But a more serious answer is that a lot of the engineers that we actually have on the quantum team actually have physics backgrounds. So this is this is a hop and a skip away from recycling talent from a completely different field. But these people who have physics backgrounds were working on other things, but then got looped into the quantum computing initiative.
You'll wait for a while.
So, there are a lot of challenges that have to be faced to actually get to something that works out there. And the thing about quantum computing is it's got so much potential, and there's a lot of hype out there now. And so, there's a lot of cash flow, and people are hiring, and you're trying to build up teams to do it. How long can you sustain that before you start actually getting some ROI? But where are we on that hype cycle?
Well, it keeps getting worse as far as I can see. So still going up, I think.
Well, it's still going up, but how long can you sustain that without getting any kind of return?
I don't know if someone else wants to take this. The short answer is, I don't know.
Yeah, I don't think there's no return.
I think the hope is that, okay, so obviously the gold standard is reaching, fault tolerant quantum error correction. And that's, where the exponential speedups are proven. But we're entering like a really interesting regime where, there's starting to be some small scale demonstrations of, either quantum supremacy, or there's some theoretical, like very rigorously proven mathematically proven quantum advantages that are being put out. So I think my hope is that within the next decade or so that more like proven, mathematically rigorously proven quantum advantages are produced for near-term quantum devices. So things that can be run on these noisy intermediate scale quantum devices that don't require quantum error correction, but you can still get some sort of quantum advantage out of them.
Yeah,
so
I agree with you.
That's kind of the hope for the near term before quantum error correction is achieved.
And I should have said, sorry, I should have said, IBM and there are other companies as well. We've laid out our roadmap for the next 10 years. We have very specific goals that we're trying to meet in terms of software and hardware at every single year. And we have continuously met those goals, and we will continue to meet those goals, up until 2030. I think the roadmap extends until. So that's our plan.
April 14th.
Oh, I'm sorry. Yes, April 14th, which is World Quantum Day. I think that's why it was April 14th.
To build on your analogy to data science, that term probably came into common usage fairly recently, maybe around 2000. And it was just that one term, data scientist. But it's now involved in different specialization, machine learning engineer, NLP specialist. specialist, data engineer, goes on and on. Where do you see specializations evolving in the quantum field, and what are some of these titles that you might see going into the future?
So at least on the software side, basically we are trying to build the whole stack, software and hardware, from nothing. So basically anywhere there's a classical person working on a compiler or some sort of operating system or some sort of protocol for distributing your computation efficiently, there's going to be some sort of quantum analog. And the quantum expert is probably going to have even more responsibilities because all of those things, distribution, parallelism, efficient scheduling of your computations onto your qubits, all of those tasks are going to be even more important if your qubits are going to be limited. So at least from the software side, I can pretty confidently predict that just about every classical software engineering title or reliability engineering title is probably going to have some sort of quantum equivalent. Of course, they're probably going to have to wear many hats in the interim.
So you just add quantum to the current title.
Just stamp quantum on them, we move along.
That makes it easy.
Yeah, I was just going to mention in regards to the issue with high beam, I came from Santa Clara, California last year in a big quantum conference, and they were already talking about the hype going down. A lot of people were upset because they brought the financiers up. They had a panel, and what do they talk about? We want to see something that's realistic, that's in use, so they could prove useful in a few years. And so the idea there is that, yeah, the companies like JP Morgan Chase are looking at investing in it, but of course they want to see an ROI. That's a big thing. In regards to the education side, I take myself as an example. I went through the Q World out of Riga, Latvia, and I mentioned it earlier. But you've got lots of people coming in, engineers, data scientists, and then just general educational personnel that are trying to build courses for other people. And out of the 300 people that started, maybe 100 last, and some people have no idea what they're doing in the quantum world, but I think it's the exposure. In regards to the 12-year-old, if anything, exposure is the most important thing, I think, at least so that they know and understand. A lot of them are going to come in and they're not going to continue or pursue a STEM career, but at least they know something about it. And if you can affect a few of them, 1, 2, 3%, I think that's important. So I think the exposure is the important part. I'm glad that this conference is going on. I mean, there were so many people there in California when I was there, and it's great to see that this, I was talking to Mr. Hurley earlier, that a few years ago when he did a talk, no one, there's very few people, and now look at all the people that are here, highly interested.
This is a loaded question, but if you were to advise a college freshman as to whether they should major in computer science or physics, have a great career in quantum computing, what would you tell them?
Well, I always ask them what they enjoy, because there are no guarantees in life, right? You can do everything by the book, you can get the right degree, you can have the right internship. There's no guarantee there's a job for you at the end of it, not in this field, not in any field. That's not to try to be too negative, but I think it's really important that you do something that you're going to enjoy and you're going to build skills that are applicable to many different things in the long run. So if you have a student who enjoys working with their hands, I should say, engineering might be the right choice for you. If you have somebody who really wants to fundamentally understand the nature, maybe physics is your path. Or if you love programming, I would say computer science. But I think it really just depends on what career you want specifically in quantum computing, because like my fellow panelists said before, we need everybody. So, sort of choose your own adventure.
Yeah, I agree with that. And it's a great question because I was in that position not that long ago. And so, in thinking about it now, when I was coming into this field, I found it to be pretty much dominated by physicists, at least in terms of the people that I was interacting with. So there's arguments to go either way, right? For example, you could try to learn their language and work better in the world of physics because you'll be surrounded by physicists. I also think that it's valuable to take other perspectives and bring them in to, for example, just make sure that we're not reinventing the wheel, right? A lot of computational concepts from classical computing and software engineering are really valuable and should probably be imported or emulated in some way.
Yeah, just
I guess just to kind of add a little color to the ROI question, and you know, feel free to you know, please add thoughts to it as well, because I'm sure you're seeing similar situations. The use cases are happening out there now. I'm with Zapata Computing, and so for instance, we're doing stuff in catalyst chemistry, right? And not all of these are necessarily on a quantum computer. In some cases they are. In some cases they're on a quantum simulator. But you know, we're doing things in catalyst computing at some of the tier 1 oil and gas companies, which started at 100 billion and go up. Right? It's all the big oil and gas names you would know. You know, one of them came to us with a 20-year-old catalyst chemistry problem they couldn't figure out, and so we threw a bunch of quantum scientists and engineers in a room with their subject matter experts and wrote up some algorithms. Within 2 weeks, we solved a 20-year-old problem that the industry had yet to figure out. It's going to be kind of an interesting thing going on this year, which again is probably going to end up more on a quantum simulator than a quantum computer. But we've actually, and this is in one of our press releases, we actually teamed up with Andretti Autosports, which is kind of cool. So our CTO is going to be in the pits with them all IndyCar season. We're going to have folks in the trailer nearby running quantum ML on their real-time race day game. So some of the use cases are starting. You know, Monte Carlo models in finance, which of course if you can do Monte Carlo models in finance, right? NVIDIA, I came out of semiconductor. I was a couple decades in there. Monte Carlo models are big in design and manufacture. So use cases are starting, but to the ROI question, it's not self-sustaining. You still need to be funded. But certainly any thoughts you guys have on that? Because I'm sure you're seeing use cases as well.
Yeah, so building off of that a little bit, I mean, the ROI question is always being evaluated relative to something else, right? The opportunity cost of investing in this or something else. And so sometimes the struggle is coming up with an application where this technology is uniquely good at solving it. And so the question that I would ask myself there is, what are the sorts of applications where the best way that we could know of solving these problems, which we want to solve, like, you know, the quantum chemistry ones, what is the best way of doing that? And arguably it's with a quantum computer. You can't do it without one, right? You could spend all of your time and energy investing billions of dollars into better classical computing infrastructure. It will never allow you to simulate nitrogenase, right? That's just strongly believed to be the case. So, you know, if your goal is to better the world by helping us solve nitrogen fixation, then the ROI is, there's nothing to evaluate against almost.
That's really good.
I guess, you know, hundreds of millions of dollars going into it, right? And usually when you invest, you want some off-ramps along the way. Do you see any potential off-ramps that you could work towards that will eventually get you to quantum computing, but can apply more practically to something else?
Yeah, I think so. I think first of all, I think expectation management is very important to be able to just getting that out of the way. But I do think there are a lot of interesting things that are currently coming out, quantum startups and things like that. So I know there's various quantum startups that, you know, in addition to working on hardware, they work on software and AI and ML solutions for things like control solutions. So I think, you know, even if the quantum hardware is not developing at the rate that we want to for, you know, quantum advantage in the next 3-5 years, something like that, I think a lot of still like interesting, useful technologies are still coming out in the field.
Yeah, and I think managing expectations is a really important point to focus on. We keep talking about, you know, applications, not just at this conference, but, you know, all over the world and the internet. The most interesting applications of what quantum computing is going to be. This is a budding technology. Whenever people ask me what my favorite application of quantum computing is, I say, I hope we've never even thought of it yet. I hope it's something that nobody has even, you know, had a neuron firing thought about yet. I hope that that is going to be the coolest application, because everything is still just getting started.
Yeah, actually, exactly to that point, you said you don't know the application yet. My question was, you talked about specific use cases. Is that a need at the moment? We also talked about ROI. ROI generally means industry application, right, somewhere in a commercial scale. is that actually what's important right now, or coming back to the talent part, are you looking more for researchers because you're actually very, very early on in the hype cycle and still in the research phase and not even near to even thinking about productization?
Well, IBM has a lot of different strategic partnerships with large corporations, large companies. I actually particularly work on the academic collaboration side of things because that's the people that I'm really interested in focusing on, because I think a lot of the new gold nugget ideas are coming out of academia still, because like I said, this is really a new fundamental technology, and it's not necessarily ready to be, you know, stamped and commercialized at mass yet. So that's something that I think is really, really fun, is collaborations with lots of academics to try and figure out these breakthroughs that we're going to need to move on to the next stage.
If I could, I'd like to push back on your comment that we're way far away from commercialization.
Oh, that's my question.
Well, D-Wave is making quantum computers are not universal quantum computers. They're made for optimization problems, and they've got a market. They're selling them. The length of time to get to a universal quantum computer is arguably some period of time away, but for something that can be a quantum computer for quantum communication, it's a much simpler task. It doesn't take thousands of qubits. So I would say we're not that far away from return on investment on quantum technology. It's a lot. I think still, I'm not sure how long till a quantum universal quantum computer. It's not going to be real short for sure, but there are some active applications of quantum technology.
The quantum key generation, no, I think there's an organization or company that produces quantum keys.
Yeah, so we're not that far away from commercialization. Maybe not the huge commercialization we'd like to see that will come.
Yeah, I agree.
So, as you have all these challenges with quantum computing, are there other disciplines that you're seeing emerge that are going to be important to pull in as we go? You know, chemistry seems to be one that hasn't really been the first go-to kind of discipline. Is there something emerging that
I think quantum machine learning is a really emerging field.
Which one?
Quantum machine learning. Yeah, so I think I've seen a couple of recent papers coming out with some like rigorously proven quantum advantages if you had a good quantum computer for machine learning applications. I think like quantum information science is obviously an old field, but that's not really something you can major in. But I think a lot of like really important developments need to come out of that field as well, for like devices and trying advantages on noisy devices, things like that.
Have you seen any quantum wireless charging?
Quantum wireless charging? I don't think so.
We have a startup company that we got Boston in March that they have developed quantum wireless charging outside of the electromagnetic field. Charging point to point, kind of device concept forever battery.
You may end up charged and not charged.
I have a question. It's a little bit different than most people. So my point of reference on quantum is I teach and study something called a quantum energy blueprint, which applies to a person. And I'm just curious, my point of reference is quantum as it applies to energetics and frequency. And I mean, I realize this is quantum computing that we're talking about, which is not my field, but I'm just curious how much of that do you have any idea what I'm talking about? Like when I say, like, we're quantum beings and then we have a quantum energy blueprint, each of us, that's kind of a configuration that explains who we are, why we're here, and all that. I mean, it's a way of looking at the world through an energetic lens, and I don't ever hear quantum tech people talking about this, and maybe it's the same word and it's just two completely different meanings, but I'm curious if, you guys are experts in quantum computing, if what I'm saying makes any sense to you. Like, do you you talk about energy and frequency and that type of thing in your work, or is this?
We do talk about energy and frequency, but
Okay.
it seems like it may be a separate thing.
Completely different. Okay, cool. Well, there is such a thing as a quantum energy blueprint that we all have. It's a way of knowing yourself, loving yourself, and practicing self-care that helps you live in alignment. And it's pretty amazing. And the only reason I'm bringing it up is because I've heard so many questions about other people asking what are the possibilities here, what are the applications, and I realize it's out of the scope of what you're directly talking about, but just as a point of bringing it into awareness, it's really fascinating, and I think it's one of those emerging aspects of quantum that is underutilized. So.
Sure.
Thanks, Brian.
Yeah.
So I'm an experimental physicist, and this is really interesting to me. I also watch what's going on in foreign R&D on quantum information systems. How much what's the competition for talent look like from the other foreign interests that are working on quantum?
So, sorry, I'm not sure I understood the question exactly.
Okay.
So how is the competition looking between?
So, yeah, you've got talent out there. Foreign entities are working on quantum development, trusted networks, things like that. What is the competition for that talent between you and those foreign developers look like?
Yeah, well, first of all, I think a lot of people like to frame quantum computing as a huge competition because it sells stories and it sounds really good and it's, hypey and appealing. I don't like to view it like that as much as possible. I like to view it as a collaboration between the best minds that we have on the planet to develop this new technology. So, obviously there is competition for talent in every aspect across the board, but to me and, to IBM and I think a lot of these other companies, I think we're all of the viewpoint of the more people who are learning about this technology and the more people who know how to apply it, the better, period.
Ideas in this field and a lot of related fields, they tend to diffuse out very quickly. Again, I'll use machine learning as an example, right? Like the field is successful largely because when people have developed a better way of doing things, they share it with the world. And even if they didn't, it would rapidly make its way out into the world anyways. I don't know if it's necessarily true about some of the specific hardware designs, for example, but for more of the fundamental principles, applications, general ways of thinking and doing things, I agree with Olivia. It's more of a collaborative mindset.
Thank you.
So we have, and I apologize, I came in late, so you may have already talked to this. We have 4.1 million open cybersecurity positions. We've got how many hundreds of thousands open AI positions. So are you guys competing against that same pool, or are they the same people that become the quantum talent?
I don't think we're necessarily competing for the same pool, just because, in my view, the current state of affairs is we're trying to pull basically PhDs who are coming straight out of these quantum programs, and that's not to say that that is the ideal case, because we certainly want to expand that pool to other talent pools, but I think we're still at the phase where we're developing the infrastructure to really tap into that time, train people from other fields into the quantum field.
So you think it's a cannibalism of the chipset manufacturer talents? Like, where is this pool coming from? If it's a finite pool, and hopefully we start investing in science and tech education in this country, but assuming it's a finite number of students who want to go into these fields, like, where else are you pulling from if it's not cyber and AI?
So when I first joined industry 3 years ago, it was essentially the same, something like 10 research groups coming out of academia, where all of their students would go to the various quantum companies at that point. And the field was much smaller than at least in industry. But I would say at this point, people are starting to pull from just more general physics backgrounds, but and also computer science. I'm not sure if I know. Maybe there's a few examples of people getting pulled from the AI.
Yeah, I don't really think it's pulling from the AI community too much. I mean, I know my story isn't super different than a lot of other people's. Like, I majored in astronomy as well as physics. I plan to be an astrophysicist. And then I went on an observing run, and I was like, that's not for me. Nothing against astronomers, I just didn't have fun. So, I mean, in that way, quantum mechanics kind of pulled me out of my desired astrophysics path, and I wouldn't be surprised if that happens to a lot of other, you know, subjects in physics as well.
Very cool.
How do you see the distribution of talent in the US versus in other countries? And are you pulling from the international pool of talent? And do you find also, because there are these pushes to do, you know, export control and you know, there are rumors, and does that influence how you gather your talent?
Well, IBM is a global company. I mean, I can speak for IBM. You know, we have a huge presence in Europe, in Zurich specifically. We also have a large group in Asia. So we pull talent, not just back to, you know, IBM in Yorktown Heights, but IBM pulls talent from all over the globe to work wherever they're working. In terms of export control, you know, I think it could make our lives harder in the future. There's no other way around that, but you know, I understand why.
It's going to.
Yeah.
Well, I mean, a counterpoint on that is that a number of years ago, the U.S. government put export controls on cryptographic schemes. Right? You could not export cryptography that was strong. And what that really meant was just you export the same algorithm, but you just say, please don't use this flag or something like that. Like to some point, the ideas are not really amenable to being controlled in that way, but yeah, the risks are uncertain.
Yes. That's still not going to make your life easier as when they come back after you with export controls. I don't disagree with you, but there's a certain level of fear, which is getting worse every day, about what all this is going to be, and so I think that's going to be something we're going to have to live with.
Yeah, it's another piece of the puzzle. I mean, quantum computing is already hard, and this is just something that's going to make it harder. But you know, we'll overcome it. Like we overcome all the other things. I guess.
Is this field becoming more interdisciplinary, similar to how semiconductors did decades ago? Like, get chemists studying quantum physics and et cetera, et cetera?
Yeah, definitely. I think my time at IBM, the last year I started working with a lot of like quantum chemists, and you know, who had no background in quantum computing, but you know, pivoted into the field because you know there are a lot of interesting applications. So I do think it's becoming more disciplinary.
And I think it's part of a bigger push for, you know, computing and the things that are powering computing, the things that computing can enable. It's a larger trend of interdisciplinary work being done.
For sure, and I think, you know, this wasn't my original thought, but I think it might be even like Carl Sagan pointed out, you know, our entire population has become more and more reliant on technology, and fewer people understand that technology. So when we say interdisciplinary, I mean literally everything. I don't just mean like engineers and biochemists and, you know, computer scientists. I think the more people who learn about technology from any background, from like humanities, you know, they have a perspective, philosophy, ethics. They all have a perspective that could, I think, contribute to the development of the technology in some way.
Yeah, I'll give you an example. I'm a national security professional. I did 30 years in the Army. What did I know about quantum 2 years ago when I walked out of Army Computer Command? I could spell it. That's about it. But there's a like in our company at IBM, there's a badge program that's very easy and you know, easy enough for an Army colonel to learn this stuff. They go in and you learn about superposition and entanglement. You learn who to go call when you have big conferences, right? But it's literally that part where it's interdisciplinary from a set of understanding, right? Who should be your front man or woman on these things, and then who should have the understanding so they can talk to the environment, right, and the ecosystems that you're involved in. It's really powerful.
Thanks, Brian. Your comment on your roadmaps could be hours-long discussion just in itself, and I think it'd be very fascinating. I've read some work on Australians doing silicon-based quantum development and ion traps, and everything else seems to be in cryostats. as you're developing your talent workforce and looking down your roadmap, do you have the ability to pivot if one or the other becomes the mainstream effort?
I think the answer is yes. Speaking from my own experience, like my background PhD was in semiconductors. I was working on individual spins in silicon, but going to IBM, which obviously they were kind of superconducting systems. It's a different technology, but like a lot of the concepts translate, and a lot of the control methods also translate. So I think if there is a clear winner down the line, I think that field would be happy to pick up like all the other topics.
Yeah, I mean, I think IBM is obviously, we're all in on Transmon superconductors as our platform of choice, but I think I would be amiss if I didn't mention, we've made Qiskit, which is our computer language that we interface with all the quantum computers, adaptable to other systems as well. So you can use Qiskit to program the ion trap computers at IonQ if you so choose. And this is part of, our strategy and our belief that we want to make it as adaptable as possible. So yeah, we have the opportunity to pivot if need be.
There's a constant balance that you have to strike between picking the right, terms, words, programming languages, constructs that can be shared across a variety of different technologies so you can be as agile as possible, while also making sure that each one actually works and actually is efficient and can be mapped efficiently to each particular choice of hardware. This is really a delicate dance that nobody has managed to perfect yet.
And it's also not necessarily like a zero-sum game. So we could find in the future that some hardware is really good for some application, and this hardware is really good for this application. Like, it's not necessarily that one hardware will be like the champion.
To rule them all.
Yeah, one hardware to rule them all. Probably not the case. I don't know.
Actually, we've already seen that.
Yeah.
Okay.
We've seen companies like D-Wave that switch from annealing over to trapped ion phosphate, I think, Barry.
Just a question on, moving along the education route and getting people kind of tuned up from multidisciplinary fields. Where are we heading in terms of standards? Are there any emerging talks about standardizing various aspects of quantum technologies, quantum computing?
If I could, the Quantum Economic Development Consortium has a whole effort on the standardization. And Joe, you want to say anything about that? Do you remember from?
No, I don't know those people anymore.
Okay. Check with Celia Mosbacher and the Quantum Economic Development Consortium. They definitely have some efforts in driving towards standardization.
So in terms of like software, there's of course a bunch of different hardware platforms, and then there's a lot of different software plans. But what a lot of people are thinking about currently is kind of these intermediate representation. So there's something called the QIR, the Quantum Intermediate Representation Coalition. I think it was founded out of people from Microsoft, but it's a bunch of very smart people from various parts of the field who are thinking about like what's a unifying intermediate representation, so that that's basically agnostic to the hardware that you're actually running on. So in that sense, at that level of hardware, there are standardization efforts going on.
One more question before we wrap up. What do you guys think of Rick and Morty? Well, that completes our quantum talent panel. Thanks so much for all of your interaction with us. Join me in a round of applause for so another 15-minute break, and we're going to come back for quantum technology. Thanks again.
I just saw it now.
When we walk back I was trying to get so I was on there, I was in the U.S. government AWS popped up in the very operating
Somebody else I saw had to all the
Eventually it'll all start.
We only can I'm sure users will demand.
Well, you know, when somebody starts terraforming Mars,
Right, we're waiting for the series.
Obviously, that's right. So I'm in the next
I'm a co-founder of Capital Factory. I'm a co-founder of this place, Capital Factory. So it was our team. They do a lot of work, so I sit down and sit and learn.
So, did you have any trouble going out on some of their companies?
More demand than we've had for tables, for sure. We probably could have sold another 30 or 40 tables, but there's a limit to it. There must be, I don't know exactly what it is, the first gives to our portfolio companies that are in the Capital Factory portfolio. We have an investment and have equity in the company. The next level would be companies that they're not in our portfolio, but they work for Capital Factory. And we just put it out there. I honestly don't know what the criteria is. They need to be tech companies. Tech. Flower shop, somebody that's a marketing consultant, but I honestly, I've never had this is the largest one ever. Yeah, for sure. Last night, last night's kind of like it's on the south side. That's only been the case for about the last 5 years. Before that, it was our own kind of private on the side. We had to go on a Thursday, so we'll go on Thursday night. Josh and I were there was a Capital Factory that did some summer food on Accelerate summer. So there were about 20 researchers who were that's why the first but Josh Bear and I he was part of the Capital usually they're the idea developers they get access to our mentors, they get a product from markets, they pay customers, they become eligible, they consider to join our partner fund, they give us 1% equity, we don't invest at that point, it's just advisor equity, we have our investor relations team, relationship with more than 1,000 investors around the country, matchmaker, they gain access to our education partners, the only introduction we make to our corporate partners are portfolio companies, and then we are very interested about getting investment partners out of
How was the trip?
I was just checking earlier today. Yeah. don't know about North Dakota. I know we keep a log of all of that. Our various corporate partners, some of them want to actively engage licensing technology. Other corporate partners, to be honest with you, are less want to actually engage with the startup. They want to see the startup. They want to know what the experiences are, whether they find the startup actively. Some of our corporate partners is actually as important for them branding and sponsor activities that people see as an innovative brand. So it's like this. The report card varies. Based on some activities, branding, visibility, and activity.
This has got to be way out
Very strange. I left this one a long time ago, so that's not super surprising.
You have access to all of them. So you have access to every month we run an event called First Look. It's about a dozen to 15 companies most recently brought into the portfolio. We showcase each of them. It's the first Thursday every month. And you are invited to be a part of that, every single one of them. We put together an online forecast for each one of those meetings. You have access to it. Mary. She's their technology lead, the partners with Jeff. Yes. You need to talk with Mary.
All right, everybody, thank you very much for joining us. This discussion on quantum technology. So it's an amazing panel. Just so you know what the schedule looks like, we're going to start here right now, and we're going to go to about 4:15, and there'll be about a 15-minute break before the last panel of the day. So what we'd like to do is start with having each of our wonderful panelists introduce themselves. And I'll start with you.
Sure. I'm Bob Sutork. I'm the VP for Corporate Development at Cole Quantum since last Tuesday. Before that, I spent 5 or 6 years under executive leadership in the IBM Quantum program, a few decades before that. I want to just follow up on the plug since you brought your book with you. I'm the author of Dancing with Qubits, which is an introduction to quantum computing, and Dancing with Python, which is an introduction to computing, both classic and sorry. It's great.
I'm Antía Lamas-Linares. I'm a principal research scientist at AWS in the quantum organization. And my background, as many of the panelists here, is in physics, experimental physics, specifically quantum optics. So I did my PhD already a very long time ago, already making entanglement sources. So I've been on this path for a fairly long time. And at AWS, I lead some of the areas that are not directly quantum computing, but adjacent. So, say more quantum technologies in general, communications, networking, and so on.
Hi everybody, my name is Michael Brett. I'm a principal specialist for quantum computing at AWS, so I work very closely with Antía, but I focus more on the computing side of things. So anything to do with computing at AWS just go to me. Anything to do with other technologies goes to Antía, so we'll route the questions today accordingly. My background is originally in aerospace engineering and did a lot of high performance compute. And so I still have a great fondness for that, but moved into quantum computing about 10 years ago. Started a startup company called QBranch. We were acquired by a company called Rigetti that makes quantum computing hardware, and then I moved to AWS about 18 months ago.
And I didn't introduce myself because I know literally half of you, and this is like the fourth quantum panel today. But I'm Willie, CEO of StrangeWorks. Let's jump right into it. So, first of all, breaking down quantum technologies can be done in kind of three areas, right? Computing, you have the sense of kind of communications. Maybe we could start with some quantum internet and a little overview of communications from you, and then Bob, go to you for the sense of impact for computing.
Sure. Yeah. So we've heard about quantum computing a lot, which is natural. That's where a lot of the excitement is, and where some of the really big companies are investing in. But even before people had developed Shor's algorithm and these fun things, there was an emerging field called quantum cryptography, which we now more properly call quantum key distribution. And the idea there is that you're making use of qubits, of quantum states, but not stationary. They're not interacting with each other. They go from A to B, and you can do useful things. So it's quantum communication. And the original ideas around this were to essentially use properties of quantum mechanical systems like cloning and superposition and so on, the same kind of things that you get in quantum computing, but for the purposes of sharing a secret key. And not just a secret in some arbitrary sense, but rigorously proven secret, so informationally secure secret. And it turns out that people care a lot about that, because encrypting information is really important. So there's a whole field. It's a lot simpler than quantum computing in the sense that you really don't need these very complex systems interacting with each other. It's technologically easier. So there are companies already doing these things. And the technology interestingly feeds off quantum computing, because the more likely it is that we have a quantum computer able to break current encryption systems by Shor's algorithm, for example, the more relevant it is to have other alternative encryption systems. So that's one aspect. It's the oldest, better known. More generally, what we call quantum networking and the quantum internet maps to what we have in the classical world. We have computers that are individually interesting, but nowhere near as interesting as they become when you network them together and you get everything hooked up. So quantum networking does that. It eventually joins quantum computers together. It does this secure communications. It can join systems of quantum sensors. Sensing is yet a different field. So it's I would say a very, very interesting field that is likely to produce marketable, or is already producing marketable technologies, probably ahead of what we get in quantum computing.
And that's a great segue to Bob. I know your new company does a lot with quantum sensing. Maybe you can tell us a little bit about quantum sensing in that area of technology.
Sure. And let me say in some sense, quantum is quantum is quantum. Certainly if you look at the news over the last few years, quantum computing has gotten most of it. I'm a little guilty. I'm sorry.
And yeah, I was going to say, don't just call me out.
Right. And of course, it's a little bit easier to describe in the sense of really hard problems and so forth and so forth. But many of these quantum technologies go way back. I mean, quantum information theory, the phrase was coined in 1970. If you've ever had an MRI, right, you have a knee injury or something like that, that technology goes back to the 1940s. That's an example of quantum sensing, in particular quantum imaging. So you're using quantum to get a much higher resolution view of something. So it could be imaging, it could be detecting acceleration, it could be detecting gravity for a variety of applications. There are, in fact, cold quantum devices on the International Space Station right now using cold atom technology. They do tend to be a little bit simpler, again, than quantum computing, because you don't always necessarily need entanglement as But you need enough qubits to do what you need to do, and you need to do it in a small enough footprint. You can't afford a room-sized quantum computer, or even a 2-foot by 2-foot quantum computer or quantum device. So, like many other parts of hardware, what is happening right now is the miniaturization of all these different technologies. So my view is, of course, while quantum computing will continue to be extremely important, what you'll see is much more pervasive use of quantum sensors in ways that we haven't imagined. So just as now you look out and you say, well, how many classical processors are there? Oh, well, there's an Xbox, there's 8. There's my car, there's 47, right? And then you walk around like this. You're going to see these quantum sensing devices, sure, show up in healthcare, right? But I think also start showing up at the edge in different ways. You can do them as quantum RF antennas, much, much smaller than traditional. So quantum communications across a broader spectrum, that then becomes interesting in lots of ways. And oh, by the way, as a segue to you, is I already have all this great data in a quantum form from sensors, and I use your quantum communication. What can you do with it if I hand it to you to quantum computer?
Yeah, what I heard was much simpler, so now tell us about the complex.
The really complex stuff. Yeah. So I love Bob's description that quantum is quantum is quantum. There's at the fundamental level across all these 3 technologies, it's a different kind of physics that's going on. So it's quantum physics, not classical physics. And with a different kind of physics, it means a different kind of math. Different kind of math means a different kind of algorithm. And a different kind of algorithm means we can solve problems in a completely different way to classical computers. And that's what's so exciting about quantum computing. We've got a new tool in the toolbox, a different kind of computer. It's not just a faster computer, it's not just more horsepower, it's a completely different set of algorithms solved in a different way. And so what we're doing is trying to piece together these early stage quantum computers and to learn from them so that we can then inform the next quantum computers that we build the next generation. And at AWS, we're building quantum computing hardware. So we've got efforts underway to build our own hardware, but we're also working with a range of other companies that are building quantum devices of some kind. So D-Wave building quantum annealers, IonQ and Rigetti building gate model quantum computers. We'll be launching a new system from a company called QEra, based out of Boston, that's a particular type of approach for doing analog Hamiltonian simulation, so a different kind of set of algorithms again. And we've created at AWS a unified platform to engage with all of these different quantum devices, all of these different kinds of computers. So we've got the service in the cloud. Anyone can use it anywhere in the world. It's just like any other cloud service at AWS, so it's just another form of compute to us. We've got CPUs and GPUs and other specialty processors, and now quantum computers available there. And so a developer who's working in machine learning or computer science can access these devices and start to learn for themselves and experiment and explore on different kinds of quantum computers and understand why it is so different, what the impact of that is. And hopefully we all learn together so that we can build better systems, we can network them together, do sensing together, and then pave the way so that we can get to a commercial quantum advantage as quickly as we can and start to extract some value from all of this.
That's awesome. And earlier in some of the panels, the encryption thing comes up. We're happy to handle any questions on that, but I'm going to skip those questions because one of the things I'd like to know that's similar is when we're talking about the quantum internet, what are the benefits to me as a user, as a quantum internet versus the classical field internet that we have now? What are the advantages and disadvantages of that technology? And then, where do you see that in this development timeline?
So it depends, right? There are lots of things that one can do with the quantum internet. So one of them, the obvious one, is the encryption. Increasing the security of the network is something that doesn't get a lot of visibility. None of us, nobody cares about security unless it fails, right? So it's a hard technology to sell. But in terms of positive things, you can do things. So people have shown that you can do, for example, blind quantum computation. So you can submit a program to a quantum computer where that plenty of people are, or you want to avoid having to, maybe it's a question about having to audit things, like I just don't want to have to audit something like AWS. Just want to take that out of the equation. It would be great to have a system that can be proved to be perfectly private. So that would be one example.
If I could just follow on. So going back to your initial statement, which is connecting quantum devices. So here we might even look at a quantum intranet. Let's not go out to the whole world. It's just you imagine you have a bunch of quantum devices and you need them to talk to each other. Well, the basic problem is you can't just use classical channels to do that. You're exchanging quantum information with their states. One of the ways we're going to hit this, long before standardization or anything else, is, when you're making quantum computers, and let's think of the quantum processing units, people aren't going to be able to make them so big, right? So whether it's a few dozen, a few hundred, a few thousand, a few tens of thousands, you're going to hit this maximum. And as we saw earlier today, you're going to need tens of thousands of physical qubits to do really interesting things. So we're going to have to break through this barrier of the size of an individual QPU and do this type of quantum communication switching. So as you talk to your providers of quantum computers, ask when they'll hit that QPU boundary.
It's really important. And Michael, speaking of QPUs, can I maybe you tell us about the relationship between the classical and quantum that you as moderator on, but you barely touched on that. But I know AWS is doing a lot of work to take their massive classical infrastructure and make it available to people using quantum computing as well. Maybe give us some insights on the relationships.
So the way that AWS thinks about the role of quantum computing in a business context is it's part of the high performance computing offering. So I don't work for the quantum computing team, I work for the high performance compute customer team. And so our job is to deliver the function of high performance compute using all of the technologies of AWS. So it's bringing together the CPUs and the GPUs and the specialty processors, but also high performance storage, high performance networking, all of the tools that deliver an outcome that feels like high performance to that customer. And so quantum computing is one more tool in that toolbox. It's one more processor in the portfolio that we can deliver high performance compute with. So a lot of the internal engineering effort in quantum for AWS right now is how do we optimize the hybrid interaction between quantum and classical. When you're running a quantum computing enabled workload for whatever it is, let's say it's a logistics problem, a lot of that processing is happening on a classical system. It's happening on AWS servers that are completely classical. And then we're sending some algorithms to the quantum computers, and then looping back through, processing loop, or back to the quantum computer. And so that loop that we go through, quantum classical hybrid loop, it's not sending quantum information with NTIA, it's sending some classical and some quantum information and some quantum and some classical information back through both systems. And so we need to figure out how we optimize that loop to get the delivery of a high performance outcome from that. So that's, it's challenging to build a quantum computer. It's also challenging to integrate a quantum computer into that high performance outcome.
So I'd like to, we've talked about quantum communication simpler. How much is the transduction problem to come from a particular kind of computer, let's say a superconducting qubit, which is generating microwaves, and then maybe you want to get it into an optical fiber, or maybe you want to send it with microwaves that you're coming from, do you have the transduction problem of keeping the quantumness of the information that you're sending from one kind of quantum computer over a different kind of communication channel?
Yeah, absolutely, and it depends. So absolutely, if you need to go inside these dilution fridges where you keep your, say, if it's a superconducting quantum computer, unless those things understand microwaves, RF signals. If your quantum computers are reasonably far away, the only reasonable qubit is really a photon, a light. So for the same reason that we have optical communications in the classical world, we use photons.
So where are we with that technology transduction?
So it exists, and it's actually a very active area of research. And you have to maintain, again, the trick here is that you cannot measure anything in between. It has to go directly from one to the other. It needs to maintain all of that superposition, the whole coherence of it. The problem, so systems to transduct into between these qubits exist, they tend to run into troubles of efficiency, right? It's like how well, what is the success? And a little bit of an error, So it's an active area. Now, having said that, it also depends on what kind of quantum computer, because some of the quantum computers out there, if they're optically based, then they're naturally matched to some of these things. That's not the case for microwave, sorry, for superconducting computers. But it really depends. Then again, superconductors, if the fridges are really close together, you can do direct microwave. So there are all sorts of questions depending on the platform.
And that's a great segue. There's a lot of different ways to build a quantum computer. So if we look out 5 or 10 years from now, we've got the prime traps and the photonics superconducting. What do you see this looking like 5, 10 years in the future? Do you think we have fewer options? Do you think we can start consolidating around things, that annealing disappears or not, or whatever the case may be? Or do you think we have even more techniques we use to build these machines? Kick that off with you.
I think annealing has always been on the side, to be honest. So there's universal quantum computers, and then there's AM. They use that word quantum, and that's fine. But there's also classical simulated annealing, and you go to companies like Fujitsu and FPGA approaches and things like this. It's all annealing. And as we saw earlier today, it's are they really that much faster? And we're not talking about linearly faster, twice as fast. We're talking about some of these types of quantum advantages that would be quadratic, or we might even go exponential. I certainly don't see one winner, because there's not going to be one type of application. And the press, of course, many great articles, but they love to say, who will be the winner? And sometimes if you only have one technology, that's going to be the winner. I suspect it will boil down to about 3 or 4, over the next decade. I think some of the ones that we've seen might fall off. Even if we look at some of what are people using today, ion traps go back 20 years. NMR goes back 20 years. Photonic goes back 20 years. Even superconducting goes back 15 years. So people keep trying them, and they keep seeing the applications. You might ask yourself, well, if I'm going to have a large computer in a data center where space is not an issue, well, okay, that's going to change it, right? And energy's not an issue. If I'm going to start distributing small quantum computers at the edge, well, that's a completely different thing. So cold atoms, in particular, I think have a lot of potential for this type of scaling, and scaling broadly across different types of quantum applications. So we're a long way, I think, from seeing this. And I'll also go 50 years when I'm not around. Boy, there will be some amazing quantum we don't even know about yet. Right?
Well, Michael, you were talking about the high performance computer and quantum. In 5 years, am I going to see more types of architectures, or do you think that there's some consolidation, and I'll be able to buy fewer of those through the AWS platform?
So if you go to your AWS console today and go to the drop-down list and select a classical computer from that list to do any workload you like, there's about 30 options of classical computers from AWS. And some of them are memory optimized, speed optimized, cost optimized, networking optimized. There's a ton of different classical systems that we've got. And here we are 70 or so years into a computer revolution on classical technology, and we got a ton of classical computers available. It's getting broader and broader. So now there's specialist devices for machine learning and for speech recognition, and your own phone in your pocket's probably got 6 or 7 different kinds of processing in their classical technology. The same is going to be true for quantum. We're going to have different processors optimized for different applications and different workloads, some from the same company. So your Rigetti system that's optimized for one application and one kind of workload, and then there'll be a different kind of Rigetti system for that workload. So
yeah, but those are all CMOS.
No, there's FPGAs and ASICs
still
and different applications there that
no, I don't disagree that they're very different computers.
Yeah.
But it's architecture. It's the same manufacturing process.
But not when you get to let's say cold atoms.
No, that's yeah.
Right.
That's different.
But I think the different properties will enable different kinds of applications to come through there.
And I saw that I think it was you who kept raising your hand. I didn't mean to.
It's fine,
You're right blocked
yeah,
you. If you want to kick your question out, feel free.
Well, it's a little thick. And I consider myself a bright guy, and this is well above my pay grade here. So I work in the space of national security, particularly around how do we secure the energy sector. And I have this theory that says we're combining cybersecurity, artificial intelligence, and quantum computing. And that's our holy grail. And if we can do that, we can build private clouds for the energy sector off of different technology. How many decades, how many years, before that can, anything close to that can be a reality in your world?
Big question. I mean,
Because I have no idea.
From my personal view, I don't think I'm overly optimistic. I think that comes sooner. I don't think it's decades and decades away.
You think it's 7 years? Are we in the fun cycle?
Without going into customers that we're working with,
right.
We work in the energy space. There are already customers using quantum sensing and doing things that are a little outside of cybersecurity, but they're oil reservoir management, things like this, that are all part of that, securing those resources. So they already have the sensors and they're playing around with the quantum computers. The one that NVIDIA Grokkey is using quantum machine learning. So not quite AI, but to kind of come through there. And so I could see work being done on that, now until whenever. When does it become something that's ubiquitous or standardized or whatever? That could still be 5 or 10 years away. I don't know.
Also the next panel specifically is going to address government and security.
Okay.
Yeah.
Yeah. But also, I'll give you an example. For example, the Department of Energy is very worried about securing the grid.
Mm-hmm.
Part of securing the grid is making sure that the grid has good timing information. So synchronizing the grid is a huge deal. If your grid gets out of sync, then bad things happen.
Right.
And a lot of it's true of the electrical grid, but it's also true of a lot of other infrastructure elements out there. And there is a huge reliance right now on GPS. And GPS is notoriously it's spoofable, and it's not it wasn't designed to be, when they came up with GPS, nobody thought about how reliant civil infrastructure would become on it. So there are, one of the areas in which quantum sensing and quantum networks too have a great influence right now, and there is stuff being deployed, is in helping with that tiny infrastructure. So both in having just small clocks that can preserve time, even if they get disconnected from the grid and not lose that synchronization, but also in doing time transfer. So it sounds ridiculous, but if you need 2 remote clocks to agree on what time it is, it's actually a hard problem, and we're hugely reliant on GPS for that. And there are techniques from quantum communication and so on that allow you to do that time transfer in a secure, resilient way. So very related to quantum distribution.
How many of you, other than those of you who work for Cold Quantum, related clocks and quantum before you came in here?
I've heard it before. That's
okay. Huge application. It's just going to get bigger. So high-speed trading network. Anytime the word network comes into this, you're going to be looking at better and better clocks that will become more organized.
And so we're talking about these 3 different technology areas. What are the barriers to these? What are the barriers and the milestones and things? We talked about computing earlier, so we're kind of into that. But Bob, maybe tell us about the sensors. Where are we actually at? Sensing's $150 billion market a year, right? And so clearly there's a big opportunity there. Where are we at the evolution of those sensors towards the internet?
I think somebody mentioned scale in 2 ways. So one in general with these quantum technologies, particularly quantum computers, it's just the sheer number of fully functional, fully connected qubits operating at very high quality. You cannot solve hard problems with little tiny quantum computers. You just can't. Okay. And that hype versus marketing, right? Things like this. But it goes to the quality issue, right? So how many qubits do you need? And we still call them qubits. I mean, this general 2-level quantum system, we might as well call them qubits, right? Whatever the application. The scale in that sense is how can we go down from a few feet by a few feet to a shoebox, or even smaller. right? Because if these devices are going to become more pervasive, eventually maybe even showing up in cars, right? The laser devices that show up in cars are much, much smaller than they used to be, and far, far cheaper. So it's going to be driving down the size, it's going to be driving down the cost of these. The nice thing with some of these approaches, plug and co-atoms, is that leveraging the same innovation coming from other fields like LiDAR, right? So borrow, right? Take this quantum technology that's being used elsewhere. It's not just the quantum physicists who get to play. It's everybody who are doing this. It's across industry.
So it's a $150 billion market in 10 years. How many of those sensors have migrated to being quantum sensors? Because I know they'd be very useful in things like semiconductor manufacturing and things, new MRIs, things like that. What do you think is in 10 years? Like, is it 20% of the market is now using quantum sensing, or?
I think more. In my second week here, I'm not going to make that prediction.
But I know you've written 2 books. I don't know. You might be able to. 2 weeks in for you could be like 3 years or something else.
I'm going to ask the same question to my colleague Laura Thomas the next.
Maybe we should refer this.
You guys talk, but I would just be guessing.
Yeah. And what about the quantum internet? Why do we have a quantum internet? Right now or in a year or two. Is this 30 years out? Is it 3?
No. So there are a few stages of the quantum internet, right? The first one is, can you get the quantum state from A to B, like state transfer A to B? We can do this. It's not that hard. You just send it around down an optical fiber or from a satellite. You can do that. The next thing is you want to distribute entanglement. So you want 2 things that are already entangled together, because then you want to entangle the ends. That we can do to some extent. They're good entanglement sources and can go pretty far. And then you want to have things like quantum repeaters that allow you to do sort of kind of extend your range and do sort of error correction on the way. And the first one I would say is ready. Like, we can do that now. There are companies that already commercialize these things. The second one is a little bit more complicated just because we have more challenges. And the third one is, a quantum repeater at the end of the day is almost like a small quantum computer, but it's a much smaller quantum computer. So, and then you have the transduction problem, which is how do we translate between the different qubit kinds? But we can already do the first sort of low-hanging fruit applications of quantum networks now. It's just that it requires new hardware, and there's that is hard. It's hard to do, because networking, when you do networking, you have a networking effect, right? It's more valuable the more nodes and the more things you have connected. So there's not a lot of value in connecting just 2 things, and it gets exponentially more valuable. But the technology is in principle there. It's ready.
Some applications or hardware being developed for telco will be leveraged back to quantum.
Yes.
Once again, here's a win. You have much broader, many more people working on the problem.
Well, Michael, when you think about it from the AWS perspective, right? You guys already have computers online. We're partners with you. We've been working with all of these hardware companies. What do you think the barriers are to us seeing, all of these different industries we talked about, energy, pharma, etc., using quantum computers every day? Like, is it more of a matter of the workforce? Is it more a matter of where the computers are? Maybe a little bit of multiple things. What's your thoughts on that?
So the key barrier is how quickly can we learn together? We are in a learning process about this new technology, and so it comes down to how quickly can we learn what the next generation of hardware needs to look like and iterate through that cycle. How quickly can the workforce learn how to use them? How quickly can we learn about the applications that are unique to quantum computing that can sit on top of that? And so that's why you see kind of larger and larger fundraising rounds from quantum hardware companies, because we're trying to learn as quickly as possible. And so if we parallelize a lot of the development efforts, can we produce 2 quantum systems at once and then be able to compare the differences between them? What if we had 10 different quantum systems and candidates that we could learn from and compare across that and then inform the next generation of development? So one of the things we say about our product at AWS, it's called called Bracket. That's the name of the quantum computing service. The whole purpose of Bracket today is to learn how to build a better bracket tomorrow. That's what it's for. That's its purpose right now. So we need all of you involved to help us learn what version 2 needs to look like in the future, whatever the hardware, software, and application mix is.
So my last question before we go to audience questions, when we look at quantum computing, the evolution of these technologies, this is gonna be my last one. I don't know if I want to commit to this question. No, I think this is a good one. This is one of my favorites, so I don't want to skew it. But I always think about where we are in the transition from applied research, from advanced research, right? There's all this science that's been going on in the labs, and we've talked about quantum computing since the 80s, the original, sensors and all these things. They've been around for a while. It's not like it came up in the last 36 months. Where do each of you think we are in the transition from advanced research, where we have physicists learning how these fundamental things work in nature, to the applied research where we have the engineers computers and making it more ubiquitous? Any one of you, whoever wants to get that on this on. Looks like my thought is ready to get them on.
Well, I see it as the balance, maybe not advanced versus applied, but I would do it as to what true science has to be developed versus what's engineering. And that will vary from approach to approach. Because
in the sensor area, what's that look like?
Well, so engineering, you say, okay, well, we can do certain things with lasers today. But in the future, you have to have much better control on certain things. Right? Maybe you're shifting to optical circuits, the transduction problem that you talked about. It's not just engineering. Right? So I would tend to say in this general area, roughly speaking, 25% science, 75% engineering. I would look at some of the other qubit technologies and say it's much closer to 50-50.
You wouldn't answer the other question earlier, but you just said 25-75.
That one is, because I'm not going to make up economic numbers. I've always been suspect of those.
What do you think? What do you think about that? What do you think about Bob's 25-75 mix?
I think it's highly dependent on what system you're talking about. Again, some systems in quantum communication, some systems, I would say it's almost 100% development. We just need to make it more reliable, smaller, integrate it with other things. If you go to the more advanced parts, the repeaters and transduction, it's 90% research still and 10%. Yes, we need to tweak this, but yeah, we're still trying to figure out what are good material platforms for repeaters and what is going to be the most advantageous in terms of then doing high efficiency transduction, low errors, and all of these things. So it's highly dependent, but some areas are there. Some areas it's almost, we're at the development stage.
So when AWS looked at what should our quantum computing strategy be, sort of like trying to decide whether to just buy some quantum computers and put them in the cloud, or do we go build our own, or do we just leave that aside for now and go do some fundamental research and just like advance the science? And in typical AWS style, we decided to do all three at once. So buy some, put them in the cloud so we can learn, build our own, and then do some fundamental research because there are really hard problems that need to be overcome to bring us to commercial fruition. There are some Nobel Prizes yet to be won or yet to be discovered before we get large-scale fault-tolerant quantum computers in the cloud. So to that end, one of the things that AWS has done is built a brand new research facility on campus at Caltech in Pasadena, where our fundamental science research group is underway. The reason we built that facility there is so that we could share faculty and resources with one of the leading institutions in the world for quantum physics. And this is no small investment from AWS. Even a company as big as ours doesn't build research facilities every day for particular technologies. This is a unique thing for even AWS to do this. It's a multi-decadal commitment to build out like these kind of centers to do this kind of work. So that gives you a sense of where we see the level of investment required. It has to be in this fundamental science and research activity as well.
That's perfect time. We have just about 20 minutes left, so I want to turn to the audience questions. unusually high amount of audience questions today, which has been great. So if you just want to raise your hand, I'll pick you out and address the panel. Nobody's hand was. Alright, that's better. Let's start with you.
So I do love the fact that you kicked off the Amazon answer of it depends. It kind of just fits into this. So there are a lot of companies that are emerging and starting to go into this. How do they begin to plug into and start working with groups like Bracket, like the advanced research teams, like Cool Quantum? How does a company that, or an entrepreneur that has an idea to grow this stuff, how do they get plugged in?
So on Bracket, our quantum computing service, depends what kind of service you're offering. So if you're building quantum computing hardware and you want to make that hardware available via AWS to the world, and we can help you aggregate that demand and distribute it as a compute service. We've got a couple of standards that you need to meet around security and accessibility and some SLAs there, and we can come up with a commercial agreement. So we've got 5 companies that we've done deals with, startup companies that have built quantum hardware that are now making it available to the world through Bracket. There will be more that get added to that over time. So if you in the audience are building quantum computing hardware today and you haven't talked to us about making that available, like let's have that conversation. So that's downstream of Bracket. Upstream of Bracket, companies like Strangeworks building on top of Bracket and building on top of AWS to then distribute that and find niche value centers in specific sectors that they can make quantum computing enabled workloads. And I kind of use that phrase that quantum computing is just one piece of the puzzle. If you look at the Strangeworks architecture diagram on top of AWS, it's a spaghetti and meatballs sort of diagram of about 20 different services that are interacting. Bracket is one of those services that enables some of what they do. So if you're a company that's looking at building out an offering to the world in whatever your domain is, then AWS can provide infrastructure, including quantum computing, to help do that.
So how would following on that, how would an entrepreneur that's interested in the quantum internet, like where would you even start with that? Because I don't know that I can.
There isn't such a clear answer for that question because there is no service, right? This is a different kind of activity in this case. So there isn't such a clear and structured answer to that. I think generally what happens is that you establish a conversation and see, because sort of dovetailing to what Michael was just saying, we have all of these things, right? And one of the issues often with startups that are developing a little slice of the technology is that slice is not enough to provide a useful thing, and you need a lot of other pieces to make that into a useful service or something that you can offer. And that's where a conversation with us with AWS can make a lot of sense.
So you're saying it depends?
Yes.
Well, what about, I'm super excited about the sensor market. I mean, so if we use them everywhere, right? How would I get started with that?
Well, so first of all, let's say that out the cloud.
Yeah.
Yeah. We call it AWS, or we call it the cloud with the various vendors and things like this. When IBM did put the Flat-Computer quantum computer on the cloud in 2016, it was ridiculously unique. Suddenly, everybody had a chance to do this, and right now, only 400,000 people have accessed it. Right? So there's the quantum talent and things like this. So your first expectation in any of this, whether it's how do I get to quantum computing, how do I get to these technologies, should be somebody should be offering a cloud-based service. QuantaCert does that, will do that for the ways that you expect. I think sensor work, how do people design brand new sensors? Do you ramp up all this infrastructure yourself, or do you do something on the cloud? Last year we had a system where actually you could design this across the cloud. And well, what happens then? Well, do you license the technology? Does somebody build it for you? Whatever, things like this. I also like university connections, because this is really critical at this time. We've spoken a lot about commercial, what companies do. A lot of this research is coming out of the very best universities in different. Quanta happens to work with Madison University, Wisconsin-Madison University, Colorado, others will follow. So you can do that. And of course, there's always bespoke work, right? If you have something in mind, you really want that sensor, right? Yeah. We can
Other audience questions? Yes, sir. Since you had one, we'll go a little bit around, but don't worry.
No problem, no problem.
I know you're my go-to if I don't get it. Yes, sir.
So, I wanted to, understand a little bit more about, the, quantum internet. I understand the value proposition is, anti-tamper and maybe distributed timing. What's interesting is if you, pass the entanglement, is there a possibility that you could do, either distributed processing or parallel processing once you do that in a different way? That, you know, to expand, you know, you have a limitation on qubits, but if you have this network, is there a way to, you know, make that happen?
Yeah, I mean, eventually if you are able, and there are a lot of concatenated ifs, right? You have your quantum computers that are not quite big enough to do what you want to do, and you're able to distribute entanglement between them and transduce it into the brain. So you get entanglement between quantum computers. Now you have a quantum supercomputer in the same, it really maps to the classical analog, but that information transfer between them has to be in this quantum form. It's no good if you make it into a classical bit and try to re-inject it, then you break the link between the computers. But if you're able to entangle the qubits inside the quantum the distant quantum computers, then yes, you have distributed computing. And there are all sorts of interesting sort of proof of principle ideas and things that you can do there. But that's even more complex than the, you know, we're still working a lot on the algorithms just for a single quantum computer.
You almost need like a network slicing to make that happen.
Yeah, and you need things like long coherence times and memories and.
That's nothing.
Yeah. So how would you possibly write an application that is smart enough to work across quantum devices on a network? I mean, you could hand tune it, you could go in and say, do this communication, things like this. So, you know, we're used to decades of optimizing classical compilers that do amazing things, right? We need optimizing quantum compilers, sometimes they call them transpilers, that will lay out the original circuit that you designed, right? Across whatever hardware you have as appropriate, and sometimes it's distributed or not. So there's a huge part of computer science that's going to rise up around quantum. Some technologies that we thought were dead, you know, in the sense that everyone knows how to do this, it's GCC or it's whatever, right? There are going to be massive areas of research specifically to make this hardware work.
Alright, so I'm gonna comment, first I said I was gonna heckle Antia, so I'm gonna heckle her on the quantum thing, because you didn't actually fully answer. You started earlier, but what can you do with a quantum link between computing elements? There are things you can do when you combine classical computing, you say, oh, I have a bigger word, or I have more space to operate in. But in a quantum domain, the amount of what's called the Hilbert space, which is what you compute into, actually grows exponentially larger as you increase the size. So you can scale a quantum computer much more quickly than you can a classical computer if you can do it correctly. But the other thing, which is actually, I believe, in my personal belief anyway, is even more interesting, is this whole concept of blind quantum computing. So blind quantum computing is a case where you can compute, as Antia said, you could send a program to a computer, and that computer can execute it, not even knowing what the program it is that it's executing. Not the data, but not the program itself. That's something you cannot do typically with a classical computer. But there's even yet one more thing that you absolutely can't do, which is this thing called guaranteed deletion. So when you go and you compute on a quantum computer, you can actually guarantee that the data, when it is done computing, is gone. It's not there anymore. And so you can guarantee that the data that you've asked somebody to compute on is no longer available to them. And that's very different than what we can say today about what people call homomorphic computing, which is where you encrypt your data, it's calculated on in its encrypted form, and you send back the results. But the problem is, because you can make a copy of that encrypted data, and if the key leaks later on, somebody can then figure out what it is you asked them to do. With quantum computing, you cannot do that. So that's something you cannot do. Anyway, sorry.
Yeah, that's a very good point.
Back in the back.
I'm doing the layman questions today. I have another one. Let's assume we can get these technological questions figured out around the transferability, et cetera. How much of the existing internet infrastructure is completely useless in a quantum world? That is to say, both of our mobile phones, of our home networks, of all of that, like how much of that has to be completely replaced because we have to do it via optics or some other microwaves, et cetera?
So surprisingly, the vast majority of it is usable. You have to do some tweaks. So we have fibers everywhere, right? And these are typically, I'll use the specialist wording, but it's a single mode fiber, which means that's the optical engineer's name for it. But for us quantum people, it means that it maintains coherence to a large extent. So that's fine. We can use existing laid out fibers. What we cannot do is we cannot transverse optical amplifiers anywhere. So if you have, normal optical communications goes through, laser down the fibers, and at some point the lasers get attenuated because the fibers absorb a little bit. Not a problem in classical communications. You just have an amplifier, you crank it back up, and you keep going in your merry way. You cannot do that with quantum information because it destroys the coherence. It's equivalent to making a copy. And we have something called the quantum non-cloning theorem that tells you that if you try, you're going to mess it up. So we have to find a way around those optical amplifiers. And the way to do it is you skip the optical amplifier and you have a quantum repeater that allows you to do that. But generally, so the optical fiber infrastructure works for us apart from the amplifiers. So that's one big part that is already there. The other part that works is, and that is a growing field right now, is optical communications from space, laser comms from satellites. Again, it's a free space channel. Photons are happy to go down there, and you can do quantum entanglement distribution from space. These things work. Now, things like the mobile phones, that is not probably won't work, and the reason is that is an RF frequency, and if you do that, it works inside a fridge, but there's a reason it has to be at millikelvin above absolute zero, and it's that otherwise it's just too noisy an environment. So we use RF in Texas, right? It's too hot for quantum information. So we don't think we can do quantum communication over RF applications.
But you might have a quantum sensor in that phone that is your RF antenna.
Yes, sir.
Great segue into my question, is besides the quantum repeaters, what are the other hard problems to solve within this whole field, and do some of the recent discoveries of macroscopic quantum, like the quantum tardigrade, have to, what are some of those things that might help you solve those hard problems?
Sorry guys, I was sure that wasn't gonna come up.
Okay.
We almost made it through the entire day.
I know the guys from the quantum tardigrade, and they already won an Ig Nobel Award 2 years ago. I don't know why they need to try for another one. So what are the hard problems to solve? I think the quantum repeaters are clear. Quantum memories of different types and transduction. I would say I have to say, so I'm not talking about quantum computing, but in the quantum communications internet area, those would be my three picks.
And quantum memory, and sometimes people call it keyword memory. One of the first things I usually say about quantum computing is they're not big data machines. I remember reading some article maybe 5 years ago saying, oh, humans create petabytes of data every day. Thank goodness we'll soon have quantum computers to sift through all of them. In many ways, we're still flipping zeros and ones, right? Which is called qubits, right? and things like this. So you have to say, well, when will we be able to handle inputs of a reasonable size where you're not blowing the coherence time by just setting the data? So this is why you eventually need quantum RAM and some sort of fast transcription teleportation, techniques to actually do these things. So So there are gonna be many things to get to really solving these big enough hard problems. So for all the use cases, I would say quantum computer promises to help solve. I try not to say will, but promises, but there's always a gotcha. And it's exactly these types of questions. But where is that roadblock on which approach?
So can you talk a little bit about the interface between classical and quantum? We live in a classical world. We're not quantum creatures outwardly.
Oh, you're absolutely fine. Do you have any atoms in your body?
Yeah, not that I can help. I don't.
No, but
I have none.
So, what was the question again?
The question is, talk about the classical and quantum interface. How do we, because we gotta go from, in some ways, to communicate information into the quantum world. Don't we have to transfer information back and forth? It's one of the key things we're working on at AWS.
Yeah, that's right. So I talked a little bit before about hybrid quantum classical interaction, like compute, and it's part of our high performance compute portfolio. When we program a quantum computer, though, it is relatively easy to do the programming. You know, the folks that build the compilers that take our abstracted code and then turn that into essentially the machine language equivalent, you know, that is extraordinarily difficult, but there are people building out those tools to do that work. So, you know, a lot of investment needs to go into that compiling work. But as a regular software engineer, regular computer scientist, programming a quantum computer, it is relatively easy to do the programming itself. The hard part, this is the hardest part in quantum computing, is not on the programming, it's on the whiteboard. Doing the math to take the foundational equations of quantum computing and turn them into the specific application that you've got for your workload or application. So it's that applied mathematics, some quantum physics that happens on the whiteboard before you touch the keyboard to do that work. And so if I could, you know, snap my fingers and get a bigger workforce in any part of our go-to-market strategy for AWS, it's a lot more people that can do that whiteboard math.
And also, for those of you who've done some coding, if you've ever done a statement like, let X equal Y. Nope, you mentioned no cloning, can't do that. Okay. Yeah. How about if so-and-so is true, then do this, else do that. Nope, can't do that in quantum. How about do this 10 times? Nope, can't do that in quantum. So the fundamental quantum programming model needs to be extended by the classical programming model, whether you call it hybrid or integrated. Those are the types of connections. So we're going to need very tight, very fast communication between classical container, let's say, and a quantum computer to do all these things, and ultimately to get the things like Airflow.
So with that, we're almost at time, so kind of final Jeopardy question, because everybody wants to know. So like, what, you know, when you're out trying to get your quantum startup funded, you get the question of, isn't this 50 years away, 20 years away, 5 years away? Not trying to make predictions, but I mean, I remember when we started, when we met in Tokyo for the first time in 2018, there's like 17 qubits, right? And now there's all kinds of different qubits. There's 5,000 here, 1,000 there, 100 there, 80 there. When you guys, irrespective of that, when do you think companies, which will be the first people, you know, probably trying to use it, what the, you know, the majority of, say, your Fortune 500 companies will be interfacing, interacting with some sort of quantum computing program, be it 3 or 4 people researching it or actually doing work. Michael, we'll start with you.
So I'll leave everyone with this thought. There are lots of technologies that can have a huge impact in the world. So not just quantum computing, but you know, all manner of investments to be made in emerging technologies that have a massive total addressable market we can go after. If you map out all of the emerging technologies and their potential total addressable market, and then compare that to the amount that's been invested to get a return on that total addressable market, quantum computing is underfunded compared to other emerging technologies for its total addressable market. The dollar of investment per total addressable market dollar is underfunded in quantum computing right now. So I think there's plenty of opportunity, hype aside.
Physicist, I don't know how to answer that.
You can literally just throw it to Bob if you want. Bob.
So when I talk about quantum advantage or business, so I'm talking full scale in production, part of your workflow. I'm not talking about experiment. right, on the side. By the end of the decade is what I would call this practical quantum advantage for some problems. Sensing, it's today. It's only going to get better. And communications, that's what
Well, I didn't ask that one.
No, but
that brings us to time. Actually, 20 seconds left for maybe a round of applause. For we'll have a 15-minute break, and the next session will be about 15 minutes right here. It'll be the final session.
Thank you. All right. Hope I didn't shoot myself too much on time. Have a little levity in there. I'm John. I've actually been at a conversation with NVIDIA and conversation with Rich I use physics wherever I I had a wonderful, turned into a friend of professor Stacks Dynamics who jumped up on one table and said, the reason why there's this moment visualize the ring and actually stretches the string until it's flat, and that's how you have to run it. That's why the normal force is always identically the same as force pressure is. And I love those I tried to know when I was in class.
Around the last section, really good.
Yeah, I am looking forward.
They keep saying get
Yeah, so let me give you a background. There's a book by Tom Long. I think it's like some chapters are
We are connected. So I'm gonna hang around while
yeah, everyone thinks the same. I feel like every single one of these is like, what is the best one?
So, do you like the quantum theory conference
I think it's extra funny because I'm not a theorist and I like to make fun of theorists.
Sure.
So for me, it's like, I know. So now I'm gonna be like, I heard this really funny joke. Next week, that's what you conference. I know. You're gonna beat me up at the party. What do you say?
Most theorists I know seem to take that in reasonable right side and go, okay, the ones that well, most of them understand limitations.
Otherwise, you're not really doing this. It's
I've been proselytizing for this It goes back to Pythagoras, Plato, Socrates, Aristotle, Maxwell, Faraday, and that's as far as I made that point. Really,
should I suggest it in my book, or is it not at the...
No, it's actually amazing. This guy thinks it's amazing. There's a few times I had to think a little bit about what he was talking about. So, for instance, I learned all sorts of stuff about Pythagoras, like I said, and he was known for his philosophy. He also became the first guy to figure out why certain by using weights to make different places he figured out, that there are integer offsets in the length of the frequency. And also he was believed in the immortal soul and was a vegetarian that still said, "Thou shalt not eat because demons have souls."
Well, you can't expect me to be right about everything. He did so much, you know. We'll give him a pass.
No, but they're doing really good. And he starts talking about, there's an historical and he is deciding to real from the legend. Because the historical that's a pretty good that's a pretty good guess. No, but I found it I suspect that you too. Check it out. My guess is you'll like it in the right way. That's my guess. That's it. Me and organic, yeah, but I'm saying, there's just right. Yeah, I can watch your cartoon.
So what we do.
Company called Animatrix, they're a small photonics company. Talking about what it is we're actually doing, but we're in the
I'm going to catch everyone.
What kind of industry is your company?
I've been in the cybersecurity business for 25 plus years.
Alright, so I'm going to send you an email. So we can
Yes, sir.
Ready, Joe? All right, got everybody ready? All right, first to help out our panelists a little bit, let's just sort of do a little, see who's here, okay, if y'all don't mind that part of it. So how many are here from the academic side of the house? I got a good one there. All right, three. All right, the academic side out. Let's go large businesses, the medium-sized industry. You can get a feel for it. Okay, okay. Small businesses or startups. Oh, okay. Oh, good. Investors or capital ventures. Okay, you got to hold up your fort. Oh, two there. Okay. And what did I leave out?
College student. Bigs.
Oh, policy. No, well, you're academic.
College student.
I'm sorry, what is that?
Government.
Oh, shoot. Yeah. The government. Yeah, how many here for the government? Well, thanks everybody. It's good to see everybody. You know, it's interesting comment when we started. I know some were, and I am pleased too by the amount of folks that are here for this topic area. But for some of us to have a discussion on this topic and then to see sunlight at the same time, that's something new too. Okay? Some of y'all know what I mean by that. All right. So let's go. My name is Bobby Blunt from the MITRE Corporation. So fortunate to be the moderator. I will tell you, the panelists that we have here are, I would like extremely knowledgeable. Some of you know who some of them are, but just even their background and their history in this particular space we're going to talk about, as well as the areas. So really leverage that opportunity. We'll start out, I'll have two questions I really want to get in because I think it'll set the framework. We have some others if needed. So really get into the opportunity to leverage what we're going to talk about here. Our primary focus or mission that we really want to get across is really talking about how quantum can be beneficial to the government and for those doing business with the government or supporting the government. Okay? So really important that part of it. I think by reaching out to this the group we have here is going to help that out. So we're going to start out, first we ask the panelists to introduce themselves. And for those, remember the book Start With Why? Yeah. Okay. Our panelists also give a little bit of why they're in this space. I think that'll really set the background for us. So, Lauren, you want to say?
All right. So good afternoon. I'm Lauren Rogers. I'm with Defense Innovation Unit. I'm an Air Force engineering Defense Innovation Unit in the space portfolio. For those of you not aware of Defense Innovation and what we do, we're an organization that's under the Secretary of Defense, Research and Engineering. We were stood up in 2015, and our mission is really to take commercial technology, bring it into the Department of Defense quickly. That's one of our key points, quickly, and modernize the defense, or the Department of Defense, increase their capability, increase their capacity, and really develop the national security innovation base.
And your why? Why are you?
Sorry, thank you. So quantum is part of the space portfolio, and since I'm assigned to the space portfolio, I got quantum, so I'm here for that.
So I'll start with the why, and when I look at the geopolitical landscape, I mean, I really think that whether the world becomes more democratic or more authoritarian over the next few decades is really going to depend on the result of the great power competition that we're in right now. And I think technology is at the heart of that competition, and quantum is one of those critical emerging technologies that really has the potential to tip the scales one way or another. So that's what attracted me to this field. I'm the VP of Corporate Strategy at CoQuanta. My name's Laura Thomas. And before CoQuanta, I was a case officer with the Central Intelligence Agency for 16 years, and I ran a number of our sensitive programs overseas. And right before I left the agency, I was advising on emerging technologies. That's how I came across quantum. And ultimately, it was just so exciting to me that I decided to leave a rather exciting career and join what I think is even more an exciting industry, at least it's playing out that way so far. So nice to be here.
Good afternoon. My name is Kevin Kane. I'm the Chief Executive Officer of American Binary. We are a cybersecurity company with expertise in quantum computing as it relates to network security and national security. We have one of the early performing production carrier grade implementations of lattice-based post-quantum encryption. Currently, we have federal customers, and we're working on our first enterprise. In terms of trust across networks and deployment with telecommunications companies, we are the market leader as far as standard commercialization, ahead of standardization goes. I got into this space because, as well as my colleagues, we formed this company recognizing that within this decade, it's a reasonable risk level that maybe not a general purpose quantum computer, but a very special purpose machine that leverages quantum mechanics will make it efficient to factor large integers and unravel something like RSA, which is the backbone of the financial industry. Seeing that mission, we felt it compelled to really focus on that and try to solve that problem.
Thank you, Kevin. Joe?
Great. Well, on the why would anyone do anything other than that? So, I am with IBM. I'm Vice President of Quantum Markets at IBM, and glad to see a number of colleagues here and people that I know from my prior job, which was standing up the QEDC, the Quantum Consortium, for NIST and then for the government and the industry. So it's a real pleasure to see a lot of familiar friends and faces here, and I look forward to the discussion. Thank you also for Mary and Bobby and others here for inviting us to this panel and hosting this today.
And Joe, while you're talking, let's start the first question and do with you. So, what are the benefits you see to the government of quantum, and how can the government do better in that space? It's sort of a two-part.
Okay, so the benefits of quantum to the government and how can the government do better in its support. So there are a couple of ways to approach the answer to that. First, governments are by themselves enterprises, and so the benefits that would inure to a government are the absolute same that would inure to any corporation, any large enterprise. They want to run with efficiency, they want to return on the operational investment that they make, and governments have missions that drive them. Governments are a little bit more unique in the sense that they govern a society, and quantum is going to fundamentally change those societies that they govern. Whether you're dealing with sensing, or eventually comms, or computing, right around the corner, that is going to change the societies that nations and governments govern. So, from that standpoint, there's another interplay between government and quantum. Probably a third is that it's important that nations stay competitive.
economically, scientifically, technologically. And quantum is something that is going to it's going to provide, unfortunately, a very uneven playing field for quite a while. Although Friedman talks about a flat digital Earth, the quantum Earth is definitely not flat. And I don't know if it ever will be. So I'll leave you with that, maybe we'll elaborate later.
And Lauren from a
Sure, so the United States government has been investing in quantum for over 30 years, as well as several other countries. Right now, we feel that we're the leader in investment right now. We're leading the world. In fiscal year 2021, the Office of Secretary of Defense Research and Engineering invested over $700 million in quantum technology. From the military's perspective, we break quantum apart into kind of 4 separate areas. We've got atomic clocks, quantum sensors, quantum computing, and quantum networking. Atomic clocks are really the most mature technology that has the most use to the government or to the military right now. We're flying atomic clocks on the GPS Block 3 updates or upgrade. It's enabled precision location information and then more secure comms for the military. The next thing that we see is quantum sensing. We feel that the U.S. is also the leader in the country or in the world for quantum sensing. DIU, as well as about 8 to 10 other government agencies, have active contracts right now to bring prototypes of quantum sensors to maturity and start flying them and making them operational. We see that that has the most near-term impact on the military, so that's where we're really focusing efforts right now. Next would be quantum computing. We also feel that the U.S. is leading in quantum computing, but the struggle with quantum computing from a military perspective is everybody agrees that there's a potential there, but there's not a clear problem that it solves in the near term. So we're still trying to figure out what is that problem set and how do we apply it to a DoD mission. Even though we all agree that there's probably something good there, we're still trying to figure it out. And then the last would be quantum networking. And that one still, we believe China leads us in quantum networking. We think that it may have the biggest impact and the biggest game changer, but it still is one of those, we don't have the direct problem that it solves yet. So we're still working on figuring that out. It's more of a long-term play.
And then Kevin from Yago, you touched on the likelihood. What was your response to that question, Dave? What you see for the benefit to the government of quantum and some of the challenges?
That's pretty broad.
That's very broad.
I've been in a rabbit hole on a narrow problem. Well, it's a soft power opportunity for the United States if it's rolled out correctly. So, if, for example, a 10,000 or 100,000 cubic machine, if we were able to scale that and we're able to turn it into something digital, maybe we could fold protein, and a company within the United States cures Parkinson's or something like that, right? And that is attributed to an innovation fostered by this free market, so that when it's exported, people that now have their grandparents and friends no longer suffering say that free world is why this is possible. And so if we tie that to the brand of the image, that innovation, and the investment we make, it's a huge win for the United States and the government.
To add on to that, I mean, economic security is national security. I think that's pretty obvious. And just like what you were saying, to the extent that the U.S. government can help fund some of these commercial companies to build these products and have these discoveries, I mean, that's absolutely to our benefit. Ultimately, we need a globally dominant quantum company coming out of the United States, because that is going to be able to set standards, and setting standards really matters when we start talking about international competition and making sure that this is a technology that will be able to be used by many people, and there's merit-based trade and all sorts of things around it.
Yeah, go ahead. Bobby, you had a second part to your question. That is, what could the government, the U.S. government, do better to support quantum? The U.S. government should be applauded for the tremendous support it has given quantum, particularly over the last 3 years with the passage of the National Quantum Initiative. There are 14 nations on Earth that currently have strategic quantum programs, that is, quantum strategies. there are about 17 nations that either have a quantum strategy or 3 others that are investing heavily or partnering in some way or another. That is, the U.S. has been among the leaders in developing a strategy and in providing money. That said, the U.S. should probably put another 0 behind the money that is going to
And remember, now this is, into the audience, this is question number 2. Remember I said after 2 is when we would have level set it, and when you have questions, please let us know.
I could go back and reattack the what can we do better aspect of question
Okay, then
number 1.
we're still on question 1.
So So from our perspective, you know, it is a high priority. We do have, it is one of the top 7 priorities in the Office of Secretary of Defense. We do have a Principal Deputy Director of Quantum Science who oversees quantum activities within the Department of Defense, and he coordinates across all the agencies and all the projects that we're doing. That being said, we feel that we can do better to educate the community. You know, DIU, as I mentioned, we work with commercial companies. We also work with the government. So we've got contacts with venture capital. We've got contacts with the national, the Defense Innovation Base, the National Security Innovation Base, and all these different organizations, as well as relationships back into the Department of Defense, including the agencies, the components, the combatant commands, and all the services. So we feel like DIU is really in a good spot where we can be that connector between what's going on in the commercial industry and how do we connect that with our government folks who need the technology. And we feel that we should be there to start educating the folks in the national labs and the applied R&D folks in what capabilities quantum has, and help them figure out what their problems are that quantum can solve. So I'll give a plug for DIU, a shameless plug for DIU. So the way that we are different than other government organizations is that our goal from problem solution or problem definition to contract award is 60 to 90 days. So traditionally with other types of government contracts, you're looking at about 18 months. So we really look to execute quickly. And we also look for that contract to be somewhere between 12 and 24 months long to deliver a prototype, and then it can go from there. You can use other contracts, or you can go into a traditional government contract from there. But we feel like we could do a better job educating the community, helping commercial companies know what the government's looking for, helping the government know what's going on in the commercial sector, and help matching everybody up for the greater good of the government and the country.
I'll jump in too. What could the government do better? I mean, the government's done a fantastic job at funding the R&D. Now it's about how do you get this technology out of the lab and actually get it into government programs and programs of record, because that's where a lot of the real money is. So we have to get these items out into the field, particularly like with cold quantum, we do quantum sensing. Get the sensors out, start testing them, let them fail, figure out how to fix them, and then deploy them in a way that is ultimately to all of our benefit.
One of the challenges, I think, there are people in the U.S. government that when they hear the word quantum, they shudder because they think of failed investment. And so there's some nuance that's required, and maybe, I don't know, a council of experts on it or something to help create a better understanding and narrative so that that doesn't happen. Maybe they shudder at the thought of a general purpose quantum computer. Maybe that's a realistic thing to shudder at because it's quite far, maybe. But you can have, like, imagine an FPGA powered with quantum mechanics, or imagine an ASIC, or special purpose machines that are not computers. And these things may be much more realistic, but people who put them forward might not be heard because people imagine it has to be like a monument architectural computer, and that's total nonsense. So it's like getting into the details of the details is extremely important. But decision makers don't do that, and they get like market research level knowledge. The important things are done not in anything you can find in Gartner. They're in the 1% not in that report. And I think that that's lost on a lot of decision makers.
Are y'all ready for question number 2? Question number 2 is this, and Lauren, you touched it a little bit, but I'm gonna first go to Laura because I think you have the background on this. Earlier we talked a little bit, started about sensing and quantum computing. From a government standpoint, let's sort of level set on what areas are we breaking down into.
Yeah. Well, I mean, obviously the U.S. government's enormous, so there are certainly different parts of the government interested in different things, and for the most part, Department of Defense technologies, you know, some communications as well, and of course, you know, quantum computing, but a lot of interest in precision navigation and timing, and that all goes back to our reliance on GPS. And we just cannot continue to rely on GPS. We're going to have to be able to cut that link and find a way to be able to navigate independently of outside signals. So there's a huge appetite for that within DoD. You know, Department of Energy, certainly there's interest in quantum computing and communications, and then of course, you know, military service labs, part of DoD, that they use communications as well. So you know, it's a wide swath, and then you can go to NSF and how does that fund some of the just basic talent and early research from, you know, universities and basic research that needs to happen in universities.
Any other, go ahead.
Yeah, we need a lot less physicists in quantum computing and more people in radio and in, physicists are wonderful. My favorite person to interact with intellectually is a physicist because their mind is wide and beautiful. But you know, I used to work in quantitative finance, and I ran an alternative data team for one of the oldest hedge funds in the world. And if we would, I'll make a generalization, if you bring a physicist in with no training and you leave them alone and say make money, it won't happen unless they're really extraordinary. Because so you have to give them tools.
I just got quiet.
It's really important. It's really important because physics is a skill set, but you also need to know about computer science and radio spectrum, and it's a large interdisciplinary thing. And there are individuals, no matter what they do, will be extraordinary. So they can be a physicist, they can be a scientist, but it definitely is an interdisciplinary problem. And I would think that that's just really important.
Yeah, I'm gonna go with a little bit, see if something else. I'd go even further than you. Yeah, I'd like to see if we have some policymakers that understood that too. It may lead to us getting more financial, more funding, etc. So it actually goes interdisciplinary. To me, it's even broader than the technical skills that we identified. I mean, really, it is very vast. Anybody else? Any other areas we haven't identified that we think is important for our audience here tonight?
I might just expand on PNT a little bit. Yeah. So in position navigation timing, the T timing, atomic clocks, we all know about the Block 3 CSACs and Rubidium. There are in the works right now in U.S. laboratories just extraordinary designs to look at miniature optical clocks. So, for example, using ytterbium, using better elements with more precise, finer line widths, and therefore better Allen deviation, meaning they will keep accurate time longer. So, more accurate time for a longer period. This allows holdover and could perhaps be a very important bridge in, for example, navigation. But not just navigation. People think about that first because, hell, I got here using a GPS on my iPhone, and I bet 90% of you did too. And so we think about that, but there's another one. Time is a huge commodity, and it's a very important commoditized element that, yes, it is downlinked from GPS and GNSS systems globally, but it drives communications. When you do a wavelength allocation in telecom, you add several hundred kilohertz bandwidths to the side of every allocation to allow for drift error. If you have accurate clocks, you can narrow that, compressing the amount of information in a given bandwidth significantly. All right, this could add orders of magnitude to, for example, our current wavelength allocations if we had very accurate commoditized time distribution. So land-based, satellite-based, there are a number of different ways. It's not an easy problem, by the way.
What I want to do, it's okay, let me get question 3 and they won't open it up, okay? I really want to leverage the group that we have here. It's a very diverse group that we have here. I want to talk about startups and small businesses for just a second. And say, how can startups and small businesses engage in this quantum? What are the challenges? How can they partner with you, et cetera? For example, DIU can talk about from a government standpoint, IBM from your leverage standpoint. But first, I wanted to ask Laura and Kevin to talk about their experiences and what they would tell startups and small businesses how to get involved in this area of quantum.
Well, go in with eyes wide open. Experience it's a high barrier to entry type of industry. I mean, it's hard. We're solving really hard problems, and there are significant, in some cases for some companies, significant science that still needs to be discovered. In our case, there's certainly engineering that still needs to be done, and it's not trivial. So finding the small programs, the SBIRs out there, that's a start. NSF, I-Corps type stuff. I would suggest in an industry like this where there is that high barrier of entry, look for partnering opportunities for companies who already have a reputation in the government space, who already have some of those connections.
Kevin?
It's hard enough to be an entrepreneur, but to be an entrepreneur and working in and around quantum computing and national security as it relates to quantum computing is an order of magnitude more difficult. So my advice is to make sure, if you're a personality of an entrepreneur, that every single person that works for you is that much more impressive than you in every way. And if you can't build a team like that, you're going to fail.
From an IBM perspective, how do you support, I know you do, left and right, but in the area of quantum, what advice do you give to small businesses?
Yeah, when I think of small businesses, I go to the supply chain. That's extremely important. Look, a quantum computer has, thousands of components in it, and many of them are derived from businesses, small businesses, that come up with a very specialized component. When I was with the QEDC, one of the things that we asked the small businesses that had joined the consortium was, what can we do to help them? It's really, as Kevin pointed out, it's really hard to be an entrepreneur. It's really, really hard to be an entrepreneur in the quantum space. And then when you're looking at, say, quantum computing, the widespread adoption, volume sale of your small miniaturized laser, or your traveling wave pulse amplifier, or your isolator, you're only going to sell 10 or 100, 500 of those next year. That's a tough market now to break into because the market isn't there yet. So we try to support obviously our suppliers and domestic suppliers as much as possible. I think it is a very difficult space. So there's the supply chain, and then there are the developing the end uses of quantum. There are many small startups in the software area, applications area as well. And some not so startup anymore. I mean, Cold Quanta, I remember when Dana started that, and now it's a fairly major force in the quantum arena, so it can be done.
So the life cycle of a unicorn in cybersecurity is 4.3 years before they reach $1 billion in value, if they're going to reach that, right? That's pretty easy for investors to get behind, yet it's really hard to get cybersecurity investments done. IBM makes investments in venture investment. Do you guys have a long quantum horizon where you're willing to carry that unique entrepreneur in the space for the 7 to 20 years?
Yeah, I can't really comment on that because I'm fairly new to IBM, having come from the consortium over about a year ago. So I can't really comment on what IBM's policy is at this point. But I do know that IBM is very supportive of small niche players in various areas. And yeah, I mean, there are components that we have to make. I know, for instance, at NIST, take them for example, at the National Institutes of Standards, there are a large number of components that they actually just have to handcraft, and they would love a small business to take that away from them and start manufacturing some of those things. So there are a lot of opportunities.
Yeah, go right ahead.
Just to address that, just because I work for IBM Ventures, we do have a pretty long-term horizon on the quantum investments, and it's really all around accelerating the ecosystem of software applications in the space. So yes, it's going to be longer than most typical software data where we can get an exit probably in a relatively shorter time than VC. Quantum is going to be that longer tail. Yeah.
Thank you. Yeah, go ahead, Kevin.
I missed the previous panel, but it's very related. So also a shortage of talent. So in our space, the number of people in the world who have like real depth and competence in lattice-based and post-quantum cryptography, there's only 1,500 people on the internal list. So, and maybe people who are capable of doing it, we'll just guesstimate, maybe it's 10,000 people in the world who, when you know when they hire them, it will get done. And then the cryptography part's not enough. You need to know about the OSI layer, you need to know about transport security network, they need to know about Linux kernels, and that's gotta be one person, not a team. That number of people who can do that was even a short list. The United States is really short. So we have a huge talent problem because, like the United States, the president put out a memo that they have 180 days to get everyone down to AES 256 and 3000 RSA 3072. None of them are meeting that standard right now. And I don't know that all of them have the internal engineering capacity to redo everything. So the goal is here, and the ability to do it's like here. And it's a major talent problem. The other issue is that for a lot of people, they see that maybe someone else will take their market share because they can meet that standard. And so it's going to require like federal contractors being a little bit more cooperative with each other rather than trying to take something from each other, because they're just going to fail.
Yeah, just from the cold quantum investment angle, I mean, we're not creating the next food delivery app. I mean, this is deep tech and it's hard, and we're looking for investors who, you know, they get that, that's their mindset, and they want to, you know, potentially they want to invest in a technology that really could be a platform shift. And, you know, for a long time, it's not really been in the mainstream, but it's starting to become more mainstream, at least from the investment standpoint. Ray Dalio, Bridgewater founder, just wrote a book this past November, and it was Principles for a Changing World Order. And towards the end of his book, he basically mentioned quantum technologies, and he said, you know, this is, in his view, going to underpin massive wealth creation. So when you start to have more mainstream investors really start paying attention, I think it's for the benefit of all the companies that are out there trying to raise in this market.
If I could do a commercial break also, but I'll say too, from my sense for operating federal funded research and development centers, we try to help out to some extent your question by hoping to short that down, and that's from an investment standpoint. Is one, providing our technical folks available to have those type of discussions and say, where are you, mentors and other things, just to try to move things along. On the other side of the house, we also have our program side of the house that can introduce you to, for example, whether it be an IBM, a DIU, the Air Force, and others, to say, hey, this looks promising, and engage them as a part of it. So that's something else that we sort of do role-wise. And we'll get DIU, and then we'll get your question. What about DIU? What do you offer the small? I'm looking at you really. The small businesses and
right. So you kind of touched on it earlier, where there's definitely this feeling of failed investment, and so I think when approaching the government, there's kind of this history of failed investment around quantum and overpromising. So what we would say is come in with realistic expectations and be realistic about what problems you can solve. Be transparent with us. Tell us what your challenges are. Tell us where you think your risks lie. Don't overpromise to us and then underdeliver. And that being said, you know, also try to understand what our mission is from the government's perspective or the military. Understand what the nuances are of the military's perspective, and then tailor your solution to that to help us get there. And organizations like DIU are there to help, you know, to help you with that and to help translate what the military is doing into commercial language to help startups be able to work with the government. That's what we're here for. And if, you know, even if you're not a company that is necessarily where DIU would invest, because we're a little bit higher on the TRL scale, we can put you in touch with the other organizations, whether it's an AFRL or, you know, put you in touch with the folks who do SIVRs and things like that. And so we're definitely there to help you, even if it's not something that's going to end up in our bucket. We can help navigate the system, because it is difficult working with the DoD and understanding our organization's challenging.
I think there, just an opinion, it would be helpful to have two approaches. There would be this approach where we have 80% solution in science, and 20% it can be a complete failure, and we'll be finding a pivot. I think there need to be investments that are willing to take 100% losses. Otherwise, we're not gonna get the innovation meeting in time to be competitive against adversaries that do it. And if we're just gonna iterate, then our adversaries who are willing to throw 50 billion and lose all of it on genuine science, then we don't have a shot.
We had a question in the back, and we'll go over here next.
Yeah, so to go to both what Laura and Kevin were just talking about there, the biggest challenge I've run into in working with startups, and I work with literally thousands of them, is DIU's fantastic and AFWorks and the others, but this persistence with the government is the challenge, right? So they get started and you get a fantastic proof of concept. That is not a program of record. How you bridge into that, because as Laura said, there's a lot of work that still needs to be done. So you can validate it with a proof of concept, but moving it from a validation into an operationalization, that's challenging, and especially in this area where the science is changing almost as fast as the technology is, as we learn more from the research that's going on. So that ability to create that bridge beyond where a DIU is engaging at, to get it to actual operations.
That's really important.
That's really important.
Yeah. You know, was it who has the ion trap machine, IonQ, and University of Maryland developed a fault-tolerant qubit. The week before, they did it, it was field tested, and they spent 6 months on it. The week before, someone was telling me that, we don't have that, so, we're not that far. The next week is a completely different thing. The week after, it's a completely different thing. The innovation in quantum computing is double exponential. Even at that rate, you can imagine a computer still a while away, but it's moving so fast that cognitively people can't process it. And if the president gets a report on quantum computing, a month later, it's all dated and wrong. It's moving that fast. So if a person says I'm an expert and I studied that a year ago, you're no longer an expert. You don't know anything anymore. It's moving very fast.
And we had the first question here, then we'll go there next.
Yes. Kevin mentioned something that I have already heard from other people, that we are moving towards a technological and economic war between democratic countries with US as leader and authoritarian countries with China as leader. And for instance, in the case of artificial intelligence, which also seems quite critical for possible impacts in our lives, I would say that I have a feeling that the main innovations have come from the private sector. And the truth is that, depending on how you measure it, China is the world leader in artificial intelligence in front of United States. So, do we have to, or what do you expect in the coming years, that this threat of this technological and economic war will change the mindset of the government and will start taking the lead more to avoid that happens what has happened in artificial intelligence, when US is no longer the leader, and this will be like, okay, we have to do things differently. We need more public intervention in the market to make sure that those investments that you were saying that have to take 200% risk. So somebody's doing that.
If I can jump in on that. So the Joint Artificial Intelligence Center is failing left and right. It is designed to be the centralized group for the Army to figure out how they're going to source that and allocate artificial intelligence. And the generals, the commanders are not taking the advice. So you're correct. I fully agree that you're correct. We're in this arms race, and it's around cyber, artificial intelligence, and quantum. And we're failing miserably from the government's role of orchestrating that. You hit on a statement right there that is core to this whole belief of mine. We need the family offices of the United States, the billionaire families, to be going after the altruistic view. And I think the people in this room have a louder voice than the grand majority of this country to go make that happen. So I certainly have been out in front of the family offices for the past 2 years, pounding on this, but I welcome the rest of your participation in that, because they're the only ones who are going to solve this.
But I was trying to say the question you're leading to, are you trying to say, how do we get more?
Do they foresee that the government will change and will start investing more and intervening more in the innovation?
How do you
get just to the market?
So what he's getting at, to some extent, I follow you on everything you're asking per se. So the government trying to lead per se, how do you get more private industry? Is the government willing and trying to do that, and how?
Well,
I think, okay.
Yeah, I mean, there's a famous quote, it was by John Boyd. He's founded, the idea of the Buddha loop. He was Air Force colonel, and he basically said, bureaucracies don't change until there's a disaster. And so what is the disaster that has to happen where we really supercharge, our approach to quantum? That, of course, we're investing in quantum
we'll go there and then here, because I know you're very waiting for, the young man has something to add to this. I would say the government sort of does recognize that need, that it needs that private industry drive, especially some emerging technology area. We're seeing a lot, I can tell you for a fact, we've changed how we operate totally as writer just for that reason. And that's why we're willing to do public-private partnerships. We've actually set up a corporation to do that just to benefit the government for a reason. Now, if the money's there, the policy's there, that's a different question, but there is sort of that's sort of known to some extent. We'll see where it leads to. Yeah.
So, we start out talking some very nice things about quantum. What are the warts? What are the most critical things? And we've been dancing all around this. But what are, from each of your perspectives, what are the most critical problems that we need to solve or can't solve?
Okay, did you talk to Kevin prior to this?
I'm trying not to give it.
I know.
No, I'm just a
I'll give you the one that I think is acceptable to give. The internet will stop working as you know it, because there will be any kind of guarantee on security, and that quantum computing, in the worst imaginable theoretical case, breaks every kind of encryption that can ever be made with software. And that means that there's no ATM transactions. From an insurance liability perspective, no one would want to move it. Imagine you're BlackRock, and every time you send orders to an exchange, they're being dumped, decrypted on the internet. Then that asset manager they're afraid of being sued. So it's the end of the financial system, and it's not an impossible thing. That's part of our mission. So that's the afraid of PG version.
That's national security, John. I think y'all touched on some other areas too. That's a real good one. Because I think you also touched on the fact that the lack of talent base that we have in this space. What else can y'all think of? What are the warts or other things? National security concerns.
Cognitive warfare, so influence operations. Already, populations are influenced by algorithms, and they're. Right now, if you look at a certain conflict in the world, influence operations are a big part on the internet, lots of disinformation. Quantum computers will know they will enable algorithms to know more about us than we could ever know. I always say the most easiest person to influence is a high IQ intelligent person. And one of the reasons I believe that is because their whole life they're told that they're smart. And if your whole life you're told you're smart, you don't want to find out you're being influenced because your identity unravels. And so quantum computers will get everyone. And that's a good problem. I think that there should be two approaches. It'll be interesting for the United States president to bring together some of the world leaders and in like a NFL-like style, broach the conversation. Can we agree on a moratorium for using quantum computers for cognitive warfare and others? And then watch the reaction and let the world realize who the good and bad people are.
Anyone else?
Yeah, anybody else? Any of the awards that y'all from DIU, from IBM, or?
Well, what I might offer is this, paraphrasing John F. Kennedy: ask not what your country can do for quantum.
We do the hard things.
Because honestly, look, a lot of the agenda when people interact with the federal government, our federal government, is what can they do for me? How can I get my research funded? How can I get my graduate students funded, et cetera, et cetera. I think if the private sector took a more mission-oriented view when approaching the Air Force, so I also serve as senior quantum advisor to the Air Force as well, so I can speak from that standpoint. If the private sector adopted a more mission-focused, mission-oriented approach when approaching the federal government, saying, look, this is what we can do, this is what we can't do, here's a realistic approach, that would really help bridge a gap that does exist.
Yeah, I would agree with that, and coming from CIA, my whole job was to handle assets and determine the truth, lies, and everything in between. And I really hated it when people tried to bullshit me. So when you go into one of these government offices, especially on the security side, you have to be able to speak their language, and you can't bullshit them. You can bullshit some people, but you can't bullshit all of them. And they pick up on it, and they don't like it. It's not going to go over very well. So that's one thing, sort of to that comment. But when we really look at the government, I mean, so many things obviously that have to be fixed, but ultimately it comes down to acts of Congress to change the way federal acquisition works, and that is a tall order.
Right now, DIU uses a other transaction authority on a number of things, OTA. Great, we love it, I've done a lot.
That's a good one.
Not at IBM.
You dropped the mic on the congressional acquisition, but we'll continue. We'll go here and then.
So, back to some extent to what Joe was talking about, and what we touched on a little bit earlier about support from, as how much your government can do. In the previous panel, one of the AWS guys said, look, we are starting to undertake some fundamental research around quantum. When I was growing up as a young person that wanted to be an engineer or scientist or something, IBM, Bell Labs, Texas Instruments was doing fundamental research. Then we kind of got, it's been a wonderful thing, but we got on Moore's Law. There was a straightforward engineering path to greater and greater digital power. And our biggest corporations cut back on the amount of research they were doing. We're going to let academia and national labs take care of that. Quantum has come along, and it's scary, okay? And so we need our biggest companies. Small companies are always willing to take risk, okay? You get a little small company, they're willing to take the risk. The big companies need to step up and take a mission-oriented, long-term, especially on something like quantum, and make the investments and do the independent research. Right now, as a small company, I'm kind of stuck. While we're doing some pretty advanced research because we think it needs to be done, but our sources of funding are short-term venture capitalists and the government that's doing their best and often picks them. I've had great support from DARPA and from the DOE and from the ARO and from NASA, for Christ's sakes. They've been great and valuable, but they don't provide enough discretionary funding. I really like it that a company like Amazon started off selling books on the internet is doing fundamental research in quantum. We need more of that from our corporations, taking a longer term view on AI, on quantum computing, and quantum encryption. We've lost, I believe, as a nation, our technological unquestioned supremacy, in part because there's been less investment from the big corporations.
I think a couple want to respond.
Just a really important, negative thinking creates negative thinking, and they're definitely in that situation in the world where people are clenching their fists, but I think if we control for risk, quantum computing, as we imagine it, maybe not what we have right now, but as we imagine, I have to be a dreamer, right? So I have to believe that we can cure diseases, we can have our grandparents living longer and have more conversations with us, that we can use it for optimizations for nuclear fusion to make them more usable, and to create a resource abundant world. I think it's very important not to lose sight of that. I don't think anyone in the world wants to fight, wants conflict. Maybe some people do, but if they grew up in a different environment, they would think different too. And quantum computers offer that. And I just wanted to point, I don't want to finish with this negative note.
No, we're not done. We'll finish. We got a question there. Yup.
Yeah, just a suggestion maybe, but just wondering, Lauren, you and DoD, we keep hearing this date of April 14th, not 15th, the 14th, for 2030 when we reach Y2K and the end of classical computing versus quantum computing. Is that sort of a goalpost that DoD, you think, would endorse as, we need to do something about this, and perhaps craft a campaign of research, development, and operational capabilities towards that date?
I think that the DoD probably needs to move faster than that, to be quite honest. And I think that's the first time I've heard that. I think that we're really just trying to move as fast as we can. We're trying to beat our adversaries. So I think we're trying to move as fast as we can. Is the short answer to that.
Yeah. Some of us are cautious about mentioning dates and other things in this environment because
I didn't make it up.
I know, I'm with you, but
the timelines for like post-quantum encryption, every single one overall, they're like 2027-year field testing. We're already deployed with the telecom. So in quantum computing, the timelines, whether they're off or not, is going to be about whether some smart physicist who's 25 years old at not even an Ivy League school, at maybe some school in Oklahoma, who realizes that he has developed a different approach that's more novel, so I'm just pointing it out that, this is actually one quantum computing at this level of complexity is really the, I'm not qualified, but the land of the geniuses. I have worked with some people that smart, and they're bronze medalists in physics Olympiads, and I can't keep up with them. Those are the people who are gonna do it. And they come in all shapes and fashion, and so the problem is that one might develop a new theory next week that changes the way we approach it, an indirect observation or a lot of things. And you just don't know when that's going to happen. That's what's so interesting about it.
Just a couple more questions. I think, right there, man.
So, war theory, a guy named Thucydides said that fear, honor, and interest cause us to go to conflict. And if quantum is actualized, you have the ability to change all three of those elements through the use of that quantum. So are we going to change the character of war, or are we going to let somebody else do it? That's the question.
You're one of my favorite people in the world, you know that, Brian?
Pretend like you didn't know him. Okay,
I already knew that. Come on, give me some shots.
Oh, it's not a pre-talk. Like in the back?
Yeah, I just wanted to mention, so in, I think 1983, 1984 in Austin was created the Microelectronic and Computer Technology Corporation. That was created by the U.S. government. It was funded by 20 Fortune 500 companies, and we rapidly commercialized disruptive technology and really put the U.S. ahead. And a lot of people don't realize the history of that. It feels like we need that kind of collaborative, rapid commercialization. These one-off guys who might think up the idea, those are out there. But when you bring these really bright guys together and throw things against the wall, and go with it. That collaborative research can really propel things forward in a rapid way. So I would really like to see that approach. And that's all I'm gonna say. You've got other questions here.
Well, let me phrase it the question. Have y'all seen or anything along that particular line that's occurring right now?
I just want to highlight, if it's okay, I highlight a real big barrier to entering quantum computing is the existence of full stack quantum computing companies. Because if I develop quantum algorithms and I have to use your computer to log my stuff, then I don't want to use your stuff. And so we need to get to a quantum computing company that sells the computer and has nothing to do with it. And this full stack business is a barrier to entry for all the other smart people. Because building an actual computer is very hard. Not a lot of people can do that, but many people can use quantum algorithms. But if they're going to use their computers and log them, then no one should get anything. Oh, I just won't do it because it's like you're stealing my stuff or suspicion of it.
Just use Qiskit. It runs on
when you want to take it to market, though,
I'll go there and then since he hadn't had a chance. I'm sorry. I'm not ignoring this.
You don't look over here, but that's what Brent just said. In 1983, actually early 82, late 83, a company and a group at DIA called Socrates came into existence. And we ran that to 1991. Every innovation that he's talking about for MCC, Dell Computer, everybody came out of that initiative. And it was killed in 1991 because three reasons. One, Reagan screwed up, right? Number two, they cut the funding because we went to the Gulf War. And the promise was made then to reinstate that program once the Gulf War was paid for. That never happened. Then it was tried to be reborn during the Obama administration, believe it or not. And if you remember, he gave a big speech on technology and Ronald Reagan, and that lasted a week. Then they killed the program. So DIU was actually spun out of Socrates and was thought about back in the 80s, right? And they started it, and actually what's interesting, did you ever meet Mike Brown at DIU?
Oh yeah.
Okay. Mike Brown can tell, I think he's gone again now, right?
No, he's still here.
Okay.
Yep, he's still alive.
He can literally tell you about how this was actually born back then. And then it took Obama giving up on doing the bigger program and launching 15 DIU. The problem that we've got is you have Congress, of course, that thinks every year. Because in the next year they're running for re-election, right? So the problem is, and here's the worst part of this, guess who has taken over the exact program that Socrates wrote? Any guess? China. China is actually operating under that exact model. and they've got 5 provinces that are each trying to beat each other on Socrates. So you want to actually fight these people? We've got to actually get aggressive, and people have got to start demanding that we spend money and don't look at. The difference is Socrates was based on technology and not finance. Right? You can go look this up. It's actually a very interesting read. After the Gulf War, we went to finance-based technology development. So everything we're talking about here is all done on budget.
So, I did not talk to these gentlemen. I thought about this question some time ago. But I'm glad they set me up to ask this question. Are national resources, such as the Trusted Foundry Program, going to be equal to supporting y'all on these tasks? Yeah, other national Trusted Foundry Program and other national assets like that.
Well, I'll just say from IBM's perspective, we feel very confident in our program. We have a well-defined roadmap. We have hit our milestones on that roadmap 2 years running. We have no doubt we'll continue to hit them. And if you look at our roadmap, we'll have a 1,000 qubit machine with great quantum volume in the year 2023. We'll continue on. We're already at 127 qubits. We continue to enhance our error mitigation. We continue to progress as a company. So we don't have a need for a Semitech or something of that sort as a large entity. That said, we enjoy the collaboration. We do collaborate, and I'll add something. Every American here should be very upset about a fact, and that is the government of Germany and Japan and soon Canada, these are all announced, have better quantum computers and quantum systems at their disposal than the United States government. And IBM sold it to them. Our government is not paying attention. I lauded them earlier, but they're not paying attention to the fact they need to buy quantum systems. They need to start spinning up a quantum workforce. They need to start orienting it to the use cases and missions around national security. And getting them to listen has been very difficult.
Anyone else? And those, by the way, are warts.
I was just going to circle back on that comment, kind of your comment about private industry. You know, China's investment is mostly from their government, and that's one thing that the United States has that they don't have. We have free enterprise, right? And we have private industry that's doing all this innovation. So you guys should leverage that, and we should use that, all that innovation money, and we should pull that into the Department of Defense and all these other agencies, and we should really try to work together instead of separately. I think we're trying very hard, and you're seeing that. You're seeing Defense Innovation Unit, you're seeing Army Futures Command, you're seeing all these organizations. You know, every service has their own X, you know, AFWorks, SpaceWorks, NavalX, and all these things, and we're trying, but then we hit these issues, these transition problems, right? The valley of death, and we can't get there. And I think for the department, it's a culture change, right? It's the folks who've been, you know, the middle management who's been doing it the same way for 20 years, and we don't want to change the way we do it because we're going to lose our job. And I think that's the hard part for us right now, is changing our culture and realizing we got to change, or there's going to be nothing left to change, right? And I think that's really the struggle where we're at right now.
It's very difficult for the government to think holistically, and a lot of it's very piecemeal. So you start thinking about what it really takes to scale up quantum, industry. It's going to be so many different things. Talent, workforce, obviously being a key one, and then thinking how quantum lashes up over different technologies. So, fortunately, at CoQuantum, we work across computing, sensing, and communications, and we sort of see that holistic, how they all come together. But how are you going to start Quantum. Japan is one, Australia under AUKUS. But we're going to have to be doing a lot more of that.
And let me ask our panel just one final question for everybody. How can others here either partner with you or collaborate with you or help fill your needs out? How would you answer that? How would they get in touch with DIU? What are the opportunities? Maybe talk a little bit about that for TRL.
Sure, so our website's diu.mil. We've got folks, you can reach out to us. We typically post solicitations to respond to, but even before that, if you're looking for, we call them Sherpas, we'll be your Sherpa, we'll help you navigate the Department of Defense. Even if we don't have a solicitation or we don't have money for what you're working on, we're certainly there to help, and I can give out contact information from our folks who can help you and help you navigate that system and go from there.
And Laura, Kevin, you have a difference of how might you collaborate, partner with others?
I mean, we're open for any and all conversations, so find me in the back.
And Kevin, I know you had the narrow focus, but you gave some very broad answers. But
we have, we will be vetted and approved. Well, we will be in a position long before NIST standardization where our encryption is ubiquitous in the private sector. And so we have drop-in solutions right now that I can take you aside and show you the vetting and the people involved and say, this is carrier grade built, and carriers are using it on their servers. So we've been in stealth for 3 years on this, and so our website is looks like junk. Because there was a bit of, I forgot, I haven't looked at my website in 2 years. I haven't. Someone told me this looks horrible. This doesn't look good. I didn't know what it looks like. I was like, I honestly haven't visited. And it was kind of an opportunity for us for a while to not, you know, we wanted to be a market leader and we wanted to be the custodians of our national security, and we didn't. I was a restaurant school, competitive. So it would be better that we're not educating other people what they should be doing, so that we could widen that lead and create that moat. And we want that moat, and we're going to continue pushing it on throughput and other importance. We want to replace RSA in 7 years. And so if you go to ambit.inc, you can see something that's going to be almost coming into play. If you contact me on LinkedIn, I can go through. We're going to be rolling out a new website in the next 45 days that hopefully will be more instructive.
Good. And Joe, you got the end. Remember, you got the end on a positive note.
Well, our website's in great shape. So go to IBM Quantum, and you can see what we're doing. We're always happy to talk.
I do have a joke then, since you got to us.
IBM. Should I close it first and then you tell the joke?
It's a factual thing. So IBM has we actually built our stuff off of one of them is called Kyber, and that was in part thanks to IBM, SRI, and ARM built. But IBM has hybrid solutions, quite classical, and ours is pure post-quantum. We do not espouse to, we don't support the hybrid approach. So we can talk about that.
No response, Joe. All right, let's give Alice a hand. Thanks for they really did. This is the first time I met these folks. This is really great. And I do, Mary Ellen should be at your final comments. This is the last session. But I do want to thank Capital Factory and also the Innovation Council. The names you saw a little bit earlier through the days. I think it's the first time we sort of done this type, and I think it's worked out great. So, and thank you all for attending.
Yeah.
world that we all know.
Now we're trying to rebuild it. We made a porch on or if you want, if there's somebody else, look at my LinkedIn, it's like, this guy over here.
You have my phone number for the pictures?
Nice job.
Nice to meet you.
Thank you, Bobby. Thanks so much. It was fun. It was really fun. I would love one of those. Do you have an XL?
I've got an XL right here.
You are just super. Thank you so much. Isn't that nice?
Bobby, great job, man.
Oh, that's great. It's nice.
Oh yeah. I both applaud you for taking the risk with Kevin King. I both happy you did it, but I'm sure.
Kevin, good.
Yeah. I met him last time we did one with these guys at Fed Supernova. It was like,
Good to see you again.
yeah, watch.
I know. Yeah, I think a good dog on a leash. I know exactly.
I gotta go let dogs out. Good job on. So which part of minor do you work in?
I'm in charge of Texas. Yeah, we're building
And a large sweatshirt.
our job. Now, my job is
Okay, interesting. Well, I did not realize. I'm Will Oxford, by the way. So we're a quantum photonics company in cybersecurity based here in Austin. And so we have 2 Air Force contracts. Yeah, so information director, Mike Hayduck, if you know him. Yeah, so Mike is one of our big supporters there. Well, we know about them. We don't have, you're talking about down in San Antonio, right? Yeah, we don't have any close contacts in there. Oh, really? Well, if you have some contacts for us, I love it. Oh, really? Good. Well, we go to ASEAN events, you know, and try to make contacts there, but it's that'd be great. But just send me an email, whoever we can talk to, we will. We have basically, we're about a year away from having the first prototype. And probably a year after that to having. You did a raise. Nice to meet you.
Yesterday on the one of your programs. How do you pronounce it? You're with them. I said on the webinar, one of your guys was on the doing customer chase for we're having an industry roundtable in September. We're trying to bring together to set the parameters around the framework for cybersecurity standards around the Internet of Things and security. That's something you guys should be involved in.
No doubt. That's my real area.
Okay, so I'm the one that conceptualized this, and I'm leading the webinar series. And we're now putting together an organizing committee for it. Because this is kind of a much bigger thing.
What level are you operating at in terms of engagement? If I can pay, we just got a new VP that I can talk to her at what working level or what?
Well, if you look at the documentation we have, we're looking for executive level participation. I'm kind of conflicted with that. So
So we'll eventually ask the executive level to bring working level people with them to this technology. So this doesn't say IEEE on the program manager. I've been working on it now. So we're doing a series of conversations. It's the reason I'm asking to high court.
It's definitely nice job.
But I could send you minimal information. It kind of feels like you guys have
that's our main focus. But you got the emergency with this. We're working closely with this. We got these all kinds of stuff. So we've been doing. The reason why when you said I try to read, we've also been working on the IEEE and ICS and cybersecurity. So we've been on those conversations too.
We're really the rubber's hit the road now. Now it's a matter of getting the right companies. We're getting good participation. Meaning we get commitments from Boeing, Microsoft, and Hitachi, etc. And Schneider Electric. We'll get the right people. But it's just when I learned a little bit more about these companies, I should at least ask.
And I'll send you more info about that.
We're not asking for money. We're asking for the right people to come to this industry. It's planned to be here in Austin. We may move it. If there's more convenient times, we may move it.
Based on where everybody's at.
We got currently headquarters are in New York City. We can do it there. We can do it in Napa Valley.
Here's good.
I like your time.
I think they like it.
Good job.
I'll do it. Take care. Thank you.
Bobby, you did a great job.
Oh, appreciate it. That was the right thing.
Well, it was a like the cantankerous team.
Nice to meet you. So I doubly appreciate it. I live in the place right now. That's what I'm looking for. Okay, so are you in Quantum? I was Cyber System lead on now my job is to build partnerships.
Relative
your environment by being able to take a drone and identify the source of right now that it's weird. The building is so the entire grid is also served as the map of the Wi-Fi. So we started off with 7 and now we have 12 and 4 which are everything. And those 4 are all so our next contract is no. With our list, we guys go, when they're interested, and then we want to accelerate our service where we can technology, as opposed and the only thing I heard is the intersection of cybersecurity there's something going on. And if you have line then I bring you the concept back opportunities that
But either way, yes, exactly. That works both teams.
I reached out to you on this. Once you and I connect, I'll send you a bunch of information. I have a card here. I guess
what you're doing, understand. Where's it coming from?
Okay, question out. My wife just my house. I guess we're going to be around here a little while. I don't really know. As long as you are quarterback, actually, tomorrow night, Greg, right there, and I, and our quality control.
I flew my own airplane. Did you really? Believe it or not, well, pleasure to meet you. Looks like it, but yeah. Well, it's hard to say before.
Well, I mean, it's a really simple airplane. Just having access to people who are qualified.
I tried to, I don't know if I can. I tried to go at least once in that. There's nothing worse than feeling behind
So,
That's something you just bring up. We have one of that.
Well, the thing is,
so how do you just talk
yesterday I didn't have to do it, but I was driving here. It's about a 3 hour, 30-minute drive. You wouldn't have gone. You had these gale foils coming up. But it's good to yeah, well, I actually looked at no, my state good went for it. I'm not going to get into a lot, but I looked at the prognosis.
Hey, Kevin, that was awfully interesting.
My point is, if I get to be somewhere, so I never plan on using the airplane.
Right, so we're trusting California provider.
It's funny,
The Department of Defense is looking for some technology that we don't want for investment. We're with so it's old something like so we
yeah, no, it's our feedback. I have, there's cases of that's got carry over. Yeah, well, I really get in trouble here. That could be a real serious problem.
Yeah, I recall I was in South Africa. And you're in Seattle.
I was looking at
it was easy. Everybody was drinking. But I'd like to have a follow-up conversation.
There's no bad.
So I finally
they weren't stopping.
And the guy behind me tested me for a follow-up. You know, I'm trying to
you could tell him to stop.
Well, my friend is 6'4".
Well, no, we've got those in the airplane. I've never had any issues with them.
3 o'clock, 12 o'clock, no coffee.
I usually go just before the meeting, try to and then actually here's the way more so high vibration. Which is a lot. I know. Now,
compared to when I learned 20 years ago. You've got a map on there, you've got traffic on there that shows you where everything is. You can have weather. It's just such a long way to go. When I first learned it was like a lot of publications to make it easier.
I've seen some beautiful airports. I went to Slovenia and saw a company that they used for electric. Well, both. They're well known company. They actually been doing like electric aircraft and Airbus.
Still got a ways to go. It's just we talked about total range. But you have to understand, there's always something you're not anticipating. Are you aware of rerouting? I can tell so battery technology, it's got a ways to go.
One of my colleagues flew in from Milwaukee, New Jersey or something. James Cross, the old the airline put one place.
Oh my God.
The day to land.
How's your flight coming in here? So we flew in the windstorm.
Yesterday?
Yeah. So it was like,
yeah, it was bumpy when we got close to Japan.
And then all of a sudden it was this, and it was like, okay, they're gonna land the plane. I don't need to cry. Like, just
they know what they're doing.
Right, they're professionals, and the computer knows what it's doing.
Chances are that's what was flying.
Right, exactly.
They weren't hand flying.
Oh, and then they got right down, and it was smooth as glass. It was like, wow, I'm impressed. But like the approach was definitely like, okay,
because the wind was solidly down the runway.
Right.
You know, 30 knots.
We did. It was good almost the whole way. At the end, I remember.
Oh, it was definitely like big smart.
Sorry, when are you talking to Arthur?
So I'm gonna go. They're at the bar right now, and in fact, here, let me just answer.
Yeah. I've been here since 7 o'clock.
So we're going up for tapas.
Please do. We got this toys and tacos. It's going to be great. Great.
Like, these are my people. You did a great job, dude. That is awesome. So, I definitely want to talk with you about what's next. Right? So,
we have space tomorrow.
What do you do?
We have space tomorrow. Same sort of format.
Okay.
Next Monday.
I'll be back tomorrow.
Oh, I'll see you. Thanks, Michael. Awesome.
We were talking about.
Do you need some help, Mary?
Oh, yes, yes,
I'm
yes.
just stacking the gray chairs so that when they come through.
I'll help you. I'm a big believer in moving. Move around. When you find one person who loves you, another person.
Alright, so I'll find out from her. I'm gonna head back to the hotel now. Right, just coming in. Regardless, one way or the other, you're doing dinner with me tomorrow.
Okay, yeah.
And I've got a handful of people who said, yeah, they're interested in doing this.
Oh, good.
I figure tomorrow we'll do something casual.
Alright.
But I'll
I'd love to meet Arthur.
Yeah, it'd be great to talk to you. Yeah, I mean, you might as well walk over with me now if you want.
Okay.
They're still going strong in Captain America. There's a panel discussion. there's a panel going on. Yeah.
I'm going there.
We're losing, like, this,
You know what, Tammy, we should take all the water, if there's any of those, but nobody's really